Hello and good morning, everyone. How are you? I'm not entirely sure what you're happy about because I'm only here to say two things. First of all, this is the thing that you've been listening to all morning, and I'm behind that voice that kept telling to you, Code Dive, a conference you cannot miss. I was hoping for some applause, but okay, fair enough. And second thing that I'd like to say is that we've got a 10-minute delay, so feel free to gossip among yourselves. It can be Star Wars, it can be C++, or God forbid, other programming languages. And we'll be back with the official commencement of the conference in about 10 minutes. Thank you. Na wózku wjechał, to by była konferencja. All right, I think we're ready to make it official. So hello, good morning and welcome. My name is Rafał Motriuk, I'm a broadcaster. Thank you, thank you. I'll be your host today, so thank you very much for having me again. This is Code Dive, and it is now officially open. I'd like to welcome everybody gathered here in the New Horizons cinema today, as well as our friends who are watching online. We have grown so much over those years, and let me say we are people of all possible nations, creeds and ages. And today I'd like to have a special welcome from everybody to our youngest participant ever. She is 10 and her name is Rebecca. A big hand for Rebecca, please. Thank you. It's the 11th time that Nokia has organized Code Dive for us, and to mark the start of its pre-teen years, Code Dive is going back to the roots. Catch my drift? We're going back to the roots. A dad joke number one this morning, thank you. And we are going back to the roots in a figurative meaning as well, because we will be focusing on C++. It was this language, C++, that was the inspiration for this conference 11 years ago. And so our special feature today is this magnificent recycled cardboard tree. Initially, we thought we'd get a real tree with real roots to really hone in on this year's theme, but then we decided we are too eco-friendly, so we got this beauty. And as you can see, it is decorated with carrots, which are also roots. That joke number two. So here at Code Dive, we believe in supportive working environment, and we are not great fans of sticks, and so the carrots are our encouragement for the speakers to perform, and you, the audience, to show extra enthusiasm. On a more serious note, a GloBy ISO C++ standard committee, also organized by Nokia, has just ended, which is why we managed to bring to Code Dive this year the brightest C++ minds. Although C++ will dominate our conference, one of the rooms will explore other state-of-the-art technologies such as cybersecurity, no-code tools, communication and productivity. Now, Code Dive, as you know, is an excellent opportunity to network and exchange experiences, and this conference, of course, is mainly for the professionals, but there will be also talks for beginner programmers. Recordings of all the talks, current and past, are and will be available on our YouTube channel. And this year we have 3 conference rooms, 28 speakers, 24 lectures, 6 lighting talks, and 1 much-loved lunch break. After the conference, there will be an after party at Szklarnia Cocktail Bar. You can walk there. It's literally 7 minutes away. When it comes to snacks and food stations, there's a Pan Pretzel on the 2nd floor. Downstairs, there's a cinema cafe and also a bike cafe and a bakery, Gorąco Polecam. And now, in line with our tradition, we are starting our first networking event. So on my count, I'd like to shout out your name, then your job, and on 3, your favorite programming language other than C++. So just to give you an example, I know, what is there to say? But you can still stay silent if you don't have one. So in my case, it will be Rafał Broadcaster Python. Ready? 1, 2. Very long titles, thank you. And 3. Okay, I heard JavaScript. I don't know about the reaction of the room, but we will check your faces later. We will analyze them on the recording. Now, a quick question for me. How much did you pay for this conference? Exactly. This conference is free, so may I ask everyone to please put your hands together and thank our organizer and sponsor, Nokia. Before we begin, just very quickly, some house rules. Please put your phones on silent. It would be great if you didn't interrupt the speakers until after the talk. There will be a Q&A session after each talk, and we are using an old school method this year, so no fancy online stuff, just regular mics in the room. And this year we have a Wheel of Fortune. You win prizes by spinning the Wheel of Fortune, and you also need to answer some questions correctly. And additionally, if you'd like, you can enter a special number, and then you can take part into a special draw later. The lucky 3 winners will be announced during the closing ceremony. And last but not least, you're going to find the forest on the first floor, where you can grab yourself a free 10-minute massage. Lunch break is at 1 p.m. There is no food provided, so everyone needs to get their own. There are several places to eat within walking distance. And now I'd like to give the floor to our panelists. So let's welcome our keynote speakers first, and I'd like to introduce them as you can see the photographs in our slide. So let's welcome to the stage Herb Sater. He's chair of the ISO C++ committee. Hanna Dushikova. Hanna is staff software engineer at Woven by Toyota. Jason Turner, he is a speaker, developer and trainer, and also the author of Jason C++ Weekly on YouTube. Bjarne Strovstrup is a member of the C++ Standards Committee. He's also a professor of computer science at Columbia University in New York City. Taras Lukaniuk, he's country manager Nokia Poland, and he's the guy who is actually paying for this conference. And the person who makes it all happen, Eva Okołotowicz, Code Dive project lead. So we are going to have a very brief panel right now, and it'll be pretty simple. One person, one question, one answer, and we need to keep it brief because, again, in line with tradition, we got delayed. So just to check your editing skills. So the first question for you, Herb. How, in your view, have ICO C++ Standards Committee meetings evolved over the years?
Probably the biggest thing is the growth in the committee compared to, say, 15 years ago. So at this meeting, we just, less than 48 hours ago, finished our 6-day meeting here in Wrocław. Actually, some groups continued until almost Saturday dinner time, but because they were doing core language wording, and that's very important. But we were able to have over 220 people, 2/3 of them physically, the rest via Zoom. Very productive meeting, representing over 30 countries. So you already did this, but I want to do it for the committee. Thank you to Nokia for hosting us. It was a very productive meeting, and we really appreciate it. Thank you. But that has also caused us, as we grow, to have more subgroups to do work in parallel, and it's great to see all the people interested in C++ joining and working in different domains, and it's really helping progress the standard. C++ is very much a living language.
Wonderful, thank you so much. Hanna, over to you. As a regular contributor to the C++ community, how do you view the role of those programming conferences? I mean, what does sharing knowledge mean for you?
Oh, for me, it means I learned a lot at my first conference. I met people, and it helped me grow exponentially. I went to CPBCon 2017, I think. I met people from the committee. Next year I gave a talk, and next year I gave a keynote at a conference. So it was like exponential. And I'm telling to all my friends, you should go to a conference and give a lightning talk. It will help you to meet people, start, and network.
Thank you so much. Jason, the aim of your C++ channel is officially making C++ fun and accessible.
Yes.
Tell us, how do you make C++ fun?
So when I first put that on the channel, I was working on projects that we made it so that you could interact with a game and you could learn C++ better that way. And I thought, hey, I'm making C++ fun. But since then, I think it applies to everything that I try to work on. I have puzzle books where I try to make things fun. And if you've been to any of my talks or my trainings, hopefully you think those are fun as well. I try to get everyone involved and interactive and engaged. And I think that's really what I'm trying to do in general.
And you try to make your characters pixelated, which is also good fun for old schoolers, I suppose.
Yeah, I have voxel characters all the time on my screens, yes.
Thank you for doing it. Bjarne, over to you. What has been the biggest surprise in C++'s development over the years, particularly from your perspective as its creator?
Two things really related. The first was the idea of using constructor-destructor pairs was there from the first week, and I have been somewhat surprised about how powerful that is and how it's at the bottom of most of the really important and powerful things in C++, and one of the things that distinguishes the language. And then secondly, not so happy, people don't seem to get exceptions. And especially they don't seem to get exceptions in connection with resource management, with constructor-destructor pairs. They try to use exceptions for everything, which is silly because it's for exceptional things. And they want to use it together with sort of pointers that are owning things, which is what you're supposed not to do because you've got constructors, destructors. The two things are closely related. And so one is great, way above what I could imagine. The other one is a bit of a disappointment. And I still hope people will get it right eventually.
Thank you. Taras, I was going through the agenda and the script and so on, and it looks like C++ is going to be mentioned today hundreds of times. I mean, literally, people are going to have fantasies/nightmares about this one later today. Why is C++ so important for Nokia?
Thanks, Rafa. To be honest, I thought you are going to ask traditionally about the budget for next year. So many people asking that. It's confirmed already, just to let you know.
Woo! Yeah,
but
next
talking about the importance of C++ for Nokia. So the modern telecommunication systems, these are huge systems and working in real time and close to real-time environment. So there's efficiency requirement. It's actually critical for us. And here, obviously, C++ is meeting all the requirements. Plus, we are working on embedded systems. I know many of us are not paying on the attention on the cost of hardware because actually it's got decreasing from year to year. But basically, when you're working on a BTS system, those resources, you cannot assume those are unlimited. So here, C++ is a perfect tool allowing you to control your environment. Second thing I would like to mention, it's basically user-friendly. I'll call it like that because, a part of being efficient, you also need, talking right now as a business owner, you need to have people on the market that are advanced and that have unnecessarily skills and knowledge. And obviously, you can these days find a language that maybe will be a bit faster, maybe will be allowing the resources yet more strict. But simply you need to have people on the market to code your systems. And with the C++, there are no any issue. And last but not least, it's future-proof. So the telecommunication systems are changing. So we are not no longer talking only about the classical deployment. So it's Cloud Run, Open Run, or any run, how we are calling it. So it's important that the language that we are using, it's also developing. So on a dinner we had with Bjorn and Herb, I have openly asked, so what's the future of C++? And you know, and the answer was from Bjorn was more than confidence. So look how intensive work there is ongoing, and the last week is proving that. How many new people are joining every month in C++. So the backlog of items, the features that is there to be implemented, it's huge. So you know, this gives us a confidence that there is still a bright future in front of C++, and this gives me a confidence that Nokia and C++ is the right way together.
Thank you. Thank you so much, and thank you for future-proofing it for us. I mean, both C++ and CodeDive. And Eva, you are the person who makes it all happen. And this year's main conference theme is Back to the Roots. Could you elaborate on that? Explain to us what this theme represents.
Last year, at this very stage, we had the pleasure of hosting real founders of the CodeDive conference. And they shared stories about its origin, deeply rooted in C++. Patricia, Dominic, Konrad, warm greetings to you. And actually, thank you, because thanks to you, I have a privilege to lead one of the biggest, but definitely one of the most exciting events in my life, this event. And as a Nokia, you've mentioned, Rafał, previously, we had a huge privilege to help to support co-organizing ISO C++ standards committee, the global committee meetings, which just have happened. And this is not a coincidence that straight after we have a CodeDive taking place. And guess what? We asked some of these brilliant minds to come over as our speakers, and they said yes. That's why they're just there. And because of that, and thanks to that, we got back to our roots, to the first and foremost topic of this conference, which is C++. And this is what stands behind Back to the Roots.
Thank you, Eva. Thank you so much. Thank you, everybody. We'll hear from each of you later. So, yeah, this was our panel. Bjarne, if I can ask you to stay, you're up next with your talk. And, yeah, let's thank everybody for this wonderful panel.
Thank you very much.
Thank you so much. And yes, we are continuing with our keynote. And let me introduce, I know you know the person, Bjarne Stroustrup. He's a designer and original founder of C++, founding and current member of the C++ Standards Committee, professor of computer science at Columbia University in New York City. So we are going to continue with our talk. Let me just add that also Bjarne is a recipient of the Charles Stark.
All right, folks, we have a signal to go, so it's time to start. So our first speaker for today is Andrzej Krzemiński. Andrzej is a software developer since 2004, and he works mostly with C++ in commercial software, which includes safety-related and high-performance system. He's a member of the C++ Standard Committee and Boost developer. He's also a co-organizer of C++ user group Krakow, known to the community for his blog on C++, akrzemi1.wordpress.com. Ladies and gentlemen, Andrzej Krzemiński, the C++ way. Welcome. A big round of applause to Andrzej. Welcome on stage, Andrzej.
Do we need to turn this? No?
I think it's okay.
That's good. So, hi everyone. Thank you for choosing this talk. And today, I'm gonna show you the ways of structuring your code that is characteristic of C++. C++ is a very pluralistic language, so you can code in a very different ways and be successful. But it has been really designed and optimized for certain usage patterns. You don't have to use them, and you can still be successful. But if you do, you immediately start to appreciate how the language actually helps you, how it makes you describe the complex reality of your problems in a really manageable way. And we'll go through 4 of them, which is value semantics, how you manage resources with the notion of sessions, how class invariants work, and how we make and break promises. And 40 minutes that we have is not enough to say everything that needs to be said. So we are only going to scratch the surface. Any of those topics deserves like an hour presentation. But it is enough if we introduce the notions and the ideas here. So first is value semantics. In an imperative language such as C++, we usually communicate with objects. Objects are like boxes where you can store a value and talk about the value, but you can also talk about the box itself. So you can take the address of an object, the size of an object. But if we think in value semantic terms, we try not to think about the objects themselves. It's irrelevant that we try to think that they are irrelevant and only focus on the values they contain. So usually the usage pattern is when my function returns something by value, I need to have an object inside the function. I call it ans here. And to modify its state the way I like, there will be another object in the caller that will be created with a value. But in principle, we don't pay attention to the fact that there are 2 objects. We only pay attention to the value that travels from one object to another. And with this, we get a very important property, which we will show by example. We tend to think, because this is what we are taught first, in mathematical terms of values that we have. But in reality, those are objects that contain this value at this point in time and different value in a different point in time. But to some extent, we can think that those, to some extent, those 2 overlap, those 2 notions. So I want to start with value 1 and 2, but there are really objects A and B happening to contain those values. And then I have a function, max, well, we probably know what it does, and it returns another object by value. And this will be the 3rd object in the game, and it will contain the same value as object B that I have defined earlier. And when later in the game, when I change my object B, and I need to peek into the object C, it still contains the value 2. So the modification to object B did not affect my value in the object C. And this is actually extremely important property, which even has a name. It's the value separation property. We can even define it formally. Like if I have original object storing value V, and I make a copy, and I change the original, my copy stays the same. What does it give me? It gives me that when I obtain an object by values, or I am returned something by value, I know that I am an exclusive owner of this value, that no one else in the world can change this value except me. And now consider data races. Data races are when 2 threads try to access the same memory location, one modifying this value. This never happens. This just cannot happen when only I can modify or see the value. All the data race problems go away when I switch to value semantics. And in C++, this property of value semantics is preserved even when we talk about user-defined classes. Now, this example differs from the previous one because I switched int to some class big int. sorry, and I have the same property. If I create object C from another object using the value from object B, and then I modify B, my object C keeps the same value. And now it may not be that obvious when you come from other languages such as Java, where the same code would mean something completely different. In Java, user-defined classes are returned by pointer, which they call references. And you get the situation where you have pointer B pointing to some object somewhere with value 2, and when you return by value, you return the pointer by value, so you return another pointer that points to the same object and also gives you value 2, as you would expect. But then when you modify the value through pointer B and read the value through pointer C, you see the modification. And you get the not so nice effect that someone else at random place that you don't control can modify your value. The value semantics propagate as you as you compose your objects from smaller objects. Here point is an aggregate, so it's not a very special class. It just makes those two integers travel together. And it gets the same property, that when I get a point by value, I know that only I control what's stored in there. And interestingly, the value semantics property, it also works for complex types, such as stud vector. Stud vector is complex in the sense that what you get on the stack, what you measure with the size of, is only a handle, like 3 pointers or a pointer with 2 sizes, but in principle, it's like a pointer to something elsewhere in memory, to the resource. If we wanted to, if we need to return this by value and naively just copy this pointer, we would get this not nice situation where both those pointers from 2 different places would point to the same resource or memory. So we don't do that, and instead, vector, when you need to return it by value or when you need to create a copy, has an algorithm that is called the copy constructor that knows how to give you another pointer without risking any value separation. I mean, risking sharing, so providing value separation. And it does it by cloning the resource. It knows, the copy constructor knows how to clone the resource, how to allocate the same amount or similar amount of memory, how to initialize all the objects there, so that you have a clone. And then the new object with a new pointer points to the clone. The old object has its own resource, and this way one object cannot ever alter the value of the other object. And we provided the value separation. There is another way of providing the value separation without cloning, and this is called the move operation or the move constructor. Here, when you need to create a new object, its pointer will point to the original resource, but the original object with the original pointer no longer owns or points to this resource. It knows that it now owns nothing and represents no value. And it looks dangerous to have an object that doesn't really store a value, but the thing is, it will be compiler that decides when to use it, and it will only use it in situations where it is harmless. Like here. I have some vector points obtained by value. I can modify it. When I do this pushback, I'm modifying the resource somewhere in memory, and then I am returning it by value. My caller will get the guts of this object, the memory. And my points will become, will point to nothing. Will obtain this null state, but it doesn't matter because this object points goes out of scope. So nobody will notice, except the destructor, that I have stolen its value. So it's okay, there is no way for me to break anything. Until I introduced casts, like remember that stud move is a cast, compiler will only do it in the places where this cannot harm anyone. And the same value separation and move semantics or value semantics rather, work for types that are not copyable, like file stream. A file stream is just a pointer or identifier of a file descriptor somewhere in your kernel. And there is no way of cloning this, so it would not work, but we can still apply this move operation where the new object is now the exclusive owner of the file descriptor and the original object is told that it no longer points to anything. And again, it is, unless you cast away the safety of this design, you can be sure that the compiler will only use it when it knows it cannot do any harm. And it is still practically useful because I can pass those f streams by value, modify them, return them, and it works. So the compiler has been, and the design of the language has been optimized for a value semantic case to the extent that it can sometimes surprise you. Like here, we are going back to the original example when I'm returning a vector by value. So I need some name, some object inside my function. It is called ans here, where I can push values, modify them, and at some point I will return them, and there will be another object, vals, in the caller. And if I wanted to check the addresses of those two objects, most of the cases in all of the platforms, this will be the same address here and there. And this works against what we are taught, at least what I was taught. It breaks the model of function frames, and you may find it surprising, but if you do, it means you are not thinking in value semantic terms, because you should be focusing on the value that travels from object to object, and not the objects themselves that are used in the process. And this works to the extent that I can even return by value things that are not movable at all, not only copyable, but not even movable, like studmutex. And it works because value semantics and return by value are not about copying or moving, but are about providing this value separation. This is all that there is to it. And another way of explaining value semantics is by demonstrating how you can break them. This is maybe even more interesting. And you break them very easily by using shared pointers as members of your class. So suppose our big int was implemented with a shared pointer that I assigned to some allocated memory in the constructor, and it appears very nice because you get the copy constructor, move assignment, destructor, everything for free without leaking any resources. It even can pass some tests. But if we go back to our example here, if I'm creating another object C using the value from object B, I have two shared pointers pointing to the very same memory. And I have created something that Sean Parent would call an accidental data structure. Because sharing, as in shared pointer, is the opposite of separating, like in value semantics. And then I'm going back to the problem of when I modify something through object B, this modification is seen in the object C. Yeah? And if you do it, you will confuse your users. So the short advice is don't use shared pointers as members of your classes, unless you point to the const data. And the same works, although we don't have time to go through it in this presentation, when you pass arguments to functions by value. When you pass by value, you have the guarantee that you are the exclusive owner of this value, of the resources, and no one else can change this value. But we often pass arguments by reference to const, because performance, and we may think that it is the same, or sufficiently safe, or similarly safe, but it's not. When you pass by reference to const, it means that there is an object somewhere outside of your function that your reference points to, that anyone in the world can modify, also as this function executes. It's only you who cannot modify it through this reference, but anyone else can. And sometimes you can get really hit by it. But we'll still do it, because if we pass by value, we may risk a copy, which is expensive. So it's an engineering trade-off here that we have to make. So the takeaway from this section is, with value separation, you get the no aliasing guarantee, that no one will change your object. You have no data races, no surprising from the outside world. Just the thinking, you can just think about the program logic, and it's simpler because you don't have to account for the external reality that could otherwise change your state. Okay, another, the second hero of the day here is how we manage resources through sessions. A resource, by resource, I mean anything that in the system that we are short of, like memory, exclusive access to the display, devices such like mice, keyboards, connections, databases, and they are all globals. We are often taught to think in terms of local state and local objects, and it is preferable. It's of course nice, but in the end, ultimately, nearly any resource in the system is a global. And another feature of resources important for us is that we are short of them. Others are competing with us for the resource. So we have to be sure to responsibly share this with others. And when it comes to managing resources, what helps is the notion of a session. A session is a time that we spend with a resource as its exclusive owner. And what we want of those sessions to be as short as possible, because others are waiting for the resource as well. And the language feature that helps us here a lot, and is sometimes underappreciated, is the deterministic object lifetimes. For any object that you create in your program, in the system, you know that its lifetime ends at the end of the scope it has been created in. And this is when the destructor is called. And we have a number of those different scopes in the language. We have block scopes, that is functions, or what gets inside the braces of an if statement. We have class scopes that work somewhat differently. In C++20, we have the coroutine scopes, which is an even different kind of scope. And we have lambdas that can be used as a hack to introduce tiny scopes in the places where you would otherwise not have them. And the object lifetime has similar properties, or the exact properties that we need when thinking about sessions with resources. Object lifetime starts when it has been successfully initialized, and it ends when the destructor is called. Whereas a session with a resource starts when we have successfully acquired the resource, and the session ends when we have released the resource. And they are so strikingly similar, and this is not a coincidence, that the obvious conclusion from it is that we should be using object lifetimes to model sessions with resources. And if we do that, we immediately get another level of safety in our programs. What we get is that if we can see an object in scope, like S here representing a socket, if we can type anything here like s.write, we have a guarantee from the language that we will do it right, that we will do it while being the owner of the resource. There is no way, no syntactic way of using this, of writing anything to the socket when you have not acquired it as your owner. When you just cannot do it. The syntax doesn't allow you to do it wrong. except that you may fail to initialize an object. You may fail to acquire a resource. And then you would have the S that is in scope, but which you cannot use. And the language has a solution for it. The moment the constructor signals that the initialization failed, all the remainder of the scope is abandoned. Automatically, not, you don't have to code it. It's just there. This is what is called stack unwinding, but we will call it differently in this talk. We will say that the compiler just, not the compiler, but the program abandons any operation that wanted to use this object as. And this abandonment continues. So our function talk was supposed to return a string. Somebody wanted to use it. They will not get the string. So anything else that depended on this value is automatically abandoned. You don't have to do anything. It just gets abandoned. And this abandonment cascade continues. Typically, unless you have a very special case, when you invoke the operation, it is because other operations down below the pipeline depend on it. And if and you don't want to call any of those operations if you know that the previous one failed, because you would be probably risking violating the precondition of the next functions. So if any of the function in the pipeline fails, you just abandon all of them. You keep abandoning those operations until you know there is a place in your program where the next operation does no longer depend on the previous one. And there is not a lot of those situations, but there are some, like in a main server loop. If you are processing a transaction from the customer and whatever went wrong there, you can just abandon the entire transaction and try to start a new one, and maybe a new one will work because maybe the new transaction is completely different. So that would be the place to actually stop this abandonment cascade. And speaking in C++ terms, to put a try catch and execute the next operation. Now, how you can break this? And it's very easily by putting a try catch in random places. Putting a try catch means exactly this. I want to execute the next operation regardless of whether anything above failed or not. And this is a risky thing to do, because you typically don't want to call the operation when you know something earlier in the pipeline failed. And this is actually a good advice in general. If you are not sure whether you should be catching the exception here or not, you probably shouldn't. The default answer is you shouldn't. Exceptions should be thrown in many places, but caught only in few. And this gives us, we can illustrate the situation as a success dependency graph, which is not very simple because the closing here of the socket in our function has special treatment. Because sessions that we are talking about must end no matter what. I mean, no matter if we are abandoning, even if we are abandoning the operations, we still release our resources because others in other threads are waiting for them. Our sessions can span across object lifetimes also. This is actually a very common situation where we have a factory function that returns the object for someone else to use. We have one object F1 here that we prepare and then return. We have another object F2 in the caller. Their lifetimes overlap, but during this overlap, we have started with the move constructor, so the original object is no longer the owner of the resource. So the objects come and go in scope and from the scope, and the notion of a session travels from one to another, but at each point in time, we have exactly one object actually owing the resource or modeling the session. And it is you who decide what is going to be a session in your program. And the criterion for choosing what qualifies for a session and what not is when you observe that you have this need to close something or release something, even if anything else is abandoned. If you see this pattern, it probably means that you need a resource managing class, unless you already have it. And how to break this? It's very easy. Just try to manage your resources manually through manual news, manual deletes, and for sure you will get it wrong. Whenever I see a naked delete in the code, I can be sure that it never passes my review. I can be sure that you have a memory leak somewhere, even if I cannot prove it right now. Because in a complex programs where you have to deal and think about so many moving parts, you will not get this right. And resource managing classes like sockets still have value semantics. That is, when I obtain a socket like this by value, I know that I am the exclusive owner of the object and no one else can modify its state behind my back. Those sessions can be composed in bigger sessions, and the class compositions works nicely with it. So my connection is a higher level session here, and it's composed of a session with a socket and a session with a buffer. And when I decide I am done with a connection, those sessions with the socket and the buffer end automatically and the way I want. So the takeaway from this part is you observe the situation where you need to release something in any case, whatever happens, even when you need to abandon the scopes. And this is where you want to have a resource managing class. Next is invariants. And invariants can probably be best described by an example. Consider these two classes which have identical object layout. I have a point that represents a mathematical point in a two-dimensional space, and I have a range. Not like a stud range or iterators, but like mathematical range, that any number between this minimum and maximum. In each case, I'm using two integers. For point here is actually like a tuple of integers. I have just two integers that travel together, and any combination of those two integers will just work. I could have used a tuple for it as well. I just needed a nicer name. In case of range, this is not that simple, because not any combination of integers will work for me. I do not want to have the mean being greater than max, because this would no longer make sense as a range. And this tension that you can feel right now is exactly what an invariant is. Invariant is a guarantee from the class author that some states of my object will never be observed. And actually, providing and maintaining the invariant is the primary, if not the only reason for having a class proper. Like not an aggregate, but a class with private members and some public functions for controlling access. If you have this, this is because you, whether you know it, whether you are aware of it, you have an invariant to maintain. And the contract here is that it is the class author that guarantees that this invariant will hold. And because of this, the users are relieved of the responsibility of checking this state, because it's already taken care of. The users can now only focus on their business logic. In our case, the business logic is to speak in terms of ranges. So the users now can, we have risen the abstraction level here, because the users now think in ranges and don't think in terms of two integers being in an incompatible relation. And this alone reduces the bugs, because our users now only focus on the business logic and not on the low-level details of integers. And our implementation of the class will look like something like this. We will probably need to provide some way of modifying the state, but we will need to control how this modification happens, because now it is our responsibility to guarantee and maintain and protect the invariant. So maybe I will have a throw expression here. If you give me the wrong combination of values when you need to set them, I will throw an exception, because I don't want this operation to continue. Or maybe I will do something like on the right-hand side. That is, I will declare a precondition. That is, I will say explicitly that it is the caller's responsibility to give me only the good combination of integers. There is no way to enforce it in a bulletproof way, but at least it is a way to make clear whose responsibility it is to give me the to pass the right to have the right values here. Whether it's my responsibility, whether a caller can give me any rubbish they want, and I am telling the good values from the bad values, or if it's the caller's responsibility to give me only the good values. Well, at least we make this clear. But in any case, this is a form of protecting my invariant. And to be more specific, the invariant holds whenever a user can observe the state of my object. So that will be after the object has been successfully initialized and after any function from the class interface finishes. And by class interface here, I mean public member functions and friends, because they are also part of the interface. And we could argue whether protected member functions also fit into this model, but this is not the scope of this talk. But the more important part here is that the invariant holds even if my operation ends in exception. So it's not like some people say that the invariant is automatic postcondition that applies to every function. It's not true, because the postcondition only needs to hold when the function exits successfully. Invariant holds even if the function ends unsuccessfully. And in fact, in my example here, I threw an exception precisely because I wanted to protect my invariant. Throwing exceptions is a way of protecting the invariant. And you can have different kinds of invariants. Sometimes, like in our case, we could express it as a C++ expression and evaluate it if needed. So this is very convenient. Sometimes an invariant is quite formal, but you cannot evaluate it. Like, we may agree that the invariant is that I'm storing an array or holding an array that has 0 at the end. But there is no way to check it. If you try to check it and it's not there, you will cause UB or run into the loop that doesn't end. You don't want to check it. But you still want to communicate that you have this invariant, that you take care of it, and your users don't have to. And being a session, having a resource in session is also a form of invariant. And we've talked about the move operation before. And you notice that there is, when you do a move, you put your object into this special moved from state, or we can call it a null state, or whatever. But in any, however you call it, is this special state that is somewhat dangerous because you no longer have a resource to represent. So like in our case with sockets, when we introduce the move constructor, now our class socket no longer represents a socket, but it represents either a socket or a not a socket. And now our users need to be prepared. So we have, with this, we have lowered the abstraction level. Now our users need to think about two things, which is not very convenient, sorry, but it's fast. So again, we have an engineering trade-off here. We need to choose between two valuable things. And sometimes one choice is good, sometimes the other, but we have to be aware that we lose something either way. So the takeaway from this part is when you feel or when you see that the same condition is being checked time and again in your program, it probably means, or it could mean that you need an invariant managing class here to make your program simple. And always try to communicate, not only to other users, but to yourself, what the invariant of your class is. Because when you do that, you start thinking in these higher level terms. And the last one is about making and breaking promises. So our functions will usually have names like fetch data from database. Or just, they are very positive in what they do. But in reality, you cannot guarantee that. You cannot guarantee that you will fetch the data from database because it is not entirely in your control. You don't control whether you lose connection or not, whether the table you wanted to read is there, even if it was there just a second ago. So the promises that you make is quite sloppy. But the thing is, those sloppy promises are good enough for our callers to make their sloppy promises. So the guarantee that we give with our functions is that I either deliver a promise, and by the way, when I say promise, I do not mean anything like stud promise or the coroutine promise type. I mean promise like in English language. And so our guarantee is that we either deliver the promise that we made, or we will have the runtime launch this abandonment cascade, that is stack unwinding. And this is good enough. So whoever calls our function get count from database maybe will not get the promise that we made, but if they don't, they will just be abandoned. So it no longer matters. No, there will be nobody there who relied on our promise because we will abandon all of them. So our get count from DB is a maybe get count from DB. And if we fail, our compute functions that promised to compute something will also communicate that it failed to deliver its promise. So those promises compose, and we have a nice way from, if anyone expected this of us, we will just kill them. So actually, this is how it works. We kill anyone that would complain. And we have actually have a better name in C++ for calling those promises. Those are post conditions. This is what a post condition is for and how it works. And the important observation here to be kept in mind that managing resources is not part of this promise we make. Like we have, suppose that we have this function get data that promises to get you data and nothing else. You don't have to know that we are opening a socket and that we will be closing a socket. What our contract is that you will get the data, and that's it. And dependency works like this. Of course, if I cannot open a socket, you may not know that there is any socket in the game here, but if I cannot open it, there will be no way to connect to the other machine and to get you to read the data. So we will have to abandon this idea, and you will have to abandon the idea of using this data. So everything else here needs to be abandoned, and obviously there will be no closing of a socket if we didn't open it. But maybe we did open a socket, but failed to establish a connection to the other socket on the other side. And then we still will not be able to get you data you wanted, so we will have to abandon, you will have to abandon your idea. We'll have to cancel all these operations, but we are not abandoning the closing of a socket, because there is other threads or other parts of the program that still need to work with this socket. So we have to make sure that this works. It is not the promise to our caller, but it's promised to somebody else that we have to clean it up. But it can also happen that We have opened the socket, we had successfully communicated with the other machine, and we have data to return to you. And we are closing the socket now, and it fails for some reason. And this is where it is important. Closing of the socket is not part of our promise. So there, you will still be able to use your data. There is no reason for you to abandon your operation. We have, of course, messed. We had made somebody else's lives harder now, because there will be no socket to share anymore. But it's not part of the promise. We will not cancel our callers. And this is why we are told not to throw exceptions from destructors. Not because there's some terminate being called, but because it is logically incorrect thing to do, to cancel, to abandon the next operations, only because we didn't do something we never promised. And this is why managing resources maps so nicely into a constructor and destructor semantics. And we've seen that abandoning scopes requires closing of the sessions, which means that we have to make sure that our sessions remain closable when we report failure, which means objects must be destructible when we report failure. And our objects that report failure may survive this abandonment cascade, so they may need to be inspected or reset. So you have to give this guarantee also, but you decide what subset of operations is still valid when your object reported failure. And the very minimum is that it needs to be destructible and it must still maintain its invariant. And actually, we are getting till the end. Hopefully, you were able to see that those 4 aspects are pieces of the same puzzle. One cannot even work without the other. If you want to have value semantics for anything simpler than ints, you will need to manage an invariant. You will need to manage some resource. And for managing those, you will need those failure and success dependencies. So it's actually one whole that we could call the C++ way. And that's it. Thanks for listening.
Thank you very much, Andrzej, and big round of applause to Andrzej. And I can see in the end that actually you managed to fill up the whole room while having this very strong competition from Björn. And Andrzej will take now a couple of the questions from the audience. So if you have a question, please raise your hand and we shall provide the microphone for you. So before you ask the question, please wait for the microphone. Questions? There is one in the middle of the room.
Hi, so I think when this comes on YouTube, I will, if this comes on YouTube, I hope it will, I will point all my Java friends coming to C++ to this presentation, because one of the biggest issues I see is the value semantics. It's very unusual for people who are coming from managed languages. Even more than memory allocations, actually, it looks like value semantics are more problematic. And one of the usual mistakes I see all over the place is copying resources where they don't have to, because this is not the case in managed languages. And what do you think of how to prevent such wild copying of your resources? I found myself, for example, instead of having pass by value, I sometimes, or pass by const reference, I sometimes put a r-value reference. So I'm forcing them to either explicitly move or copy the resource. And what do you think about that as a prevention of having wild copies because of the value semantics?
Mm-hmm. So I'm not sure about I would call it a trick with r-value references. It probably works in my case, in your case, in particular cases, but it's not something that I would just teach people upfront to do, because it is very likely to get it wrong. So what the resource managing classes do often, because a lot of resources cannot be cloned, like you cannot clone a thread. So they don't provide the copy constructor at all. Like you don't have them. The classes are movable and not copyable. And this alone, if you can afford to do that, solves your problem. Because you don't have to protect anymore anyone, because they are automatically protected. You just cannot copy it, whatever you do. I think the problem is with classes that manage resources that can be cloned, like vector. It's very easy to clone the resource. And then the situation is difficult because another goal that we want to have is to have those vectors behave like integers. With integers, it's uncontroversial. Yeah, I want a copy, another copy, and it's okay. With vector, it's, do you really need a copy? So this is the risk. And yeah, Rust solves it in a different way. We cannot afford it because we want this uniformity. So yeah, the only option we have is, as you say, to do the very controlled way of defining the references. But it comes at the trade-off of doing it very easily doing it wrong. So yeah, this is something I've done also in the past, but I'm not comfortable actually advertising it to everyone. Thank you, it's a good question.
Thank you. And I think we have time for one more question. All right, I don't see any, so thank you very much once again to Andrzej. So big round of applause.
Thank you.
Now we'll have 10 minutes break, and at 10 we'll have another lecture. So please stay tuned. Thank you very much. Welcome everyone after the break. Please have a seat already because we are going to our second presenter in room 9, who is Wenjin Yu. And Wenjin is an application engineer at MathWorks, specializing in embedded software development and code verification. With a deep passion for creating performant and reliable critical embedded system in C, C++, he brings a wealth of experience to his role. Wenjin spent 10 years as an embedded software engineer, including 7 years in automotive industry, where he gained extensive expertise in EV charging system and high voltage battery systems. His strong background in optimizing C, C++ performance equips him with deep knowledge in performance engineering. Ladies and gentlemen, Wenjin Yu, unlocking performance in C++ from profiling to optimization. Big round of applause.
Thank you. Do you hear me? Fine. Thank you. Good morning, everyone. Thanks for joining. My name is Wenjin. As our dear host has introduced, I used to work in the automotive industry, especially I worked on battery management systems and charging systems, where optimizing software was important because it was critical to make sure that batteries will operate in efficient and reliable manner. And along the way, performance engineering not only became a technical challenge, but also becomes a passion. So that's why I'm so excited today to talk about this topic, how to unlock the performance in C++. Performance, the word often sparks different feelings in different developers. For some, it is very thrilling challenge to be dealt with right away. For others, we only need to look at performance later on when something goes wrong. But no matter where you stand, the truth is, in today's world, performance matters more than ever. And so today, the goal is really to talk about, we would like to explore the journey from understanding when and why performance matters to using the right tools, and when we will look at then we will look at different techniques we can apply to improve the performance of the program. And my goal today is that at the end, I would be able to provide practical insights and a clear framework so that you will feel more confident in your future projects when you need to deal with performance issues. I hope that in the end you could have some rough ideas for future projects, how you could make data-driven decisions and how you can achieve significant performance gains without sacrificing the quality of your code. So without further ado, let's start today's talk and unlock the C++ performance. To kickstart today's talk, let's imagine a conversation between coworkers where one colleague might ask, is performance our priority? Do we need to care about performance? The other would just answer, of course we do. We are using C++. What a silly question. Of course we care about performance. But then the first coworker will ask, okay, then when exactly should we look at the performance of our code? The question is not always so straightforward to answer. That leads to the most crucial first step in this performance optimizing journey, which is setting the right performance target. It is very important to have requirements on performance, because without requirements, we don't know where we are going, and we don't know when to stop. Requirements can be explicit or implicit. Explicit requirements would look like something, this task needs to finish in that much time. Implicit requirements would look like something from the user experience, common sense, let's say. We all know that humans have tolerances when they deal with computer programs, and those tolerances can be a guideline for us to define performance requirements. For those who are familiar with the V model, which is a product development cycle, we always start with the requirements. Then we developed into detailed specifications. Then we start to code. And this idea or this model applies perfectly to our problematic as well. We need to first set the right performance target. The purpose of setting this target is really to avoid optimizing the code too early. There's this famous quote from Donald Knuth saying that premature optimization is the root of all evil in programming. It is a little bit dramatic, but it does highlight a lot of potential issues if we optimize too early our code. Because we might end with very complex code, we might damage the code maintainability, and worst of all, we might waste time because we were working on the wrong part of the code, which doesn't have significant performance issues. And in a lot of the C++ coding guidelines, in the section of performance, there are a lot of recommendations, what you should do, do this, do that. But almost in all guidelines, the first rules are always, are you sure you want to optimize it right away? Perhaps not. So that's something to be taken into account. So the solution to avoid optimizing too early is to profile. Always measure before we make any significant optimizing efforts. And then using profiling techniques, we can focus on correct path of the code, and we can measure to really find the hotspots in the program so that we can work on them. How to do profiling? Fortunately, we have a lot of tools on the market, and those tools use a lot of different profiling techniques. To just give you a little examples, we have Visual Studio Profiler, which is exclusively on Windows platform. We have also Valgrind, which is cross-platform, but it is used more on Linux. There's Perf for Linux, but the idea of using profiling tools is to gather data, and we want to see with the data backup that how the CPU is used, how the memory is used, and how many calls are made in this program. Of course, using the right profiler for your type of situation is important, but we need to know a little bit more about the profiler to know what the underlying techniques the profiler are using, so that we can avoid some of the drawbacks certain profilers or profiling techniques may introduce. For example, if you are using time-based techniques to profile, we should pay attention that sometimes the time is too coarse and your performance bottleneck is at a different scale. So it is possible that the bottleneck is not detected by the tool. And depending still on the profiling techniques, it is possible that you have interferences from other processes in the operating system. And sometimes you are not always able to reproduce a delay in the profiling process because the delay is caused by some random events. It is also to be taken into account that when you profile a already optimized program, since some function addresses will be obscured, it is difficult to map the profiling results back to the source code because you lose this kind of direct translation. So the idea is really to learn a little bit more about the profiling techniques and the profiler, choose one that fits for you. If it doesn't, then there are some complements solutions that you can use. For example, the old-fashioned way, you can introduce code directly in your program and you do the mirroring yourself. You can count the CPU cycles, the exact time. Of course, doing that way, it doesn't eliminate all the problems with the profiling techniques drawbacks in certain areas, but still, oftentimes you will have quite accurate results as well. A different complementary solution would be to debug. Using a time-based debugger, you could combine the breakpoints with the cost, the stack trace, and you gain more insights about where the potential bottleneck might be. So imagine that we have seen some profiling tools and techniques, and we have already a foundation to make some smart decisions on where we should look at and where we should work on. But identifying the bottleneck is really the very first step. Now let's move from really analysis to action, where we can start to optimize our code. In the next section, we will explore some strategies to optimize the code. I would think that algorithm improvements is the area where we will bring the most performance gain with the least amount of effort. And I just want to use a very example to show the algorithm improvements and how they can bring performance gains. It is a very trivial example. It is the Fibonacci implementation. Now, we all learned that at school. It is very straightforward. It is great to illustrate the idea of recursion. The code is short, it's clear, but it is terrible in performance. Using the big O notation, we clearly see that the time complexity will be exponential. So every time we need to calculate the nth number, we need to calculate twice for the numbers before that number. So it's terrible for performance. Now let's bring some more optimization to this implementation. Let's implement that slightly different. So since we are just adding 2 previous values, we can just traverse the sequence, and along the way, we will keep always the 2 last elements, and when we need the next one, we just add the 2 last memorized values, and we add them. So very straightforward also. Now we are doing much less. We're just traversing a sequence. So as n gets larger, the time complexity will be linear. So compared to the slow implementation, that's much better. And the code is not bad. It's, I mean, in 5 seconds, we can reason about what the code is doing, and it's quite clear. Is it possible to go even further, even faster? Well, we can. And this uses a different technique. The idea is just to multiply a base matrix n times. At the ending, the resulting matrix will be mapped to those Fibonacci numbers. And it's just a matter of getting the right element from that matrix, and we have our result. But you may wonder, we still need to multiply the same matrix n times. It is still linear time complexity, right? It doesn't change much. Well, that's where the optimization comes in. When we do the computation of x to the power of n, we can use this technique called exponentiation by squaring. Basically, the idea is to reduce the work by half, and we do a recursion. And the idea is to, instead of calculating x n times, we first calculate the x squared, and then we reduce the n, the power, by half. And then each time the x squared becomes the new base, and we can continue from there. So a couple of recursions will yield very, very fast to the final result. Or you don't care, sorry, you don't care too much about this formula. It's just, the idea is the same, just we need to handle the n being odd or n being even, but otherwise it's the same idea. So combined, those 2 kind of techniques give us a complexity of log n, because every time we reduce the amount of work by half, and that's very good and very classic pattern. So now we have a fast implementation, and it is log n complexity, but I must admit that the code now looks not so clear. If you don't know the mathematical formula behind the scenes, it is difficult to follow. And one may ask, can we go even faster? Are there the fastest implementation for this particular problem? Well, there is faster algorithm implementations, but there will not be like constant. It still be in the realm of log n, but you are tweaking the constant or the coefficients in this complexity. So I would like to wrap up for this section by looking at what we can really achieve with algorithm improvements. Of course, in real life program, you will rarely have a problem that is as simple as implementing a Fibonacci sequence. But the idea still applies. By implementing a different algorithm, we can achieve what we couldn't. From the graph, we see that with the slow implementation, even the most powerful computer will struggle when the n gets slightly larger. But with the normal implementation or the fast implementation, we can really scale without any problem. So algorithm change can bring the most performance gain. We can go on and on, searching for the perfection, the one most perfect algorithm to fit our use case. But that is not always possible to achieve. And perhaps we can look back at our performance requirement. If our implementation meets the need, perhaps we need to settle without investing too much more time. Taking the two implementations, the normal one and the fast one, when n is large, the fast implementation is always faster. Well, that's to be expected. But when n is not that large, we see that the normal implementation is faster. And that brings me to the conclusion. When we deal with algorithm improvements, when we taking account of the performance target, perhaps we need to make a trade-off between what is readable and what is performance, and then we settle at a good enough algorithm. Because if in our use case, the n is not that huge and the code is much more readable in the normal implementation, even though the complexity is higher than the fast implementation, I would still go for the normal implementation. Okay. That is for the chapter of algorithm improvements. Now imagine that algorithm improvements do not bring more performance gain anymore. Well, we can still achieve some significant performance gains by using compiler capabilities. Well, nowadays compilers are very powerful and they can use a lot of sophisticated techniques to optimize our code. The best part is using the compiler, usually we don't do a lot of things. We can really enable those things with minimal effort. Now in this section, we will explore how we can use those capabilities from the compiler and optimize the code, using the compiler to optimize the code for us. To use the compiler, we first know a few things that compilers are doing for us. For example, just a few examples that of the optimizations the compilers is doing for us. First one, function inlining. When in the source code you have multiple functions, one function is called, but it is very small. The compiler will see that and replace the function call by the actual function body, thus optimizing away an extra function. Well, in this way, we avoid the overhead of a function call, we avoid the overhead of a parameter passing, so on and so forth. And we will see later that there are some other benefits that opens doors to other types of further optimizations in the compiler. Second example would be loop unrolling. When the compiler sees in the source code that we have a small for loop and the size can be decided at compile time, perhaps the compiler will just replace the for loop by very simple statements. Thus, we will avoid the temporary variable, we will avoid branching in the for loop, and we just have very simple code. Also, it seems very simple and straightforward, but it is quite important because also that provides a solid ground for the compilers to continue with other further optimizations. One last example is called devirtualization. When we have a parent class, we have a child class that inherits the parent class. Both classes have a virtual functions, and in the function we define an object of a child class, we define a pointer of the parent class, and we assign the address of the child object to the pointer, and we call the function on the pointer. Well, normally we will need to go follow the address of the object, and then we find the virtual table, and we go follow the lookup, and then we will find that this function is mapped to the child class version of the function. And then we will load the code instructions, and then we will execute. So a lot of indirect steps. But when compiler sees this code, it can make a decision that the pointer P, although it's defined as a parent pointing to a parent class, but in reality, the actual object itself is child. So the compiler will do the necessary things to optimize away these indirect steps and directly go after the code instructions for the child version of the function. And we avoid a lot of intermediate steps. So we can use those things. So those are what the compilers are doing for us. And now it's time for us to use that. And fortunately, almost all the compilers provide those optimizations by flags. We can just specify which flag. And for example, for the example we have seen, there are flags for -f, -f inline functions, -f unroll loops, -f devirtualize. And we can just use them on the command line when we invoke the compiler, and then that optimization will be activated for us. But usually we don't go this detailed, because there are a lot of presets of optimizations that have been done for us, and there are a lot of flags that are working together. We really need to start with first of all the presets of optimizations, and that's the -o, the optimization level 0, 1, 2, 3. With the level going higher, we're adding more and more -fs to the previous level, and there's also presets, so optimization levels. Dedicated for reducing the size of the program or enhancing the experience of debugging, -os and -og. And that's how we can enable those optimizations when invoking a compiler, but we can also instruct the compilers in code to help the compiler understand our intention in the code. We can use the keywords or some directives from the compilers. Volatile tells the compiler to not optimize this thing away. Using const, the compiler will do the calculation at compile time instead of in the runtime. Static keyword, when it is used to limit the scope, it could help the compilers to improve the interprocedural optimizations and some attributes that we can use from the compilers itself. The biggest takeaway from this section using compiler is that they are extremely smart. I mean, they are smart, they're extremely powerful, and we should really learn what they are doing for us, how to instruct them to optimize the performance for us. Okay. Well, at this point, we have explored two of the most common ways to optimize performance. One is to improve algorithm, the other is to use compiler optimizations. And we really spent minimal effort. And but what if the application has unique requirements that you really want to squeeze the last bits of the performance? Well, in this case, we can take a look and how to fine-tune to really gain the precise performance gain. Well, the fine-tune or micro-optimizations are perfect examples of programming anti-patterns, and the idea is to eliminate those programming anti-patterns. Those anti-patterns may include expensive operations that you write in your code. You are not doing some necessary processing, and you are not using the most performant version when you have multiple alternatives to achieve the same thing. You are not using the string the most efficiently. There are many, many of them. Just a few examples. To shorten the screen, instead of using the resize, you are using substring. Well, with the fix is to use resize, thus you avoid creating a separate string and assign to the original one. Another example, no pre-allocation, when the use case is that you have a container for which you know the size, the number of elements in that container will be fixed, then the best practice is to pre-allocate a part of memory, then you add the values. Another example would be the copy, the move operations. Well, sometimes we use the copy, the move operations because clearly we have performance intentions, but it is prevented and falls back to copy operations. For example, you are using that on the const parameter, then it falls back to copy. And to fix that, we just remove the const keyword. Of course, if that makes sense. Well, in this little code, there's no other implication, so we can use that. I can go on and on. There are a lot of programming anti-patterns. Unnecessary padding, missing const expression specifier. We're using the size method instead of the empty to verify if a container is empty, so on and so forth. There are so many, and C++ is such a complex language. We are not always aware the impact of the code in terms of performance. So it would be beneficial to use a tool to check this programming anti-patterns in a consistent way. So I'm from MathWorks. MathWorks has this tool called Polyspace, which is a static analysis tool. It does a lot of things to verify the code statically, among which there's a lot of checkers for performance. So basically, the idea is to identify all the programming, I mean, not all, but a lot of the programming anti-patterns, and it gives you a nice summary of what might go wrong. There's a description of the problem, there's the risk associated with this problem, and the tool also provides a fix for this problem. There's bad example, potential fix, and good example. So using a tool can be very beneficial for the developer to help him keeping aware that what I'm doing now has an impact in performance, and along the way I could use the alternative to improve that. So what can we expect from the effect of micro optimizations? I would say you can see the performance improvement when you isolate the optimization and the code you are working on, but the performance improvement will vary based on the compiler, the library implementation, and the environment. But from a different angle, a lot of those micro optimizations, they are good programming practices. Well, those good practices will help, some of them will help the compiler to optimize further. So indirectly, those micro optimizations, while it brings a very precise performance gain, but indirectly they will impact also the overall performance of the program. So far, we have covered techniques about that are accessible to everyone. Working on algorithms, working with the compiler, using tools to detect the programming anti-patterns early on. They are great tools for almost all developers. It doesn't require too much of expertise. In some situations, however, we need to push the performance improvement even further, and that's where we would require a little bit more, advanced optimizing techniques. Oftentimes, that will require a little bit deeper understanding of how the program interacts with the underlying hardware, the memory of the memory system, and the parallel processing. So in the next section, I would like to touch on a few slightly advanced methods, exploring what you can use to fine-tune the performance of your application. Well, of course, there's no surprise. We need to leverage the hardware. Back in the day when Moore's law is still relevant, it's still relevant in a way today, the strategy would be you don't do anything. You just wait and get, wait for 2 years, you get twice the speed. Because when Moore's law is relevant, it indicates that the number of transistors in a CPU will double every 2 years. So systematically, when you update your hardware, you get twice the speed. So how many programmers can promise that, give me 2 years, I can bring you 200% performance gain? Well, that's difficult. Well, now Moore's law is less true compared to like 20 years ago. The trend is different. We are using multiple cores, multi-threading, the GPU for parallel processing, but the challenge is that we need to convert the problem to be adapted for this kind of processing. Itself is a challenge already, without mentioning the performance improvement part. CPUs are becoming more and more intelligent. They can predict the branching more intelligently and more precisely, so that helps. We can also use the extensions to CPUs to accelerate the processing, especially you have a lot of similar types of data. For example, the SIMD extensions for different platforms. We started by seeing them on x86 platforms, basically that we have a big vector instead of processing one integer, for example, at a time. We will process multiple integers at one go, thus saving a lot of time, especially if you have a lot of matrices, then that will accelerate the speed of the software. Well, now we are also starting to see that on embedded processors, for example, ARM. The last point is, in the end, very important. That is to use the cache efficiently. So far, I have been deliberately avoiding this topic because it connects to a lot of things. It is related to the compilers, it is related to the micro optimizations, and it is related to memory. And now I would like to spend a little bit more time on this topic to see how cache can impact the performance of the program. So the challenge is that RAM, we have a lot of RAM. This is the memory, but it is slow. We have also cache, but cache is much faster, but cache is really small. But the difference already between accessing the cache and the RAM could be huge. If we take a look at this architecture, we have different levels of cache, and the time needed to access L1 cache and the time needed to access the RAM there could be a difference of 100 times. So imagine that all the data we need to perform a logic is directly in L1 cache instead of being in the RAM. So theoretically, we can expect 100 times of a performance gain. Well, that's huge. Well, theoretically. So the solution is that, so since cache is not always used efficiently, so the solution to this problem is really to improve the cache usage. How we can help the compiler, the system, so that the cache is better used, or the memory can be better organized to help the cache usage. So that's really our solution. The key word here is locality, spatial locality and temporal locality. The idea is really to, using cache, we try to, when we need something, we will load a chunk of data to the cache, and next time we access, there will be a high chance that the thing we want to access is already in the cache. So we need to follow this idea and make the program so. To improve locality, the idea is really to, if you have data, try to store them together. if you have code, try to make them more compact. So to make the data, to store the data together is typically where we see the difference between array and a linked list. Usually, for the same problem, the array performs better than the linked list, because linked list, we have a lot of scattered memory, while the array is a contiguous memory chunk. When we load something to the cache, so there's a higher chance that the whole thing will be in the cache instead of the RAM, but it is not true for the linked list. For the code thing, we need to make the code compact, or we need to make the code inline. In this case, we have a single chunk of a code instead of going to fetch code from a different location. That's why function inlining is so important. We really put the code instructions together, and when we load one instruction to the cache, we load the whole chunk in the cache, and next time when we try to access the next instruction, it is already there. So we save this long iteration time from the CPU to the RAM. And fortunately, the compilers are doing a lot of optimizations for us to improve the layout of the memory of the code, as we have seen. So indirectly, they will improve the cache usage for us. The last point is really interesting, is that we need to follow performance optimization practices, how that could be helpful for cache, right? Well, it turns out those optimization practices are actually what the compilers are doing for us, what the cache usage is requiring. We inline small functions, thus reducing the locality, improving the locality of code. When we align code and the data, then when you load a chunk of data to the cache, you don't leave just the 1-2 bytes aside, and you need to switch the cache constantly. At last, you would we would like to make the data structure more compact and smaller, so that they are easy to handle on the stack and things like that. You could have more data that could be fit into the cache, so that the processing, when it requires, all the data is already in cache, so that accelerates things and avoids too much cache misses. If you have unused variables and you have unreachable code, try to eliminate them, because that reduces the stack size, for example, that reduces the size of one particular function. So all that is for improving the cache usage. I guess the takeaway from this side is from this section is really that although those seem like very small things, we are really doubtful if they could lead to a big performance gain. But at the end of the day, indirectly they can, because they have further implications or impact on the overall performance because of a cache usage, because of a compiler optimizations. So don't overlook those small modifications, and they are possible to bring big performance gains. So far, we have established a solid basis to really deal with performance issues. Of course, we can analyze performance issues. We can try to find methods to improve them. But let's not forget that there's the last step of this whole journey, which is to verify that everything works. It seems plain, but we need to validate that the optimization works and works on the target hardware. And we need also to make sure that the code is correct. I have seen personally more than once that when we change the optimization level, some bugs in the program appeared. Well, unfortunately, the developers are to blame, not the compilers. So we need to make sure that that is still the case. Okay, I think that's we are towards the end. In this wrap-up section, I would like to take a look back at what we have been discussing. So we start by highlighting the importance of profile before you do any types of optimization. And then we go on with the importance of performing algorithm improvements to bring the biggest performance gain. And after that, we start to look at the possible compiler features that we can use easily to bring up optimization to the program. And for afterwards, if we are happy with those two most common ways to improve performance, we have taken a look at the very precise performance gain, where we do fine-tuning to solve particular problems by eliminating the programming anti-patterns. At last, we touch on some of hardware-specific optimizations, where especially the cache usage is important. And we have seen a few methods or ideas on how we can optimize the cache and memory access to improve the performance of the program. So at last, I would like to bring a call to action. I know that performance engineering is a very complex topic. There's a lot of things involved along the way, a lot of interesting topics. We need to learn a lot of things, actually. How the profilers are doing, how the profiling techniques are used, and when it comes to algorithm improvement, how we can design better algorithms to solve the problem. And you have everybody used the compiler, everybody used the flags, but perhaps experiment more. What the compiler is doing for us, do some benchmarking with or without certain flags to see if that difference makes a sense, and just experiment and know better the compilers. Also, it is very important to adopt programming best practices from early on. Not only you develop the good habits when you write code, but also, as we have seen along this talk, that those little things might be intertwined with other big things, compiler optimizations, cache usages. So indirectly, they also contribute to the overall performance improvement of your program. I guess for today, the biggest takeaway would be this performance engineering is really about problem solving. Problem solving is very fun. It has a lot of things so that we can learn, and it's a good feeling that when we solve a problem and we achieve something. So I would really love to see that somebody just achieve a double-digit performance gain or triple-digit performance gain with just a few change in the operations, or a few by removing a few lines of code. That would be wonderful to see. So, and the takeaway is optimize and have fun, and share your experience with everybody else. Thank you. That is the end of my talk.
Applause.
Thank you.
Big round of applause to our speaker, Wenjin. Thank you very much for the speech. And now we'll take a couple of the questions from the audience. So please go ahead, raise your hands. We have first question here. Can you wait a second because it's not working?
Is it working now?
Yes,
Okay.
go ahead.
Can you please show the 26 slide again?
26.
Yes, example with the string, because I'm not exactly following how is it an optimization. Couldn't we use like a right reference?
Because it's a move, it's move operation, and here you have the name being the constant reference.
Sorry,
Yeah.
I thought that we were moving away from a moving. So my bad.
Okay.
All right, thank you. Another question here.
Thank you very much for your talk. And yeah, I have a question regarding empty and size function. I know that there is a dedicated function empty for checking if containers is empty, but can you explain what is exact difference between those in meaning of, I don't know, assembler code? Is only matter of one additional assembler in structure, or it's something behind there?
I'm sorry, I'm not following. Could you repeat the question?
Okay, so yeah. So in the guideline, I see that there is preference to use empty function instead of size. And what is exact difference in the assembler code, and how empty function is faster comparing to size?
Okay, I see. So the purpose is to check if the container itself has no element in it. So the inefficient way would be to use the size method and check if the size is not equal to 0. So that is not necessary because sometimes in the implementation of size you need to count or something like that. So well, you don't actually, because the empty method perhaps it has implementation of constant complexity. You just give you the answer right away instead of different implementations of a size which might be more expensive than const.
Okay. All right. Thank you. Any other question? Okay, I can see the question on the other side of the room. We'll get back to you, sorry.
Yeah, thanks. Is there any particular profiler you would like to recommend? For example, the one from Google or?
Sorry,
yeah, here.
Sorry.
Yeah. Are there any particular features which are the main benefits in the one you are using? Or could you recommend something?
The main benefits of the profilers?
Yeah, could you recommend a particular profiler or?
Well, there's no like one answer fits all to that, because that really depends on the types of programs. For example, if you are trying to really do the profiling on a computation-intensive task, or you are really trying to see the cache misses. So for each usage, you would like to search for a different profiler for that purpose. Using Valgrind, it is most famous for checking memory leaks. So the memcheck is widely used for that. Using the perf on Linux, that is more for the system-wise profiling. You have not only the metrics on your application code, but also the system calls. So that depends on if that sort of things are important to you as well. Of course, Visual Studio Profiler is only working on Windows. So there's also other aspects, not only to the CPU usage and memory usage. There are also the representation of the results, how it is presented graphically to you so that you can get the insight immediately. So apparently, Visual Studio Profiler is very strong at that, but perf is notorious for being for having a steep learning curve, because everything is very command line heavy. You need to do some processing to get a graphical representation of the results, and from there you start to see where things might go wrong, and so on and so forth. So I would say the advice would be first, learn a little bit about the different profiling techniques of each profiler. See if what you are doing can be met with those profilers, and experiment. If you like it, stick with it. If you don't, try a different profiler, and perhaps it works better.
If I can ask, is there anything you would like to recommend as a profiler in the case where we would like to analyze the background of the neural networks? Yeah, because for example in Python the background is written in C++. Yeah, so is any particular tool you would like to recommend in such a case?
Could you repeat the?
Yeah, sure. Yeah, because for example when we train neural networks, yeah, in Python, in PyCharm, for example, yeah, the real background is of course in C, C++ because it's just faster, yeah. And I was considering, would you like to recommend any particular tool for analyzing such a behavior, yeah? So the background of the neural networks, which is in C++, yeah. So for example, we are training neural networks, yeah, but we would like to analyze what's in the background, which we
in the background.
Yeah, in the background, yeah, because it's, yeah, C++ is in the background in such a cases usually.
I don't know what that means, but usually you will launch the provider itself is a process. You will also launch your application, which is also a process. It depending on the techniques, perhaps there are some sampling-based techniques that doesn't require to be always on the foreground. But at the end of the day, you would like to try to avoid having too many processes so that you don't pollute the result and dilute the result. So perhaps I'm not comfortable recommending doing the background profiling in this way.
All right.
Sorry if I didn't answer that question.
And we have one more question. There is a guy waiting for a long time already, so let's go.
So I wanted to ask, because you concentrated mainly on algorithm improvements and working together with our compiler to get better results. What about more manual type of optimizations, like using intrinsics or maybe directly implementing something in assembly? Is it still something that is done today, or we leave it to compiler?
Well, back in the days, of course, everybody would be considered a guru if they know very well the assembly and they use assembly. But nowadays, I think the trend is the compilers are so powerful and so capable. Rare is the case that we will write assembly ourselves. And of course, intrinsics, things like that can help, but they are linked to your type of hardware, and so they are actually linked to the hardware. And I think you can also leverage a compiler to do that for you, because when you do something like this, they are very targeted, very specific. Perhaps you are not considering all possible aspects in this whole picture, but the compilers, since they have multiple flags working together, perhaps they will yield a better result. But there's no go or no-go answer for this question. But I just would like to mention that nowadays the trend is we trust more about the compilers to bring the most performance gain. The key is really to know what the compilers are doing and know what to and what not to enable when we use the compiler. So, yeah, I think that would be my take.
Thank you.
All right, thank you. Again, big round of applause to our speaker waiting. Thank you very much for the speech.
Thank you very much.
And before you go, just I would like to remind you that we have a conference app in which you can provide the feedback both on the lectures and the conference overall. And I encourage you to use it in order to make the conference better for the next year. Now is the 30 minutes coffee break. I mean, already it's now like maybe 20. But you can grab a coffee downstairs, or you can grab something to eat also downstairs in bakery and coffee in the cinema restaurant, or here on the second floor in Pretzel. Also on the first floor there is a Wheel of Fortune competition in which you can win prizes, so I encourage you to take part in it. And there is the forest relaxation zone in which you can enjoy 10 minutes of massage. So thank you very much for this section, and see you after the first coffee break. Thank you, and see you soon. Welcome, folks. After the coffee break, we shall be starting with the next presentation, but as you can see, our presenter is currently absent, and so we will wait for a couple of more minutes, just letting you know so that you won't sit here for nothing. So let's just wait a couple of minutes till our presenter is back. All right, folks, our presenter is back. So let's welcome on stage Bartosz Moczulski. Bartosz is a software engineer and consultant with almost 20 years of commercial experience in the digital TV industry. Bartosz is a big fan of the Linux ecosystem and open source in general. He likes to call himself a Linux detective and rarely leaves a bug investigation unsolved. Bartosz has years of experience in C, C++, Linux security, and software integration in embedded systems, seeking an opportunity to pick up some Rust soon. Bartosz is also passionate about knowledge sharing and ran numerous well-received internal trainings and workshops in the companies he used to work for. In his spare time, he likes to make a wine and maintain a home lab for running a number of self-hosted services for both of the advantage of himself and the family. So without further ado, I give you Bartosz Moczulski, Shadow Stack, Fixed Memory Corruptions, Immune to Stack Protector. Big round of applause.
I was about to start with something different, but after attending the keynote in the morning, the keynote from Hepsata, I cannot underestimate how much my presentation will relate to what he was talking about. If you've been there, he was mentioning security very much, so what I'm about to show you is very much relevant. Right. Encounter, embrace, and eliminate. That's the standard recipe for bug fixing. That's how we go about it. And of course, you first need to learn about the very existence of an issue. Maybe you spot it yourself, maybe your teammate reports it, maybe it comes from your tester, maybe it's reported by your customer, the users of your application. That's usually the worst scenario, and it just pops up in your Jira or whatever other bug tracking system you use. Once you know it, you need to start analyzing it. You gather some evidence, maybe you gather the logs, maybe gather code dumps, maybe try to replicate it on your own desk, whatever is necessary. And after you've done your analysis, you probably will have already a good understanding what's wrong and how to fix it, hopefully. And yeah, by that time, you start preparing your bug fix. And that's roughly how my talk today is going to be structured. You will see it in the next slides. Just to make sure that you made it to the right room, I want to ask you, how many of you had to deal with memory corruption issues before? All right. Oh, God. It's almost entire crowd. I'm glad. And perhaps specifically stack corruption issues? Still quite a number. I'm impressed. Yes, so I was doing it myself for the last 2 decades or so. Not just memory corruption, also other types of issues, multi-threading issues, integration issues where things used to fit together, but they no longer fit together after an upgrade, or perhaps just no longer fit together because of other reasons. You know, logic errors, resource leakage. Hepsata was referring to that as well. That's why I like to call myself a software detective, because I spent, frankly, majority of my time, my professional time, investigating bugs, not necessarily writing new code. And I think that writing new code from scratch is easier. Writing or creating a new programming language from scratch is way easier than making an existing language better and improving it. If you've been living in one of these areas of the world, you might have come across the products that I helped develop across my career. These products are usually set-top boxes. If you don't know the term, these are the small router form things that you put next to your TV. You connect it to your TV in order to be able to receive your satellite television, your cable television, or maybe terrestrial television. So if I can ask you for one thing, it would be to keep watching TV, because it gets me keep my job, which I like very much. And just to clarify, I'm about to talk about stack. And let's just tell which type of stack I will be talking about. It's not the stud stack from the C++ standard library, although this is interesting all in itself. I will be talking about CPU stack, so the one necessary for execution of your program on the CPU. It's supported in your instruction set. It's referenced in application binary interface, calling conventions, so on and so forth. It's universal. It's not only for C, no, C++. It's also used in other languages. What will be your takeaways? They will be threefold. For a start, you may come here just for entertainment and to enjoy the misery and torment of your peers. Maybe you're already working in Rust or some other so-called safe programming language. Then all what I'm going to show is no longer relevant to you. But it is very much relevant to us who still need to deal with C++ and the like. Second tier would be awareness. Awareness that there is entire universe under the hood, below what your compiler shows you, below your C++ or C code. And, well, it's at least worth being aware of the fact. And the third tier will be the comprehension. Perhaps you will learn it, perhaps you know it already, and you just want some reassurance. I will try to at least scratch the surface and show you what can go wrong, how can it go wrong, why it goes wrong, and eventually, I hope, how to fix it. Right, so let's start with the first chapter, the encounter. I want to share a story with you. The other day, I received a message from a colleague of mine, very experienced guy, who was dog fooding our product. Don't know if you know the term. Dog fooding means using your own product. It comes from the dog food production industry, where supposedly one of the founders of dog food company told that you need to eat your own dog food. So, meaning not taking it literally, but figuratively, you need to keep using your own product in order to make it better. So that's what my colleague was doing. He was having a set-top box at home, watching television at the comfort of his couch. And the other day, he approaches me saying that, hey, Bartosz, you know, this new streaming service that you've been integrating recently on our platform. I say, yes, what about it? It keeps crashing. All right, that's interesting, because we've been testing it for a few weeks now. and I didn't notice anything special. So he continues, and he says that, yeah, it keeps crashing, but just when you watch live services. You can keep watching VOD on-demand content all day long. It works fine. But if you switch to live content, it sometimes crashes. All right, I mean, we've been testing it, we haven't noticed. Yeah, you know, but it only crashes roughly once a day, maybe once every couple of hours, every 4 hours or so. So if you keep watching live content all day long, perhaps you will observe 1 or 2 crashes. Okay, that makes it a little bit better, but not very much. So my colleague continues, and he says, yeah, there's just one final touch. It only crashes if you watch certain sports channels. Now, if I know something about sport, I'm not a big sport fan myself, but if I know something about sport, is that people get passionate about sport. When they watch their favorite athletes compete, they become passionate about it. So, I mean, probably half of you at least would follow some sort of football or volleyball or whatnot. Imagine yourself watching La Liga, wherever Robert Lewandowski plays now, in the middle of an action, and he's about to score, and in that instant, your application crashes. Does that matter that you can launch the application again and see the replay, you know, time travel back, and see that goal? It doesn't matter anymore. It's gone. It's past. All your friends will be sending you messages on your social media. Hey, have you seen this? No, you haven't. I mean, you will in a moment, but you haven't. So, crashing live sports, if it's anything, it's a very bad customer experience. People are angry about it. So I knew instantly that I'm gonna have to do something about it. It's not gonna slip by. So, given that, since we already established what the problem was, my colleague, being an experienced engineer, managed to grab some core dumps for me, and it was very useful because I didn't need to reproduce it myself. The evidence was readily available. So I grabbed one of those core dumps and open it in a GDB, as any sane person would, because that's on Linux, so GDB is your default debugger. So one thing that immediately stands out is the fact that they all come from a video stream thread. That's already significant, but it's not significant enough. On that slide, there's already something suspicious. I wonder if any one of you can see that. Sorry? Very well. Yes, it's unaligned, and it's suspicious. I mean, not that it's technically forbidden, but usually it's a sign of something going wrong. That's true. So I was smart enough with my years of experience to tell that, pthread mutex unlock, there's just no way it's going to be wrong. This is rock solid piece of software. It never goes wrong unless you pass invalid data into it, like this unaligned pointer. So I thought, it's worth looking at the parent function that called it, this do stuff, something. And yeah, so I opened the C++ code, and it looks roughly like this. It's a classic cliche. You log the mutex, you do this stuff in the critical section, and unlock the mutex in the end. And this function takes just one parameter, so this is an address to some sort of structure, and the structure looks roughly like this. It has some member, let's call it a pointer, doesn't really matter what it was, and at the offset there is a mutex. So right here, I would expect it to be at offset 8, because that was on a 64-bit architecture where pointers are of size 8 bytes. So address of the structure plus 8 equals address of this mutex. It's not guaranteed, but that's usually what it is. Yeah, so, well, I think there is nothing wrong in the code on the right side of the slide, is there? So I think, maybe it's under the hood. Maybe the compiler did something wrong. So I go to disassembly. Can you tell, by the way, by this disassembly, can you already tell what the architecture is here? That's right, it's ARM. It's specifically 64-bit ARM. Well, there is a reason why I want to torture you with this disassembly. I know it's not very eye-pleasing, but ARM matters, and it matters a lot. And another question to you, how many of you have something like that in your pocket? Ah, no kidding. Really? That few? I would think that some of you will have 2 cell phones already. Yeah, so most of the cell phones in the world, as well as a whole bunch of other devices, they run on ARM. And it's true for Android, it's true for iPhones as well. They may differ, so different ARM cores can be installed in, but it's usually ARM. I know that Android can also run on x86 and one other architecture that I forgot, but in practice it's always ARM. So on ARM, there's one little thing that I want to tell you about ARM and the calling convention on ARM. ARM has 32 registers, and you know, to use the classic literature, all registers on ARM are equal, but some registers are more equal than the others. So the first 8 registers are used for passing arguments to the functions. So if your function takes 1 argument, it will be passed via x0. If 2, it will be x0 plus x1, and so on and so forth. Additional beyond 8, that's a different story. Let's not worry with that right now. And there is a set of other 10 or so, yeah, 10 registers starting at x19. These are important because the ABI states that these values held in those registers must not change across sub-procedure called subfunction. So if you call some function, you are guaranteed that after returning from it, you get to keep the values in those registers. And there's the hero of our talk, of course, stack pointer, register x31, but usually it's just called SP. So let's take a quick few steps through the function here. I highlighted the relevant lines. So these 2 at the top and these 2 at the bottom are typical function called boilerplate. Allocation of a stack frame. Nothing interesting right here. Next thingy refers to what I've just mentioned. The contract of not changing x19 and x20. This function happens to want to use them, so it needs to store them somehow, somewhere. Here it happens on stack, because that's usually the easiest, and it's almost universally what the compilers would do. It's not required, but that's the easiest way, and it's supported by the hardware. And at the bottom, they are popped from the stack. Fair enough. So far, so good. Right here, we've got a calculation of some helper variables held in register x19. That's copied from x0, so the first parameter, the address of the structure. And in x20, we have x0 plus 8, so the offset of the mutex. So the address of the mutex is held in x20, while the address of this whole structure is held in x19. So far, so good. And then we proceed to calling the functions as specified in our C++ code. So moving from x20 back to x0 and calling pthread mutex log. This goes on very well. Then from x19 to x0 again, we call the subfunction, which happens to take the same address as the function calling it. And at the end, we've got this dreaded pthread mutex unlock, which crashes. But why would it? I mean, you know, copying from the previously calculated x20 back to x0, it's guaranteed by the ABI. It should not change. But it did. So over here, everything was fine at the top, and the address was as it was expected. Down there, it's wrong. Why? It shouldn't change. Something must have happened in the function in between. Somehow it failed to satisfy the ABI contract. And if we look inside that child function, we see something that we already saw, a classic boilerplate, calling a function, stack frame disposal at the bottom. And in the middle, it yes, it pushes x19 and x20 to the stack again because the child function itself wants to use them. So for a brief moment, x19 and x20 from the parent context happen to be on stack in the child context. That's crucial. So the issue is not in the function that crashes. I mean, there is nothing wrong with pthread mutex unlock, obviously. Similarly, there is nothing wrong with the parent function. The issue is somewhere here. The needle is in this haystack. And as you can imagine, this haystack can be thousands of or millions of lines of code long. And we need to find what happened. For a split moment, our registers were on the stack. After returning from do stuff logged, they were no more, or at least they got corrupted. How does it happen? Well, there is no magic. If you call the function, it allocates some data on the stack. That's classic. If it calls some other child function, the child function itself allocates some fragment of the stack memory for its purposes. And we go on, call some other functions. Eventually, we end up in a buggy function, which we need to find because we don't know which of those many functions it is. And this buggy function happens to write something outside of its stack frame, maybe here. And yes, of course, you can clearly see that this is out of bound right to an array, but we don't know where. And not just that. The buggy function itself will continue to run happily, unaffected entirely, and all the parent functions up to do stuff logged, they will keep running happily, no issues whatsoever, until we end up in do stuff log and then want to go back to mutex unlock again. So I guess many of you have heard about stack protector being a feature of the compiler that might help with that. But will it? The answer is on the slide already. It will not help right here. Why? Because that's what stack protector does. It merely pushes one integer value to the stack prior to calling a subfunction and checks it back upon return. So these extra variables pushed to stack are sometimes called sentinels or guards or canaries. After canaries, the little yellow birds that used to be used in mining industry to detect presence of lethal gases in the underground chambers. And you put the canary into a chamber. If it survives, it's safe for the miners to go in. If it dies, tough luck for the bird, but at least it's sacrificed help to save some people's life. So if the buggy function happens to corrupt its own canary, it's detected pretty much immediately, already upon return from the buggy function. That's okay. It's already deferred a bit, but not very much. If the buggy function overwrites a parent canary, well, it's a bit worse, but still not dramatic. The worst case is if the buggy function corrupts something else. It's not detected by canaries at all. So the execution continues, and as in real life, if you're young and make a mistake, you may not necessarily realize it instantly. You may be haunted by that after many years. So similarities between life and computer programming. A buggy function does something wrong. Do stuff the parent one suffers. So one might ask a question, a very legitimate one. So what's the stack protector good for at all? And it is good, and it's designed for saving you from contiguous stuff overwrites of memory, not just, in this case, stack. Yes. So if you go off by many bytes, there is a very high chance of you corrupting at least one canary or many canaries in a sequence. But not if you, I'm going back one step, not if you do that. Sorry, that's just not the right tool for the job. So since I already told you what the issue was, the question remains how to fix it. because we've got this huge haystack and we need to find a single needle inside it somewhere. But how? Does any of you have an idea or maybe know a tool that might help in such a situation? We could, but in my practice, yes. Sorry, just to say it loud to the microphone. Can we set up the right trap? Yes, we could, but we don't know what address specifically will be written to. So that's the one challenge with this approach. Yes, but still, stack is 8 megabytes long. In this case, yes. In this case, yes. But the layout of the stack, I mean, it's simplified on the slides, but in fact, it was written to a different address every time. So, to an extent, we could use mprotect to guard the entire areas, entire pages of memory. Okay, that's an interesting approach. It could work sometimes, not always. Any other guesses? Memory sanitizer. Okay, does it apply to stack? Okay. I didn't know that. Interesting. Okay, we'll have to check that. Thank you. There we go. Thank you. Yes, I was hoping for that answer, and the answer is unfortunately not, because it was happening in a web browser process, and as you can imagine, web browser is quite a heavy process. So it just couldn't handle the overload. But yes, I'm a big fan. Valgrind saved my day multiple times. So yeah, I would think, yeah, let's do it this way. Can't, not this time. So I was chatting with a friend of mine who happened to be working on my team back in the day. He's sitting over there. Adam, Shai, raise your hands. And you know, I was doing some brainstorming and said, hey, we've got this concept of stack protector. It's powerful. We could leverage that. Can we perhaps modify the compiler such that instead of pushing canaries, like a simple data onto the stack, perhaps it could call our function and then we make the whatever's necessary, verify that the stack is still correct, and just return the value. It's good or no, it's not, and then just crash. And as you can imagine, that's a really challenging idea. And Adam, being himself, he doesn't take impossible for an answer. He said something along that, I think I might have an idea how to do it in just C/C++ without descending into compiler. Maybe it was something along that line. So yeah, with that, let me present you the shadow stack. Before explaining how and what it does exactly, I will first tell you where the name came from. It was inspired by the concept popular in politics, at least in British politics, as far as I can tell, the concept of shadow cabinet. So imagine that in some country there are two political parties. They are called big endians and little endians. These names are relevant. You can check the reference down there. So imagine the big endians have just won the election. They got the majority in the parliament. They get to appoint the government, the prime minister, and the number of ministers, however many there are. Maybe they are called secretaries in other parts of the world, and then there is no prime minister, irrelevant. What does the opposition do? They will appoint their own set of ministers and prime ministers. And don't get me wrong, they have no administrative power whatsoever. They are just shadowing what the actual government does, proposing alternative solutions, criticizing the main government. That's what politics do. Such that in an unlikely event of a turnover, suppose some of the members of the ruling party happen to be convinced to switch sides, the opposition instantly have a set of people waiting on standby that can take over the new roles instantly from day one, or perhaps in IT we would say from the 0 day. And that's exactly what the shadow stack does as well. it copies the actual stack and makes sure that it stays in sync. The shadow copy stays in sync with the actual stack. In pseudocode, it looks roughly like that. First, before descending into a sub-function call, just take the current stack pointer and copy the missing area into the shadow area. So copy from the actual one to the shadow area and move on. Continue with descending into a sub-function. Just after returning from the sub-function, do the opposite, right? Drop whatever was necessary, and in between, twice, just before descending and just after return, compare the shadow area with the actual area. If there is an issue, if there's a mismatch, then do whatever's necessary. In action, it looks like this. We've got the doStuff function, and it has some data on the stack here. Before descending into sub-function, we copy it to a shadow area. Then we compare both. Right now, it doesn't make much sense, maybe, but in a second it will. And as long as there is no mismatch, memcopy says it's all equal, we can proceed to a child function, and it will have some data on the stack. We've seen it already. So maybe it itself wants to call another sub-function. So again, the shadow stack kicks in and copies it to the shadow area, and then compares. Maybe it's already wrong, so we will report about the execution. So far, it's OK. And it calls another function. Same story again. Copy to the shadow area. Compare. Descend into a buggy function. Finally, we arrived at the buggy one. And we know it already very well. It corrupts the stack. So far, nothing is detected. The execution continues. But when the buggy function itself calls another sub-function, or perhaps when it returns, right here it returns, shadow stack kicks in. And upon return, it compares the memory. And it detects a mismatch. What do you think should happen right now? Crush. Good idea. Or fix. Good idea. Or maybe nothing. Of course. We've got a correct copy. We can fix it. And continue execution happily. Is that a good approach? Sometimes it might make sense, of course. If you are prepared to pay for the overhead of shadow stack, which is maybe not very huge, but it's substantial. It's n squared, obviously, because the more you descend, the more data you need to compare at every single descent and return. So it's n squared. It's not good. Sometimes it may be too much. But generally, healing it's like sweeping under the carpet, it's pretending it never happened. But maybe it's reasonable to gather more evidence. For instance, you have 2 cases of corruption, so maybe you want to find them both in one go. The alternative, of course, was mentioned. We can just dump the report to the standard output or wherever it can go and crash. And there's a huge difference between crashing here and crashing over there. Over there is far away from the corruption. Right here is very close to the corruption point. So it's just easier to look at the code and see where it crashed. Where was the problem? The implementation looks like that. In C++, it's pretty simple. We use std invoke, and we wrap it in our invoke. And we add a bit of magic here in between. All the comparison and what I showed you on the previous slide. In C, it's cryptic. It requires some preprocessor magic and some compiler extensions. And little did I know that in C, you can do something like perfect forwarding, although it's far from perfect in C, but it's doable. I don't know if I would ship it into production, but for the purpose of debugging, maybe it's worth it. And usage in C is pretty simple. You just wrap whatever function call you are suspecting into our macro and run the program again. In C++, it's even easier. If you've ever used suit invoke, it's the same syntax. So you wrap your function, you take the function pointer, and call it with the object or whatever parameter it requires. It also works with pointers to methods, although the syntax is a little bit more cryptic, as is always the case. You may need some casting in order to choose the correct method. You can imagine all of that: virtual methods, overloaded methods, const methods, all that stuff. It's supported, it works. Maybe you don't have the luxury or don't want to bother with introspecting your code, with making the changes. We've got you covered. You can use LD preload, why not? So without recompiling your broken binary, you can write a preloadable library that will just wrap the actual functions and do the magic under the hood. It also works with C++, but you need to know the mangled names. Yep, that's it in a nutshell. Now keep your fingers crossed, please, for me, because I'm about to show you it in action. There we go. Right here, a bit of a spoiler. And where's my scenario? Here it comes. Here it comes. Here's my scenario. So I've got a binary which is broken or can be made broken. Can I just mark it? Yes, I can. I will just run it the usual way. Where is this, my shift key? It just runs, nothing interesting happens. Then I can make it corrupt the stack at the offset of my choosing. Here it's offset 140. And it crashes, expectedly, because it's a demo application. We may want to, how do I do it? Like that. We may want to look at it in GDB. Why not? There we go. Let's run it. And we've got a segmentation fault, just as expected. And if we look at the backtrace, it's what I showed on the previous slide. So far, nothing surprising. I've got an instrumented version of that library, which will differ by the offset, and it now uses our shadow stack concept. There we go. Or maybe it's make it a bit smaller. There we go, such that it fits on the screen. I don't want you to look at all of this, of course, but that's the shadow stack report. Is it large enough? Can you see it all? Okay, thanks. Yeah, so after return from the buggy function, shadow stack notice that there is a mismatch between actual stack and the shadow stack. On the left side there is original being the runtime stack, which got corrupted, and on the right side there is a shadow stack, which is the pristine copy. And in this line, as you can see, the familiar 03 was written over here, whereas there should be AA. All right. So, well, at least we know that which function is suspected. And obviously we can run it as well in GDB. The same thingy. Run it. And now we've got abort, because that's what we wanted. We want to force abort. And when I showed backtrace, now we know something more. Maybe I'll make it a bit larger. Now we know that we managed to get into the other function. And from the report from the shadow stack, we know that it was after the return from the buggy function. If I list the code, can I? Oh no, sorry, I need to switch to frame 7 and list the code. So we know that after returning from the buggy function, something was wrong. There are several options. If you have perhaps fewer screen state, then you can adjust it. Oh, no, sorry, not in GDB. Right here. So you can hide the equal lines, of course. You can just show one part of the screen, just left versus just right. whatever you please. You can make the lines shorter, say 8 bytes per line, not 16 as is the default, usual stuff. And oh yeah, this one is interesting. You can try to heal this thingy. There we go. Can you see the stack fault? No, because it's missing. And there's an option, quiet heal. So don't report anything, just heal this, heal your stack. And everything is happy, yeah? Sunny day. And the last thing is the preload. So without modifying the original binary, let me scroll upwards. Over here, yeah, there is my preload kicking in, doing the stuff, without changing the binary itself. Now I will switch back to the slides, like so. Off to the summary. So I owe you the closure. Have we managed to find this bug that was haunting us in the first place? Yes, we have. Otherwise, I wouldn't be standing here bragging about it. It was an issue in one of the libraries that we use. It's called GStreamer. If you are into multimedia processing, you will know that library, very respectful library, reputable. And just so happened that in one of the lesser used functions, it was missing data inputs, input data sanitization. It was writing at offset 240 into an array of size 10, obviously wrong. And it had been fixed a few months earlier before we noticed that error. So we simply cherry-picked the fix from the upstream. On the shadow stack itself, is it mature? No, of course it's not. It's just a proof of concept. It's not a free fish. It's not even a free rod. It's a blueprint for a rod that you can make yourself. But we've got one example rod available. So you can kickstart with that. Main lessons for us. Stack protector should be used consciously. It will. It's not an almighty savior. You need to know what it's doing and how it's doing in order to apply it for the specific issue. It's good to check your dependencies every now and then. Maybe the bugs that you are fighting with are already fixed upstream. This has paid off more than once for me. And finally, the order matters. And it's not just the order in society, although that matters as well. It's the order of the stack. So imagine what would happen if the stack was growing from the other direction, from lower memory addresses towards higher memory addresses. You start here, let's say at the beginning, at 0 into a segment. You call the functions. You end up in a buggy function eventually. And it corrupts something. What does it corrupt? Free space. No worries. Don't get me wrong, it's still a buggy code. You should avoid it, you should fix it, but at least you don't get to shoot yourself in the foot in the process. Does it mean we can switch the order of the stack? As far as I know, there are systems out there that do just this by design. However, they are in minority. Most of the systems out there, they will use the regular. If you the order of the stack that you are all familiar with. So can we switch the order of the stack? I will leave you with that question. Please answer it for yourself. Now I'm happy to take a couple of questions from you.
Big round of applause to Bartosz. Thank you very much for this interesting mystery case. And now we'll go with the question, of course. So, and the questions already, please raise your hand. So first question I can see here.
Oh yes, do you know any way to use it, this LD preload method on Windows ecosystem?
Awesome question. No, I don't know. It doesn't mean that it doesn't exist. It just means that I'm not experienced with Windows, so I won't speak for Windows part of the world. As far as I can tell, the Windows loading system, the libraries on Windows, they have different semantics. In Linux, all symbols by default are wrappable. On Windows, by default, they are not. So, well, on Windows, they need to be made explicitly or wrappable or overloadable, if you speak.
All right, thank you. Second question I saw here.
I'm gonna branch out a little bit because here we have a stack at least, but what about issues where we have a program that silently corrupts memory somewhere and the behavior goes out of the window? And you know, you could use debugger, you could use silly prints, and you have third-party libraries there, and you have no idea where to start. Where would you start? Like, what would be the tooling of your choosing?
Awesome. You mean like corrupt the heap instead of stack?
Yeah. Yeah.
So yes, I did have to address any issues like that at least twice in my career. So it's often improvising, but I recall specifically one issue with custom-made memory allocator, and to our demise, it was an allocator which was using in-band metadata. So just before the memory that got returned to the caller who wanted something, there was like a header just adjacent to the actual data. So that's called in-band metadata. It's a big no-no. I discourage such design, absolutely, but that's what it was. And what did I do? I think, it was a crude approach. I made all the ifs in the entire stack to just do the extra check for me. So instrumenting the if, we turned it into capital if, and it was doing the actual thing, but just beforehand it was checking, hey, this address, is it broken already? And then when it detected it got broken, luckily for me, it was the constant address, so where I know where. So speaking to this idea of having how it's called, the debugger thingy, the trap, the hardware trap. So that couldn't be used on that system, but instead I turned all the ifs into a checker. Would I recommend it like a standard practice? Probably not, but it paid off.
Thank you very much.
Okay, thank you. Another question here, and then we'll move back to that part of the room.
Hello. Wouldn't it be cool to have this implemented as a, let's say, opt-in kernel facility? So you could run without recompilation, just opt in on a kernel level for these checks and maybe even healing?
You mean to protect the kernel itself or to protect the user space application?
To protect the user space application from kernel.
It wouldn't be so deterministic because to an extent you could do it upon the context switch in the kernel. So if the application is swapped out or maybe swapped in again, you could do this check and yep, I can see, I mean, it could be feasible, not with the current state of our code, of course. It wouldn't be deterministic, not so much. So maybe the takeaway would be smaller.
Okay, I see, thanks.
All right, thank you. I saw a hand here in the middle and then one back. And let's take those two questions still.
Hey. From what I gathered from your issue, you have to decorate every call down the call tree to try to isolate the issue. Does that mean that you basically had to add a few, then reproduce the bug, then try to narrow it down again and again? Like, how long did that take?
Yes, that's roughly what it took, and actually can show you that in the code. So I should have a diff here, maybe here, right? So that's the original on the right and the instrumented thingy on the left. And yes, basically that's what it took. We had to instrument every call that we suspected. Luckily, it was only on a single thread, so there was just a subset of those, maybe 100 or so. Yeah, that's what it took. How long did it take us to reproduce? I think around a week or so. I mean, we were reproducing it more often, the issue, but the fact that it was reproducing only once a day or maybe twice a day, yes, it got an impact. So we rather took the approach of instrumenting more than necessary in the hope that we will get something in return faster.
All right, thank you. And there was one more question in the back.
There's a gentleman desperately wanting to ask a question.
In a black t-shirt, as I can see. The black one.
Yeah. Black. There you go. There you have your chance.
Yeah, so I couldn't quite catch that, but my question is, how do you protect against like legitimate stack modification by another function? Because it looks like you're kind of detecting if someone modified my stack. But if I
Yes.
allocated a pointer for someone to use or
Of course.
kind of buffer.
Yes,
How do you
that's-
protect against that?
We don't currently. However, yeah, I did anticipate that question. Thank you for asking that. And we do have an idea how to implement it. We call it so-called ignore zones. This could be easily implemented. And if I know Adam well, and I think I know him well enough, he might be able to implement it by the end of this week. So
Right.
it's an easy thing. You just keep track of the zones that you want to ignore, and before making the comparison, you just copy that zone from the actual stack to the shadow area because you don't care, and
Sure.
then you just perform the very same memory comparison across
Well,
entire area.
Yeah, but I would have to sanitize every buffer myself, right?
Yes, you would.
Okay.
I mean, we didn't introspect the code. We didn't do any meta introspection or anything like that.
Yeah.
You need to specify that, hey, this is the area that is supposed to be changed by the callee.
All right. Since you mentioned writing a plugin for a GCC, maybe it's simpler to just run Valgrind, but on a subset of the program. Like you don't have to instrument
Absolutely.
all of the buffers. You can like instrument a
Absolutely.
small subset.
Yes, if you can narrow down the problem, absolutely, by all means.
Yeah.
Yeah. So
Also, but like, most of the features, I think the sanitizer will cover. It will do some kind of like, because if you have like a specific type, like you have a pointer to a type, you kind of know how big it is. So you know when you have a wrong access, like like a corruption. The only problem is with arrays, and then you kind of instrument every array access with a bounce check. If you don't already use like std array or other container.
Yep.
So I think you maybe want to go in that direction instead. But yeah, it's just a suggestion.
Good idea.
Thanks.
Speaking of what? Oh yeah, the sanitizer. There was a question earlier about how to approach heap corruption. Sanitizer are a good idea. Yes.
Yeah, heap corruption is great. For stack, I'm not sure if shadow memory works. I think it does by instrumenting the arrays accesses. It may not work in some edge cases on the stack. That is true, but yeah.
Yeah.
I guess you can get the
absolutely good idea.
Yeah, the results with types plus sanitizer, like a type system instrumentation and sanitizer, I think.
Sure.
And it's more like a portable and yeah.
All right. Thank you very much for all of the questions. And once again, big round of applause to Bartosz.
Thank you very much. Enjoy the rest of the conference.
And we'll be back in approximately 7 minutes with another lecture. So stay tuned. Welcome everyone. After the break, we have Filipe Mulonde right now presenting just before the lunch break. Filipe is a GPU modeling engineer at ARM Holdings, where he works on the world's most solid mobile GPUs. ARM is a global leader producing technology that powers countless devices worldwide. Filipe is also gained valuable experience in a scientific researcher at ETH Zurich in Switzerland, a prestigious institution renowned for its cutting-edge research and innovation in science and technology. At ETH Zurich, he focused on computer architecture and biometrics, but additionally, he also worked as a software engineer on the development of an autonomous train for one of the most significant railway companies globally. As an international speaker, Filipe has presented at major C++ conferences such as C++Con, Meeting, C++, and EMBO++. So, ladies and gentlemen, Filipe Mulonde implementing large language model interface in pure C++. Big round of applause.
Thank you very much to be present here. As I said, my name is Philip, and so I was curious about how these large language models work, and I step up to start understanding it, and then I feel like I think that's something interesting to share. But at the same time, it's something extremely complex. I wouldn't say to just understand, but actually to teach. And doing it in like 45 minutes is extremely complex. But we will try, but I do have some expectations for the people that are attending the talk, which I will mention pretty soon. So why to understand large language models or generative AI is being used and applied to so many different fields like healthcare, finances, banking, logistics, and so many fields is being reshaped by AI. And in fact, if you look at the transformer architecture in these days, it's pretty much used in most of AI tasks, regardless if you work with images, text, or any other type of data, such as graphs, for instance. So I think there is a good reason why we should try to understand what's going on, because I think it's one of the most is one of the technologies that created one of the highest revolution we see in the IT field. So of course, all of this is done by transformers, but of course not this type of transformers. And then we can jump to my expectations. As I say, 45 minutes to talk something as large language model is almost impossible. So I do have some expectation for the people that are attending the talk. I'm assuming you have a good understanding of neural networks, I mean the basics of it, what exactly it is and what it does, and some of the components that composes neural networks, such as normalization, for instance, or softmax functions, because I will go a little bit faster over those because they are actually very straightforward. This talk is completely inspired by this GitHub repo. And I also encourage you, if someone wants to get to know more, to check that. This implementation is in C. And you can also check his YouTube channel to follow his series of talks, which are actually quite rich in content. What are we going to be doing in this presentation? We will try to build something like this. But the thing that we're going to build will be slightly different, because we don't gonna expect a prompt. We just gonna assume that we have a trained model, and we're gonna feed the first token of this trained model into our transformer, and from there we start auto-generating text. It's slightly different to the things we see in things like ChatGPT, but the difference is very small. It's just that we are omitting context, and we just let the model create some random stuff, but it arguably the same stuff to a certain degree. So it's just for simplicity, because there is the underlying technology and the things that you're going to apply to build something as Llama is exactly the same. So example of something that you're going to build that you see most in your smartphones is basically when you try to predict the next word, and that's basically what large language models do. They just predict the next word, and then take this word, feed it inside of the neural network, inside of the model again, so that it can increase the context and then predict the next word again. And we will see how it works in depth. So let me just set a little bit of timer so that I can know exactly where I am. Okay, continuing. So that's the architecture that we're gonna go through. This is the Llama 2 architecture. So we're gonna go through the layers, and we're gonna explain what each layer is doing. As I said, some of these layers that are pretty well known, or assume that people with basic knowledge of neural network, we understand, and we go faster over them. So we go for the first one, which is basically embeddings. When we're talking about token embedding, basically the problem that embedding solve is, of course, we are talking about something that generates text, but computers don't understand text. So we need to find a bridge between text and numbers, which computers operate on. So that's basically what embedding does. So we start by creating a table, and we fill them with all the possible words that our model can predict or use. It's the same as any language. For instance, the Polish language, you have all the words that are necessary for you to speak or that are valid in the Polish language. The same for a model, depending if it's English, Polish, or which language you're trying to create a model for. You also need to define the set of words that are valid for the model to use. So we group all these words into a table, and of course we create indices to access these tables. But these are still words. We still need to find a way to transform these words into numbers, which are things that computer understand. So this is an example, for instance, of a text. So this text that we have here is a text of this conference, and then you can see, for instance, the relationship between the text and the vector, for instance. The word welcome is mapped to the number 21829, for instance, and so on for the rest of the world. And we can go a little bit deeper into understand what exactly is going on. This is just an illustration. As you can see, that every word is mapped to a particular number. But one thing to understand is that models, they don't really see words in the way that we as humans do, for instance, right? It operates in a function of frequency of words so that it can create more context that makes the model more able to predict the next word, and is tightly connected to something that is called the context windows of large language models, which we will see later. Why is it important, and why the model doesn't go exactly word by word, but actually try to find frequency words and merge them together to make them as a unique words, and then add this unique word back to the vocabulary of the language of the model. So this is an example, and the algorithm that does it is called the byte-pair algorithm. For instance, we have the first word, we have like A, B, D, A, B, A, C. What this tokenizer we're gonna do is, first we're gonna look for what's the most frequent two pair of letters that we see in the text, and you will see that it's AA. So you're gonna merge AA to a new word called Z. It will add Z to the vocabulary, and then we're gonna go back to the text and I'm gonna replace A by Z. And it's gonna iterate over and over till a particular number of words or tokens that we want to allow in our model. So you can look a little bit more deeper in this algorithm, how it works. There's a lot of contents as well. And after the talks, you can also come to me. I can point you directly to places where you can learn more about how this algorithm basically works. But that's what the algorithm does. So this is another illustration. We have I saw a cat as a word. So every, let's say, word that we have in the text that we feed to the model is mapped to a number. We take this number, we access the embedding table, and from the embedding table, we get something that is called the word vector. So we basically map a word to a number. We use this number as an index to a table, and then out of that table, that particular index, we get a vector that is a representation of that particular word. So this is an example, for instance, of the word king. This is an example of a real-world large language model trained on the text in the Wikipedia. You can see that these vectors are very, 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 very big. And different fields of the vector represent different futures. For example, nobody really knows deep inside of the model what are these futures or what they are represented, but everybody has an idea of what potential these futures are. For instance, depending on the test that you can have. For instance, each position in the vector, for instance, some of them can be something like the masculinity, the femininity, the age, and so on. Those are features that are inside of this vector that allows the model to identify exactly where to map that particular word in that particular space of vectors. One thing that we can do as well to see the similarity of words, we can try to add colors to different values in different places inside of the vector itself. For instance, if they are close to 2, we paint them as red, and then if they are close to 0, we add them as a white, and if they are close to -2, we paint them as a blue. Why are we doing that? Well, because this can help us to visualize what the model is doing. It's not just taking any index of word and mapping it to a random vector representation. These representations are learned during the time that we're training the model. What the model actually does, it sees like if one word appears similar in the same position all the time or through the training, then it's the model during the train, what we're actually doing is mapping similar words so that they can be close in that space of vectors that we have. So for instance, it's very useful for us to see that queen and woman appear in similar contexts. That's why you see the color palette between queen and woman is kind of similar. The same for girls and boys and men and king and queen and queen, for instance. But when you look at something like water, it's a little bit different than we're gonna see something like queen, for instance. Of course, all of these have a bias depending which text you fit into the model. And an example that we can have here is that the model not only learns how to map similar words that appears in the same context close in the space, but what actually it does is also learn relationships. For instance, the model learns, for instance, when you take the vector that represents women, and then we subtract it with the vector that represents men, and then it gives you a vector that actually gives you a direction in the space that actually means gender. So at the same time, when you do something between niece and nephew, to find that the opposite gender of nephew, you just follow the same direction as we get, for instance, from men and women. So that's why we can see that actually the model is learning relationship between words, and different direction in the space means has a meaning. For instance, as we can see in this picture, one of these directions is basically gender. And the way we use actually to calculate the similarity of words is basically calculating the dot product between two vectors, and then we can see if the words are similar or not. And one idea of large language model is the core idea that I want people just to take out of here if you don't take anything out of this. Is basically the idea that we're trying to do is we're trying to predict the next word based on the last word in the sentence. But the question that we need to ask ourselves is, okay, we have many other words in the sentence as well. Can these words that we have prior to the word that we're using to predict contribute to the meaning of the word that we can predict? For instance, you can have the phrase American shrill mole, and then you have one mole, and then take a biopsy of the mole. Language are very ambiguous. If you take this word representation and give it to the in the embedding table, you're gonna get the same vector representation. But these moles represent different things. What can we do so that every mole that we have in these words represent exactly what it's supposed to represent? So that's an example that we can have here. If you fit the mole into the embedding, you get the same vector. But we certainly talk about different moles, and what the language model or the attention mechanism of large language model does is exactly to help the model understand which particular mole we are talking about. In other words, is to take that mole or that vector, change it in the attention mechanism so that it can point to the direction or to become the vector that actually represent that particular, that is enriched by the meaning of that particular sentence so that we can use to predict the next word. So we're gonna jump a little bit in the code, and the way I wrote this code is trying to make it very easy because I'm trying to balance between theory and implementation, and also want to make it as clear as possible. And as I said, for some parts of the talk, I will go really fast on things that I assume that are very straightforward to implement. So we start with defining some vectors, and these vectors that we're trying to define is basically we're just trying to create a different hierarchy of data types, and then the maximum one that we have is a 3D vector that we're gonna use, for instance, to represent the matrix of weights and so on. As I said, we are assuming it's a pre-trained model that we're gonna load the trained weights and parameters out of a file, and then we just basically implement the inference. And then we have the first struct that we have is a configuration. We have the dimension of the world, so the embedding that we're going to operate on, meaning like the world, the maximum size of a word that we can feed in the model. Then we have the hiding layers that you're going to be used inside of the deep neural network layer. And then we have the number of layers because we have like a transformer layer, and then we can repeat and operate any times a particular context. And then we have the number of heads. It will be relevant when we talk about the multi-head attention. And then we have the vocabulary size, which is the number of words that our model can understand or predict. And then we have the sequence length, that means the context. What's the maximum size, let's say, of a paragraph, or how many words we can feed at the same time to the model. And then we have the transformer weights. Those are the weights of the model. We have the embedding table that came already with all the mapping between words to vec. And then we just basically access it by indexing it, and we get a particular representation of a word. We have the RMS attention weights. That are basically normalization weights for the attention layer and for the neural network, vanilla neural network layer. And then we have the weight for the query, for the key, and for the value, and for the output. I'm sorry for the naming. I know it's not very convenient, but the problem is just with the slides. If the name becomes too big, and then I can't feed anything to the slide, and then just becomes a little bit too complicated. And then we have also the last weights for the normalization, and then the frequency are important for something that's called a rotary position embeddings that will become clear as we move forward. And then we have the room state. This is basically a cache that we accumulate to store values as we move through the neural network. As we say, because we operate in layers per block, and then we have multiple blocks, so that's the reason why it's important to have something as a structure like this to keep up with what we have computed so far in the model. And there we go, a little bit faster. What we do here in this function, just a utility function, just to resize the tensors, because initially they are not really defined what is the size of each of these vectors. So we just have these functions that basically initialize or resize these vectors. As I said, some things that will go faster, and if you're deeply interested, I can give you the slides so you can go a little bit into it to see it. But basically, we're doing just resizing vectors so that they become the proper dimension that we expect from them, according to the dimension of the model that we have, that we read from a file. And then we have this utility function, basically just a structure to basically resize in 3D vectors as well. We just go through every component of it, and then we resize it to be the size of the dim, which is the size of the word that we actually process in. And of course, we do the same for the weight to the tensors, and we do the same for 3D vectors. So just believe in me, they're just resizing the vectors so that we can have proper, let's say, size that we operate in. But as we go inside of the transformer, it becomes more clear and more easy to explain what's going on and why this vector has exactly these dimensions. And then the weights for the final neural network. The same for the rotary positioning code, which also will make sense as we move forward, because without context, it's hard to understand what rotary position embeddings are. And then we have another utility function. This basically is the function that we're going to use basically to read the the weight from the file and load it to the proper vectors. As you can see, it's just really recursive functions that go independent of the dimension of the vectors. It goes till the bottom and recursively starts feeding, because down the structure, as you will see, any vector that we have in the model is basically a composition of the sequence length that we have inside of the model. And then it's just an example how you call it, and then basically how you initialize or load the weight from a file to the particular vectors. Okay. So now let's give a more concrete example of what we're trying to do. Of course, I took this example from the three blue, one brown example. We have this test, a fluffy blue creature rumored to the verdant forest, right? What our model is trying to do is, for instance, we have a fluffy blue. So we have words adding context to other words. For instance, if we have the word blue, if we're trying to predict what's the next word that comes after, we can see what the other words before that word can add to me so that I can predict more accurately or know exactly what I represent. So then you can see the word A and fluffy, when they add their representation to the vector blue, this vector becomes blue and becomes fluffy. The same things with the verdant forest. As you can see, when we add this representation of the verdant to the vector forest, then the model becomes more aware that we're actually talking about a verdant forest, and then it can predict more accurately what is the next word. So we're going to start really going a little bit deeper in what self-attention means, and basically we need to make these vectors to talk to each other so that they can update the meaning of each other. For instance, we have a fluffy blue. So when we predict the next word, like creature, you can see that now the creature becomes blue. Why? Because now the vector fluffy and the vector blue have talked to each other, and the vector fluffy was relevant or attended to the vector blue, and it enriched the content of the vector blue so that the model can predict that the next word is a creature, but this creature is blue. The same thing with the forest. For instance, when the vector that represents forest talks to the vector that represents verdant, after we compute the dot product in that space where they are mapped to, it seems that the dot product of that of these two vectors is relevant enough. So then this verdant update the vector of forest so that when we predict from verdant to forest, we predict a forest that is actually green. So these are the self-attention in a bit more of detail. So let's assume we have a context of two, or a context length of two. We have two words, thinking and machines. So the first thing that we do is, of course, we tokenize, we convert these words into numbers or index, and then we use this index, we're gonna access the embedding table, and for the embedding table, we're gonna take a vector representing each of these words. For instance, we have the x1, and then we also have the x2, represent a vector representation of these two words. After that, what we need is we need a different weight, the matrix weight that we call the weights, that we call them carries. And then what we do is we multiply these two embeddings, or each of the words in the sentence, by this carry matrix, so that we can get carries from this. And it will become clear in a minute what we mean by carry. And the same thing we do for a different weight that's called the keys. We also multiply the embeddings, not the result of x by q, but the embedding with the vector, the keys matrix, so that we also get two different vectors for that. And also we have the values that we do the same. We get the embeddings of the two words, and then we multiply it by the weights of values, by the matrix of values, and we get two different vectors. And it will be clear in a minute why we need to do that, or why we're trying to do that. So what we have then, what we need to do is, we need to find a way to compute which word in the sentence is relevant to the other word. For instance, at this moment, I'm computing the word thinking, is the word that we feed it to the model. What I'm trying to figure out is, what are the other words that can actually enrich thinking so that the next word that I predict can be more accurate? Since at this moment, at this particular position, thinking is the only word that was fed in the model, so then we need to compute attention with the thinking itself. What we do is we take the embedding of thinking and we multiply it with the weight matrix, with the carry matrix. What are we doing? We're generating a carry. What a carry is doing is I'm going to ask for the rest of all the words that comes before me if they are relevant to me or not. But how do I ask it? I ask it by computing the dot product between my carry with their keys. The keys that we also computed from the other words that comes before the word that we use to predict, they are, in a way, they are saying to the carry, look, that's what I am. Let's do the dot product and find out if I'm relevant to you or not. So that's what we're doing here. So at this particular position, we still don't have any other word but just the word thinking, and so we do it by thinking itself. So we compute the dot product between the key and the carry of the embedding of thinking itself, and we get a value. And then we do the same for the machine. Because at this point, we're trying to find out if the machine embedding of the carry, and we use its carry to compute if there is relevance between thinking and machine. So that's basically what we're doing here. And then that we need to do, we need to divide it by the size of the, let's say, of the row of this matrix, or the size of the embedding that we're computing. And then after that, we're going to apply softmax. Why we apply softmax? We apply softmax because we're trying to find weight. Because we don't want, if the dot product between two different words is too small, we don't want you to update. Let's say, for instance, if thinking that has no influence in the machine, we don't want thinking to influence machine. So for that reason, we're going to multiply, that, as we're going to see in the next steps, the value matrix of each embedding as well, so that we can actually create a more enriched representation of each word, and we should become clear as we move forward. So we have, at this point, we have the softmax of thinking with thinking itself and thinking and with machines, which means the softmax here is representing how much each of the words in the sensing is relevant to each other. So thinking is relevant to thinking by 0.88, and we see that machine is actually not really very influence, or let's say we don't see machine and thinking during training much to be close or appearing in the same context. So its dot product is basically 0.12. So this machine should not influence the representation of thinking too much. So this is basically then where the value matrix actually comes in. What the value matrix tries to do is, okay, I have the word, let's say, blue and fluffy, and I want to create this vector that is here, fluffy blue. So then I take the word, the embeddings of the word blue, I multiply it by a matrix called value. So basically what the value is saying is like, if this blue should influence any word in the sentence, how this blue should look like. So that's basically what this value matrix is doing. And we do that from the blue, and then we do that for fluffy, and then what we're gonna do is we're going to take the weight of thinking with thinking itself, in this case, and then what we're gonna do is we're gonna go to the, let's say, I think I misconfused the two examples around here. It makes it a little hard to understand, and I'm sorry, I just realized it now. But explaining it a little bit different, we have thinking and the dot product with thinking itself, and we have a value. And we have machine and thinking dot product that we also have it as a weight. So we have two weights, 0.88 for thinking with thinking itself and 0.12 for the machine itself. Then we take thinking and then we multiply it by the value matrix and we get a matrix, right? Then what we're gonna do is we're gonna take the value of thinking, like the weight that we got from the dot product between thinking and thinking itself, and we're going to multiply it by every entry of the result of the embedding of thinking with the value matrix, so that we can have a weighted manner of influencing vector. That's what we're doing here. And we do the same with machine. We take the embedding of machine, we feed it to we multiply it with the value matrix, and then what we do is we take then the dot product of the thinking and machine itself, and we apply the softmax and the division, and then we also multiply the every entry of the resulting vector of machine times the value matrix, so that we can have a weighted way of influencing it to the word thinking, as it will become clear as we move forward. So we can have this represented as a matrix multiplication. For instance, if we have two embeddings, we multiply the two embeddings, or the every word that we have in the sentence by the carry matrix, creating a carry into the rest of the sentence, and a way to ask every word that we have in a sentence, are you relevant to me? And then we do the dot product to actually know how relevant they are to each other. And then we have also, for every embedding, we also do multiply it by the carry matrix as a way to respond to the carry. When I receive a request of a carry coming to me and say, hey, who you are, I need to show, hey, I'm this key, and then we compute the dot product between both to understand how are relevant to each other. And then we do to the value, which the value is basically saying, if I'm actually relevant to someone, who should I look like, or what representation should I have to actually add meaningful representation to the other word? And basically, that's compute what is called the self-attention that we have. We have the carry, and then we basically transpose the key, and then we basically do dot product between the carry of every word in the sentence by the key of every word in the sentence as well, and then we do a weighted, taking the dot product between these two that to basically influence the value that we get by taking every embedding and multiplying that by the value matrix. And what we get in the end is the Z matrix. This is what we call self-attention. Talking about multi-head attention. So multi-head attention, basically what it does is, instead of taking an entire query and compute it for every other word in the sentence, what we do instead is slice the carry into multiple pieces, and we also slice the key into multiple pieces, and then in parallel, we can actually compute the same thing. So we can have multiple heads looking for the same thing. And every head look at particular part of the representation of every embedding, doing exactly what I explained before, which is the key and the dot product between the carry and key, and as well calculating how words should influence each other. So, and then basically we concatenate the results coming from every head. So this is then, after we have this representation that we can after the concatenation of every head, we multiply it by another weight matrix with the weight 0, the weight matrix 0, weight matrix O, meaning the output, so that, remember, when we are in the multi-head attention, we are computing in the small subset of every carry and every key, but the model operates in the size of the embedding. So basically what we do with this output matrix is multiplying the result of we get from the multi-head attention by the output matrix, so that we can map this vector back to the size of the model. And this is basically an illustration of the multi-head attention. We have an input sentence. It's called a thinking machine. We calculate carries for every embedding in the sentence. Then we calculate the attention using the key value and the carry matrix, and then basically we do it across multiple heads, and then we multiply it by the output matrix to get a final representation. And this is just a single layer of multi-head attention. So this is basically an idea of what's going on in every word. You can see, for instance, how much each word prior and after it, depending on the type of attention that you can have, can influence this particular word. And then what we did is self-attention is when after and before words can influence every embedding in the sentence. But when you talk about masked self-attention, what we're actually doing is we don't want the word that comes after me to have any influence in me because of the way we train the model. We train the model in a way that every example, every word that we see, we decompose it in a way that every word actually is trained to predict the next word in the whole sentence so that they can influence each other much more, so that at the end, the last word is so enriched in content that can predict more accurately what is the next word. So, go a little bit faster. So we start implementing the transformer. Basically, what we define is a function. It receives a token index. It receives a token position, receive the configuration struct that we talked before, and then we have the run state to keep up the state of the transformers, and then we also receive the weight that we loaded from the files. So we are in the first phase of it, which basically means let's load the embeddings, and then what we do basically, we just implement. We call SCD copy. Basically, we pass the weight embedding table, and we basically move the particular embedding using the particular token index basically to the state component of the state object. That's basically what we do. And then at this moment, the state X holds the embedding of the first word we see in the model. Then we need to configure particular things in the model. So starting, we need to define a dimension. Of course, we take it from the configuration. It's basically the size of the embedding or the size of each word that we can have in our model. Then we need to decide the hiding dim, basically the size of the. We have this neural network, and then we have like the hiding layers. So we need to basically decide how many neurons we have in the hiding layers. And then the head size. The head size meaning, like, as we say in multi-head attention, we have multiple heads. We're trying to figure out how long should be the subsequence of each carry and key each head should work with. That's basically what we're trying to do here. Then we start the first iteration in the loop. So basically, we start iterating over multiple layers. We say we have a parameter layer. So you're going to iterate over all of them. So we move to the next part. Basically, we're going to implement the RMS norm, which basically it does is the normalizing layer. It's not a batch normalization. It's a layer not normalization, which does it normalize basically activations per layer. Why it is important? So basically, we're trying to create somewhat a more stable behavior for the model during training. In other words, we want that the changes that we causes in the model after we update the parameters using break propagation, we don't want it to be so different that the model didn't saw it before, so that it forced the next layer to retrain again to adapt to that. So it's basically creating a way of creating a distribution that is much more easier for the model to learn during training. So basically, that's the equation for normal normalization. And now we go straight past to this because I assume most people here know. So basically what we do is we compute the sum of squares, as we see in the formula, in the formula over every activation that we have in that particular layer. And after that, we basically compute the inverse, basically different that we have in the formula, just to have more computational stable, so that way we can avoid division. As you can, if you want the slides, I can pass you so you can see exactly what we're doing here, exactly what we have in the formula. And then basically what we do it, we apply it. We go back to the layer that we work on, and then we apply, we call this function normalization, that basically normalize the whole state of the vector x, and then pass the value to the vector b, to the vector xb. This is basically just a buffer. And then we start with another utility function that we're going to important to us. Is basically perform vector and matrix multiplication. Just take a vector and then basically takes another matrix. It takes the vector and compute it with every row of a particular matrix. So that way, just call the STD inner product to perform that. So it's a very straightforward function for vector matrix multiplication. Then, basically what we're going to do is, as we saw before, we need to compute the k, the carry, and the value. And to do that, we basically take the carry matrix and the state key, that meaning the k in this particular state of the model, and then we pass a state xb that's basically going to hold let's say, the normalized vector that we normalized it in the prior slides. And we do it for the key, we do it for the carry, and we do it for the value. So for every embedding, after normalizing, we compute the carry, the key, and the value. And then we move next. It's something, as I will say, everything in this particular layer is a field of research. You can go 2-3 hour lecture in the end of this. So I'm trying to find a little bit of balance between both. So we tell something that's called rotary position encoding. So why rotary position encoding is important? As you see, when we feed, if I feed to the model, I like you, and I feel like, and then I will feed the same word in a very different manner, changing the word like elsewhere, like we have the same representation, because the model doesn't have any notion of position in the world. So we need to find a way of giving the model a way of understanding the position of the words, which it matters in the way we speak language. And we want these models to somehow understand, we want to understand what these models are basically doing. So that's basically what position encoding does. It gives the model the ability to understand the position of a particular word in the sentence. And what the rotary embedding position does is it basically rotates the embedding vector based on the position of that embedding in the sentence. That's basically what it does. But as you see, the vector representation of the embedding can be very big. So we need to find a way of doing it basically in a subset of that particular embedding representation. And what rotary position embedding does, it applies it at a subset of 2. So if you have a after we compute, and we do that to the carry and the key of the particular embedding. So then you have a key, for instance, that let's say 300. What we do is every pair we apply a particular, we rotate it by a particular Q and M, which is the position of the embedding into the sentence. Basically, this can be represented by this, this particular matrix multiplication. A formula, as you can see, we have like cosine and sin. I think it's something really that can take us hours to really understand. What I want to understand is just a way that we need to add the model, the ability to understand the position of the word, and the model needs to have something like that, so that it can see the pattern occurring. For instance, if I have a word that always is manipulated across different positions, the model can understand how this particular word changes. But for that, we need to do it in a predictable way. So matrix rotation, that's what we do basically. We take 2 subsets of the carry and the key, and we rotate them according to their position. As the model sees this pattern, this predicted way of this vector moves, it learns this position. And the fact that we add to the representation of the carry and the key means we are influencing the meaning of the key, so that the key doesn't become the same when it's before or after a particular word. That's basically what rotary position embedding is doing. And we do it in a pair inside of the K and the key. A more computational efficient way of doing that, as you can read in the original paper, is basically this. You have like 2 vector multiplications and then basically a sum. So basically, that's what we do here as a rotary position embedding. So we basically go to every key, for every red that we have. We go through the red size, for a particular head size. We go to, and we increase the loop by 2 because we are operating in pairs. And we basically access every pair for every particular head and particular 2 position inside of that representation. And then we basically apply the formula that we saw before. And here we divided by 2 because the way we stipulated or loaded the sign and the resize of the weights for the sin and cosine functions is that it should be the embedding divided by head and then divided by 2, because for every pair of keys inside of the representation for each particular red, we don't want a particular parameter for each of them, but for 2 of them. That's why we divide by 2. And then basically we finish computing the formula. And this is basically the whole implementation, as you can look at it as if I can pass you the slides. And then what we do next is basically just to compute multi-head attention, as I already explained it before. But before we do that, we need to actually look into something. As we explained it before, for every word in a sentence, let's say we have 3 words, like in this case, machine learning is fun. For instance, you can see that since we predict from the last word, predicting the next word, and we need to compute attention across every word and every carry at a particular stage in the function, what we need to do is we need to find a way of caching it, because otherwise we keep repeating the same computation as we move forward. And that's basically the concept of key caching comes from. It's just a cache that we can use to cache the carry and the key dot product, so that it's a way that we basically cache for every embedding the key plus the key matrix and the embedding multiplied by the key multiplied by the key matrix and the embedding multiplied by the key matrix is the key that we get, and then the embedding multiplied by the value is the value that we get, and we basically cache them. So this is basically a cache for it. Because we move forward, we don't want to keep repeating, since we just need the carry and key and value for the next word and not for the word that we already computed. So just basically caching it. So that's basically, we just call SD copy and then basically copy it to a particular cache. It's a 3D vector. In this case, we have a layer, we have a token position. There was a layer, and then in that layer, we access a particular token position that we pass it to the key cache, and then we basically save this particular we copy this particular key and value inside of the vector. So then basically what we do here, we basically compute the attention scores. We go for every head that we have in the code. And basically we go, and then the second loop, what we call is basically a time step. Basically what a time step does, it's basically is a way to capture in which word in the sentence we are. For instance, when we have like 2 words, the first attention will be just the first word, attention with itself, and then we will form attention between the first and the second word together. And basically this loop, what this loop is doing, just basically computing the attention cross. Basically what it's doing is taking every key and every carry of every word that we have computed so far, and then we store it to the state attention, and we index it using the time step variable. And then after that, basically what we do, we apply softmax. Of course, as we say, we have the dot product, but we need to apply softmax to the dot product, because the attention score of one word across every other, of one carry across every other keys need to be normalized so that they can add to 1. So that way we do a particular softmax across the dot product of a particular the key of a particular embedding that we processing across every other key that are in the sentence so far. And this is basically how we compute softmax, and I go faster into it because I have not much time. Softmax, and then basically we apply softmax. We call the softmax function, and then we apply softmax in the attention. And then we have basically the transform, where we compute the attention weighted sum. Here is basically what you're gonna do. Now we're gonna take that weighted after softmax that we have to see how much each word can influence each other. And we basically do it in a way so that we can have, and let's just go an illustration what we're doing here. We want every word, right? We have like the first word, its embedding, we take its embedding, we multiply by the carry, you get its carry, and then we multiply by the every key of the sentence that we have computed so far inside of that head. But the way we need to do it, we need to concatenate these results. So that's why we can see how these vectors are influencing basically the carry. So that's basically what we basically doing here. And we do it per head in a way so that we can concatenate the results, so that in the end we have the result from the head Z0, head Z1, and then head Z7. So basically, that's how we implement multi-headed attention. So basically, and then we basically start moving, and what we do, we take the head result and then we multiply it with the 8 output to move the vector that we get out of the multi-head attention, because remember, they're operating in a lower dimensionality, so that we need to map them back. And then basically what we do next, we basically apply residual connections. So just a way to help the model to remember what was the input coming from the previous layer. That's how we apply it. We just call this the transform, and then we transform by applying the input to the output, that particular layer. And then we have basically again, we apply again basically normalization to this particular layer. And then what we do next is basically we compute a feed-forward neural network, as you can see here. And then we have a 6-loop, basically, which is the function activation, the nonlinearity of the feed-forward network inside of the attention block. As basically that's what we do. We basically apply transform, and then we compute that particular formula that apply, which is basically 1 divided by the sigmoid of the particular activation at that particular layer. And then after that, we do again non-linearity multiplication to the model, and then after that we add another residual connection to the input. And then after that, what we have done, basically we get iterating multiple times, depending on the parameter of the model. That can be basically how much time we have, or how many attention blocks we have. And for particular input, we go through all the attention blocks that we have in the model. And then basically we apply the final normalization, as we saw in the architecture. Moving forward, we apply the nonlinearity. At this point, what we're doing now, we're converting the value that the logit, we're converting the normalized vector to logits, which are vector that we're going to use to apply softmax to, so that can give us the probability of what is the next word. So then we're going to need some functions to help us with that. So we have a sample function, which is a function that we're gonna use to basically sample what's gonna be the next word. So we have a random device, and then basically we're gonna create a pseudo-random number generator, and then we define what is the distribution of this random number that we're going to distribute. In this case, it's going to be uniform between 0 and 1. So we create a random we create a random variable called R, and then we sample from that distribution. And then basically what we do, we have the logit, basically add the probability, and then basically we return the value that if we have this, how can I say it? We have this function that we call CDF, or basically a variable that we have, and we're basically going to sum all the probability or logits that we get to the last layer of the model. So then we're going to stop it, or stop this loop iteration every time the CDF is higher than the random number that we predict, and then that's the number that we basically return. That's the index in the probability that you're going to return, which means it is the index of the next word that you're going to predict in the model. And then we just basically have argmax, and I will explain why we're going to use argmax basically. And then basically we are in the end, and basically just to apply softmax. So what we do is we define an int, a token, basically the first token that we're going to fit in the model. In the large language model is called BOS token, for instance. What we're going to do, we have the position. We start with 0 over the configuration that we load from the file that determines the sequence length, and we iterate over it, determining what's the biggest sentence that this model can generate. We pass the token, in this case it's the first token. We pass the position, in this case the 0 position. We pass the config and state. I'm assuming we loaded that from the files already. And then we pass the transformed weights that we load them from the files. Then what we do, we define a particular integer that's called next. Why is it integer? Because basically we need to use it to index. And then basically we have the temperature just to determine whether we're gonna use argmax. Argmax gonna do is it's gonna go to the logit and pick it the highest probability that we have, because the model output is the size of all the words the model can predict. And then we see which logit or which words is the most likely to be predicted, and argmax is gonna take that one that have the highest probability. So if we want this, we can always have the model that predicts the highest probability, but not what happened in practice. What we do in practice is basically we add a function, a variable called temperature that determines that the model don't actually always take the highly liked or the logit with the highest probability, but it can sample, and so it adds a little bit of randomness of the word that we can predict, and basically we predict that word and then we feed it back to the transformer function. Is that where we keep generating until we finish until we reach the length of the function, or the model predict it as the end of the function, basically. Okay. And with that, I conclude my talk. Thank you.
Thank you very much. Now it's time for a quick round of Q&A. If you have a question, please raise your hand up. Please raise your hand. Okay, we have a question there. Yes, at the back of the room.
Hi, thanks for the lecture, it was pretty cool. But I think the time was too low to tell everything about what you want to say. And I have a question, could you share this slides with us so we can take a look at it in our homes in chill environment?
Yeah, that was, I would say, I take it as experiment. If you see many people talking about implement large language model, you see it take like 4 or 5 hours. And that's why I say I will go faster, because I assume people have some background, but of course I can definitely share it. And that's basically what we can do. But I also plan actually to create a series that go into really deep details and instead of just trying to wrap up everything. As I said, every field that we have inside of a transformer is a field of research. Things like rotary position encoding, it hurts my feelings to talk it that way because it's such a beautiful concept. And I would like to go even more deeper into each of them, for instance. But of course, I can't really share, and I'm sorry if I went too fast today.
Okay, we have a question here in the middle of the room.
Hi, thank you for the talk. It was great. And I have a quick question about the rotary position embedding, because I want to make sure that I get it right. And we can say that that with that we rotate the embeddings of the word to fit the context of the sentence. Is that right?
Yes. So basically. So for instance, when we speak in a normal language, we have this word can appear in very different positions, right? For instance, the words I like you and I don't like you. You see the word like, it means different things. In one side, it means I like, another one feel like I don't like. But if you don't, the model need to say when like appear in that position, it's very means I don't like what's come next. So when like appears before, the model needs to understand that it actually likes what comes after. So that basically what you're doing is gonna get a hint to the model. Look, this particular, the impressive things about large language models is all about numbers and vectors and changing representations, right? Have these different fields that we have inside of the model, and basically it's like a machine. You keep tricking the embeddings so that they can mean different things. That basically we're gonna do. We're gonna have a different, let's say, vector representation that actually tricks that embedding so that it adds the semantics of position. So that's basically what you're trying to do. And the complexity here is you have two things. In one side, what you want is, okay, I want the model to understand, right, the position where the vector appears. But if this value that I add, for instance, in this vector is too big, then it messes with the semantics of the vector itself. So if the vector representation of like, you have another vector that representation of the position of like, and we add together, so it's all numbers, mixing up the representation, the position with the meaning of the world, which doesn't work very well. If you go to some sinusoidal position embeddings, for instance, that's where people move to rotary position, because what rotary does, it just rotates the vector based on the position, and it conserves the dot product between the two vectors, which is the carry and the key. So that's why it's been highly adapted in the field. I don't know if it was.
Okay, so it also rotates not only the embeddings, but also the key and the...
no,
okay.
It only rotates the key and carry.
And the key and carry, okay.
Yeah, because if you look at the key and carry, the representation of the embedding itself, so all of them make sense.
Okay, so it's not rotating the embedding, but only the carries and the keys. Okay,
yeah.
Okay. But also I have the question why it doesn't rotate the value. Because there is also the value vector for every word, yes?
Yeah, but if you think about the value vector is the thing that we want. For instance, if you have this word, let's say, the cat is blue, for instance, right? I would take the word, we will take the vector Kate, and I will multiply it by value, and we have a value. That makes it seem like if blue is about to be meaningful to someone, right? That's what blue should look like. And then we know that it's to be influenced to cat. But why is it influenced in the position? There is no notion really of position. We don't care about position. We care about influencing now. The position was captured before, which is the key and the query, which you used to do the dot product. That's where we want to find the relevance. And the relevance is in the relevance where position matters, not the value that we want to use to influence the actual embedding, so that it can be more meaningful and useful to predict the next vector or the next word, for instance. Like, you see, the value doesn't have no notion of position because it's not part of the equation that we use to determine how much one word should influence the other. It's actually the result plus, of course, the softmax weighted of this value that we use to determine how much you should influence, but not really otherwise. There is not really a need for the value because it's like the result, or basically the award of the dot product between the query and key to determine, basically that we're going to determine how much this value will be used to influence the next word. So it comes much after. At this point, we're already computing the query and key to find the similarity. So I don't see why it should be used in the care. That's why it's not used, because it's not really relevant for that equation.
Okay, thank you so much.
Thank you very much. Unfortunately, we don't have time for any more questions, but I guess that Felipe won't mind if you will talk to him on private, right?
Yeah,
so big applause once again for Felipe. And now I would like to invite you for a lunch break or a lighting talk. A lighting talk will take place, lighting talks will take place in each conference room, so you can stay here or move somewhere else, and you can go grab a lunch if you're hungry. If not, just please stay with us. So, do we have a lighting talk? Like the person who will... Okay, so we need a break. Okay, so 5 minutes will be okay? Okay, so let's make 5 minutes break and then see you here again. Thank you.
Hey, okay, guys, it's time for a slightly different format, as there will be given 2 15-minute lectures, and for our, of course, lectures for our receptive brains, eyes, and ears. So be prepared for fast and strong knowledge punches. The presenter for the first one is David Dulian. David is a 30-year-old IT engineering student at the Silesian University of Technology in Gliwice, and hopes that his dive into debug-friendly C++ templates will make them the powerful and broadly used tool they were intended to be from the very beginning. Hence the title of this presentation. Please help me welcome David. David, the floor is yours.
Hello, is this working? Okay. Hello and welcome everyone to my lightning talk. Thanks for coming. And the topic is how to enjoy the templates, how to use them with joy, and how to especially debug them, because that's the biggest issue with them. So first, I would like to ask you 3 very brief questions regarding the templates themselves. I would ask you to raise your hand if you know what templates are, how to generally use them, and how to implement one. Please raise your hand. Okay, grand majority. Fantastic. Out of those people, I would like to ask a second brief question. Who does actually use templates regularly or semi-regularly? Okay, so 80% around, great. The third question, out of those people, who thinks that the templates in their basic form are like comparably enjoyable, like reasonably enjoyable, like comparable to other programming challenges? Barely anyone. Okay, thank you very much. I also don't think that they are enjoyable in any sense because of the reasons I will present next. But those people that do enjoy them, great. They great. They provide great functionality. But not many people, as we can see, actually share this enthusiasm. And this talk will help you write code that will make your templates enjoyable for other users. And people who don't enjoy templates, welcome. That's why you're here. And I hope you learn something that will make it change. So first of all, a little reminder about templates. This is a code that would really use some templates because it is a function duplicated 3 times. It's not universal, and templates change that because we can just, instead of our type, like int double character that we define, we can just say that it's our type name that we insert everywhere where there is we need to use our type. And we define it, we specialize it when we use it, like lines 9, 10, 11. It's a great feature. And compiler does the rest of the work for us, and it is great. Templates are fantastic, they're great. They have a great idea of how to improve coders' life. But why are they so hated among the programming community? So here's the reason. That's why they are hated. Many people I heard that are familiar, unfortunately, with this monstrosity, because that's a casual error that results from using templates. That's just the template programmer's life. And this one specifically was a user from Stack Overflow, unfortunate one, that forgot to implement a comparison operation in their class that they used in one single function when the comparison operation was used exactly once. And this is the error. So yeah, this is rough. That's why they are hated. And they are so much hated that even there were talks how to get rid of those errors. And takeaway was to avoid using them like fire and just don't use templates at all and use other stuff, just forget about it. And for me, that is ridiculous because they provide such a great functionality that is gate-kept behind the error messages that are frankly unreadable. Maybe readable, but like 50% time, 50% like reading into errors is actually like overstatement because yeah, template errors are just very rough. So what do we do with those errors? Because they are not user-friendly, right? We can't see what's happening, and we should do something about it. So how about if this error, this one singular block of error that could easily be 7, 8, 9 screens long, if we change it to something like this, much better. We are told where the error is, line 22, and we are told what actually is wrong with our code. So function template comparing function is missing, something went wrong. So that would be much better. So what is actually missing from our templates functionality? First thing is clear errors, obviously. And second one, explanation. What kind of data types work with templates? What kind of functionality those types must provide? Because what's better than easily resolving errors? Easily avoiding making errors in the first place, right? So that's exactly why concepts come in. And these error messages, those little ones, were exactly what the concept error messages, those were the concept error messages. So they are short, simple, and they tell us exactly where to look for the error. And they are made before templates are even pasted into action. And second one, explanation on what kind of data types work with templates. Concepts are made so that they are themselves an accessible interface that tell us what exactly needs to be present in our data types in order for the template functions and classes also to work properly. So that is great. So concepts are basically requirements for our data types and for their properties. So we can, for example, require type to implement operations like comparison operator, have specific properties like member functions or variables, or maybe be specific type, and work properly in specified context. On that in a second. And that's the functionality. What do they do? But how do we use them? It's also very simple. We include concepts library, then we create a concept and we name it, and we substitute the type name keyword for our concept's name. So it's very easy. So maybe we will give an example. Right now it's just regular function that sorts a container, be it a vector, list, maybe deck, or anything else. So we have those template function, and we sort container inside. That's it. So how do we do it with templates? So that's how. First, we define, we add the include concepts, line 4 already done. Then we define our concepts body. And then on line 11, we substitute type name for our sortable, because that is what our type should be, sortable. And how do we actually define a concept? A template type name T, just as all the templates go, then concept keyword, our concept's name, and equals. And then we have all the requirements. For example, with the keyword requires, there is we put the operation that must not throw any errors inside those inside the parentheses, and that's it. That's our first concept implemented. There are also concepts that are already made for us that we can check into instead of type name keywords, and that's all great. For example, more mathematical, integral, floating point, totally ordered. We can use it just like that. But also for more programming related issues, we have those next. For example, sortable, move constructible, copyable, destructible, etc. And honestly, the first one, SD sortable, we just implemented. It's basically the same functionality. And these are just a couple I picked, a couple that are nice to showcase. But there are two that we will use once more in the presentation, SD convertible to and same as. They are quite different, but they can also be used as all the others. So that is actually all that you need to know to use the concepts. So that's this part of the presentation. And now I prepared some more examples when we showcase how to use them actually. So first is requiring operators methods. Let's jump straight to the example in a second, because it's basically we require operators to be present and functions to function properly, to be present and to not throw any errors. And here's an example. We have a function template simulate growth, and we do some things with our parameter that we pass onto this function template. It doesn't matter, but here we have it. So what do we do? No, first, we include concepts library. Then we substitute type name keyword for this concept name. Let's call it, for example, growable, because simulate growth, growable. And we create a function body. Concepts body. So here it is. Then we define requirements. So our requirements is line 16. There's default constructor with no parameters. Line 18, comparison between two objects. Line 19, .upgrade method. And then SDCout defined and object.changes must be also present. So we have those requirements, and we put it inside. So that's basically all that we need to do. We just, there's all. I don't think I need to explain further. But there's one thing more. The comparison needs to be between two operators, not operators, between two objects. So we just add another one. And instead of t more than t, which is also okay, we just switch it to t less than q or more than q, because it's just a bit safer. And then next topic, checking functions return times. Basically, what if our member function or variable or any other return type needs to be a specific one or convertible to other specific one? We use same as or convertible to inside of the concepts to define what types the return types need to be, how they need to function. For example, we'll go to an example shortly. But these concepts are a bit different because they have those angular brackets, right? So they're actually not that different from the others, because there are two ways to create concepts, is just the notation. So let's use the SD integral, but it works with any other type. This one above is just used as the concept, and this one below is used in our custom made concept that we are specifically making, right? And in our own example, we use those angular brackets because we need to define what type needs to be, what type it needs to be. There's also the third syntax, but we won't go into it at all. But just for the presentation is complete, I needed to include it. So let's get rid of it. And how do we join concepts together? Just simple logic, because it's just very intuitive, and we can just decide that our number needs to be either integral or a floating point, because that's a common use case, right? Okay, so this example, I don't have much time left, but this example we are presented with just lines 4 to 8 are important here. For example, we have the type that represents a pair, and the first argument needs to be convertible to unsigned character, and second convertible to double, because that's our requirements. We decided that it's working the best way, this way. Okay, inheritance and polymorphism is rather not common, but interesting, because with inheritance and polymorphism, we templates provide their own way to implement polymorphism, right? Because we decide what types our functions need to be specified to work with, right? And it's quite universal. So that's the first thing, and using concepts with classes that also use templates, it's just adding another layer of abstractions, and errors can get messy. So using concepts is like actually very beneficial. But also important other thing is that, let's go here. The types that are in libraries, the other external libraries that we use, we should be able to use those algorithms, for example, functions, their classes, with our own types. And this orange table let's assume it's the external library, and a great programmer provides us with a concept, shape type, that decides what kind of functionality does a type from his own function needs to have in order to function. So we can we users of this library can create our own functions and classes that satisfy those requirements, and those requirements are great, and we can use them, and we should be able to use them always. And last place, I don't have time at all, so just a little mention. STL containers, algorithms like vector lists, deck, and algorithm library. It's very common to use those types of containers inside our own functions and use their functionality. For example, here's a great example that we insert. We have function templates where we insert to the container the same number of elements, but they are multiples of pi number. And for example, it's a great concept that we defined. It needs to be pushbackable and needs to have size that is convertible to size t. It's very, very nice. And I don't have time for this example, but the takeaway here is that it is a good practice to split concepts into one singular functionality that can be used many times. So, for example, we split our parsable sortable container that prints elements into two concepts: one parsable sortable container, and second one to have printable elements. And that's actually all that I had prepared for this presentation. So to sum up, concepts are great, great to work with templates. They provide clear errors and clear interface what needs to be done in order for the types to function properly. And it's just a fantastic way to improve your code, whether you are writing it or using it, or maybe both, probably both. So I would like to thank you all for joining, and also I would like to join my team and our teacher and research guide, Grzegorz Wojciech Kwiatkowski from Silesian University of Technology, because he decided that it would be a good idea for us to be here, be present, and share those knowledge. So thank you all for joining, and that would be all. Thanks. Okay. Czy jeszcze? Znaczy nie wiem. Nie wiem, mogą być. So. Nie wiem. To jest basic level, więc raczej to jest taki bardziej introduction. Wydaje mi się, że nie.
Another lightning talk concerns design thinking. Speaker, Michał Prorok, currently working as delivery manager, will take you on a journey entitled Design Thinking, not only for extroverts. Michał is an experienced manager in IT industry. Moreover, for 6 years was active in Project Management Institute, Poland, where he had an honor to be a managing director for Wrocław branch. Originator of the Management 360 conference in Wrocław, as well as PMIthon, a hackathon-style event for project professionals. Please join me in giving a warm welcome to Michał Prorok.
Hello, everyone. Thank you for joining me for this lightning talk. I hope you can hear me all right. Right, I said it last year because it's my second time on Code Dive conference, and I will say it how many times, however many times the organizers will accept me as a speaker. It's always good to be back in those screening rooms that I used to clean so many times because I worked here, but a slightly different position than now. Today I want to show you how introverts bring unique value and are indispensable when it comes to the design thinking process, and why embracing their strengths can lead to breakthrough solutions. But let's start with the basics. Oh. Slight technical issues. Let's check it out. Okay, I will use the keyboard then. Right, introverts, extroverts. You may ask what? What is it? I think it's getting more and more common knowledge to know those terms, but still, let's start on the same page. Those are basically types of personality types. These terms were rooted in psychology and are often associated with Carl Jung's theory of personality types. We often use them as a flattened version of the information provided by the theory, but they form part of the broader spectrum of individual differences in temperament and behavior. What really does it mean to be introverted or extroverted? Let's start with extroverts, because they would be the first one to talk when asked, right? Extroverted people, we tend to perceive them as very open, very social, very energetic, people who would raise their hands when asked if there are questions in the room, right? Extroverted person tends to gain energy from social interactions. As opposites, we have introverts. Introverted people gain energy from solitude and internal reflection. They tend to spend time on their own when they want to chill, right? Extroverted person would call their friends and ask, hey, are you going out? Are we doing something? I need to relax. Introverted person would rather stay home with a great book. And we are talking today about introverts mostly, but let's destroy everything that I have just said, and let's introduce ambiverts, just for sake of inclusion. I am actually an ambiverted person because I don't really mind standing before you and talking, and I also gain energy from doing that, but I will be sleeping for the next 4 days after that, just to regain my composure and be able to go back to work. So ambiverts are flexible, extroverts gain energy from being outside, introverts gain energy from being inside themselves, their house, their room, whatever it may be. So, we know what personality types are, but there are more differences between people to take into consideration when creating a communication pattern or making them participate in design thinking process. Let's look at neurodivergence. Neurodivergence people are individuals whose neurological development and functioning differs from what is considered typical, right, or neurotypical. The term encompasses a wide range of cognitive, developmental, and behavioral variations, and is often used to challenge the notion of a single normal way of thinking or behaving. It's more and more accepted, more and more understood, and the types of neurodivergence are widely explored, to be honest, at the moment. We still don't know many things about it, but we know more than even 5 years ago. Some of more recognizable examples of neurodivergence are ADHD, OCD, autism spectrum disorder, dyslexia, dyscalculia, dyspraxia, or Tourette syndrome. I think most of them you may know, most of those you may know. What I didn't know what is dyspraxia, to be honest, because dyslexia is a difficulty with words, with writing, with reading. Dyscalculia is with numbers, with maths, with calculating, and dyspraxia is impacts motor skills and coordination. So basically we have those three terms encompassing all aspects of the development of a person. Right, let's pause those psychological terms for a moment and let's look on another side of the fundamentals of our discussion today. Design thinking. We are talking about introverts in design thinking, so it would be nice of me to tell you what design thinking is, if you don't know that. So design thinking is a problem-solving framework that focuses on understanding users, challenging assumptions, redefining problems, and creating innovative solutions through a human-centered approach. Very nice definition, but what it means, it's a set, I like to call it as a toolbox or a utility belt with a set of tools, processes, procedures, ways basically to make people collaborate, to make people understand each other better and come up with a solution while looking at the human experience during the design and during the use of the designed tool, process, any outcome that it may be. Right, so what are the key characteristics of design thinking as a methodology, as a framework? It is human-centered, as I mentioned, so the human experience of the design, of the outcome is in the center of the process itself. It is iterative, so we test, we try, we improve. It is empathy-driven, so it is important to understand what our key stakeholders and people involved in the process are thinking and are feeling and are contributing. It is collaborative, so we focus on collaboration, of course. So we focus on having everyone included and everyone contributing to the idea to the best of their abilities and their wants and needs, of course. It is problem reframing. So we focus on the problem statement as many times as is needed to provide different perspectives and to provide possibility for everyone to understand it in their own unique way. So those are 5 key characteristics of the design thinking process, but what is a design thinking process? Because I still haven't told you that. It basically looks like this. So we start with a step called empathize, then define, ideate, prototype, and test. It may seem similar to those of you who work in Agile. It's not that far away from that. But the first step is empathize instead of any sort of analysis, right? So we need to gain a deep understanding of the user's needs through interviews of our key stakeholders, through observations, and other research methods, whatever they may be, it would differ on the subject matter that we want to investigate. Then we define, we synthesize our finding from the empathy phase, from those interviews, from those research outcomes, to clearly articulate the problem or a challenge. Because we may think we know what the problem is and what do we want to get from the process. Then we ideate, we brainstorm, we create solutions. We go into the prototyping phase, where we build a tangible representation of the idea. It may be even a mirror board, right? But we have to show something to again, consistently understand in the team, what are we doing, basically. And then we test. We test the prototype with users, gather feedback, and refine. And actually, in this phase, my favorite tool is called create, destroy, and fix. So one person creates something, the other person lists everything that is wrong with this idea, basically destroys the idea, and the third person tries to fix that. And then we get to the outcome, right? So why is design thinking perceived as it is for extroverts only, as it is designed for extroverts only. Basically, it emphasizes group activities. So brainstorming sessions, workshops, collaborative discussions can be daunting for an introverted person. Again, rapid ideation and spontaneity. Brainstorming, a commodity activity, encourages quick, spontaneous solutions, speaking, what are you thinking, and providing feedback in very quickly manner. So it again may be scary for people who are more introverted, who would like to have a bit of an introspective. Social and public interactions, so easier interviews, so you have to talk to people, you have to present your ideas, you have to speak in a large setting. And then facilitation and leadership roles. So we have people who facilitate the workshops, and they are kind of hierarchical. Sorry. So if they lead, they are our boss in this setting. That may be daunting as well, and I have to keep the pace up. Challenges for extroverts, for introverts. Sorry. Pace of collaborations, dominance in group dynamics, preference for solitude. But design thinking can work well for introverts as well. Why is that? So it is empathy focused, as you know. So introverts often excel in listening and observing. So those are critical for understanding users' needs. So they can be very well adept in conducting those interviews and getting information from the users, even if they are kind of scared to talk to people, right? They are creativity depth, as I called it. Introverts bring deep, thoughtful perspective because they tend to be inside, right? They have introspective going on often, all the time. You can decide on your own. And they bring those skills to the problem-solving phase. The framework is structured, so a person, introverted person, knows what is going to happen next, even if it is like a chaotic discussion and then people are sharing their ideas very quickly. They know what is the next step of the process. And they bring diverse strengths in collaboration. And if they are in the know, if they know that they are appreciated, they can provide great value because they have ideas and they just need to be listened to. How can design thinking be inclusive? What really can we do to provide that? We should incorporate reflection time. We should allow the individuals time to process and develop ideas independently before group discussions. There are tools, of course, for that. For example, there is a tool that breaks the issue into small sections of several minutes, starting with let's say 12 minutes for creating ideas. Then we have to select them. Then we have to do something else. And then we go down in time, right? The last piece of this exercise, the last 1 minute, and you have to make a rapid decision. And then they can use this knowledge and share it with the group instead of just talking. Facilitate equitable participation. So use structured activities like round-robin sharing. So go around the table and ask everyone to share so they have their time and space to say what they have in mind. For them not to have to yell because another person is yelling because they have great idea, right? As stereotypical extroverted person. We can leverage asynchronous tools. We can employ online platforms like Miro or Mural for ideation and collaboration for introverted person to get in grips with their idea before sharing. We can create smaller, more intimate groups. We can break out those sessions into smaller ones to allow people to get more familiar with their surroundings, with people they are cooperating with. And then selected person from the group could share the outcomes of the discussions. We can utilize written and visual expressions. So we would like to encourage drawing, diagramming, creating those prototypes that I mentioned, and allowing people to use alternative ways to communicate their ideas during ideation process. So basically, you should have a whiteboard or any paper in the room, or Miro. Focus on individual contributions. Assign specific roles or tasks that people could play and people could use their individual strengths in those tasks and ideas. Especially in prototyping stage, if you ask an introverted person who knows that they cannot draw for the life of them, they will be very stressed, right? So find someone who can draw. And last one, reframe the facilitation process. Assign specific roles or tasks that play to individual strengths, including the facilitation, because the facilitator is a key player in the process that encourages the people to share, that encourages the process to go on, and allows people, especially introverted ones, to express themselves freely. You might be thinking then, why put so much attention on all of this? Because it's not easy to be that inclusive, right? Introverts are often seen as quiet, reserved, hesitant to take center stage, but did you know that they have some of the best ideas, and they are ranked as some of the best collaborators in design thinking if done properly? People who deal with design thinking, including in progress design thinking lab, made some checks during their processes, and introverted person are really great collaborators. So next time you step into a design thinking session, ask yourself, how can I make room for introverts taking part in this process? And if I would like to leave you with something, introverts aren't a limitation. They are a hidden advantage to the process. So we just need to be mindful to start designing with them and for them, because they are our users as well, so we can get better results. Sorry for taking longer than I should have. If you want to connect, this is my LinkedIn. I will be posting again about design thinking and business psychology. So thank you.
Hello? Okay. Thank you, Michał, very much. Right now we can take a 10 minutes break if you want to. If not, you can stay in the room and see you 2:15 on the Andreas presentation. So thank you very much for your attention. See you later. 1, 2. Okay. Welcome after the break in the room number 9, when you are probably waiting for our next lecture. But before I will invite our presenter on the stage, let me share some facts about him. Andreas Weiss has been writing C++ in many different domains, from real-time graphics through distributed applications to embedded systems. His current focus is on writing software for safety-critical systems, in particular in the context of automotive software. He's an active member of ISO C++ committee and the MISRA C++ working group. Andreas is also one of the co-organizers of the Munich C++ user group. Fun fact about Andreas is that his favorite comic book character is Scrooge McDuck. I think that we can share this opinion with him because I think that we also want to swim in the gold pool like Scrooge McDuck used to do. Okay, so the title of the lecture is Deciphering C++ Coroutines, Mastering Asynchronous Control Flow. Andreas, the stage is yours. Big applause for Andreas.
Thanks. This is Deciphering Coroutines. This is me. You can find me in various places on the web and also contact me via email. And you noticed on the title slide there was a part 2, because I was already here at this conference 2 years ago with a talk called Deciphering Coroutines. This talk assumes familiarity with the contents of part 1. So in particular, it assumes that you know the basics of the coroutine language mechanism. We'll do a very quick recap of part 1 now, but it will be very brief, so hang on tight. So a coroutine is essentially a function that can be paused in the middle of the function body, and then you can resume it later with all of the surrounding state of the function still intact. And there's really 3 major components of the language mechanism that you need to know about. The first is the return type. This is just the return type of the coroutine function that you see in the signature. This is a user-defined type. And it defines the interface through which the outside world can interact with the coroutine. And since it's user-defined type, you have pretty great flexibility what you put there in the interface and how you make that look like. The language really doesn't restrict you a lot there. And one of the goals of this talk is to help you a little bit better to understand what a sensible interface could look like there. So a simple example that you could have is you have a coroutine here, and then the return type of this is what we're talking about here. And you will notice by just looking at the function, you have no way of telling whether this is actually a coroutine or just a normal function. You can't tell this from the outside. And that's an important aspect of the feature. So the best way to think about this is that the first call to a coroutine function is like calling a factory function that produces the return type. It does not necessarily execute anything of the implementation of that coroutine, but it for sure will fulfill that duty of creating that return type. So since C++23, we actually have one of those return types in the standard library. That's the state generator, and this allows us to yield values from the middle of the function, like we do here, in the middle of the loop. This generator implements the range concept, so anything that works with ranges can consume the values from the generator, like we do here with the range-based for loop. You can also pass it to ranges algorithms or anything else that you could do with ranges. If you don't really see how this is useful to be able to do this co-yield from the middle of a loop, try implementing an iterator that traverses a complex data structure like a tree or a graph. Like start out by just writing the loop that just prints the element, and then try to refactor that into an iterator, and you will see that this is surprisingly difficult. And with coroutines, this allows you to write like the most simple form of that code. So it doesn't really increase the expressive power of the language, but it makes it much easier to write certain things down. And if you go back to part 1, it showed you actually everything that you need to write such a generator yourself. The second part of the mechanism is the promise type. So while the return type determines the user-facing interface, the promise is part of the compiler-facing interface. So it provides means for customizing the behavior that is invoked during startup and shutting down of the coroutine. This is what it looks like. So unlike the return type, which we can implement pretty much whatever we want, here the standard specifies a set of functions that we need to implement. And then those functions will get called by the compiler, so by the language mechanism as the coroutines goes through the phases of execution. And these are not functions that we call from user code, right? These are being called by the language mechanism, which makes them a bit special. The final part is the awaitable, the awaitable is a type that we can use as an argument to the operator co-await. So the operator co-await is the operator that we call whenever we want to suspend a function. And the argument to that operator is of type, of an awaitable type. And like the promise, this is also a compiler-facing interface. So again, there's 3 functions that are specified here, which we can implement ourselves to customize what will go on whenever the coroutine machinery reaches a certain part of the execution. And in particular, this customizes what happens before suspension and after resuming a previously suspended coroutine. And then we also saw in part 1 how all of these facilities are connected, and we built up this little cheat sheet that we can use to reason about like how data flows here. If you haven't seen this before, notice in particular the promise at the bottom here, which has sort of a central position that holds the different worlds of the caller side code and the coroutine internals together, and we can use that object to exchange data between the two. If you're familiar with the cheat sheet and you want to use it to follow along, here's a QR code where you can get it. I will leave this up for a couple of seconds. But I want to talk very briefly about like why I'm now back with a part 2 after 2 years. So at the end of the last talk, I said, you now understand all of the boring parts of coroutines, and now you can actually start doing something interesting, but I didn't have time to cover any of the interesting stuff. So this talk is about one of the interesting use cases, more interesting than just a generator, and one that is of particular prominence, namely asynchronous computation. So in other languages like C#, Python, JavaScript, Rust, they all have dedicated language features for this, and they typically use this pair of keywords, async and await. And we will see in this talk how we can implement with the C++ coroutines something that brings us very close to what we have in those languages through those keywords. But we will also see like some of the differences, how C++ does things differently. If you're like most people and don't really understand what is the deal behind coroutines, why you would want to use them in the first place. Andre gave a great talk last year here that focuses exclusively on motivating coroutines, specifically for this use case of asynchronous I/O. It's a great talk. Watch it. I will not be covering any motivation here since we're already short on time as it is. A few words of caution before we dive in deeper. I will at times lead you astray. Please don't get confused by this. Hopefully this will only help deepen your insight whenever that happens. I will not be covering multi-threading since that's its own can of worms. And this is not a best practices talk. Like this is everything you will see here is pretty much slide code. Please don't copy this into a library for general use. All right. Let's start by building a mental model for what we're trying to do here. So our scenario is we want to execute some complex task, right? So we have some function that spawns up this task, and then we have an outer function that computes like some partial results depending on what is provided by this middle function. This middle function in turn also depends on another result from an inner function. And now in this inner function, we have this blocking I/O call, right? That is just needs to do some I/O, and that could just take a long time in which we cannot really do anything except wait for the I/O to come back, right? So while we're in there and waiting, like really none of these functions can do anything sensible, right? Since they all depend on this I/O result to come back before they can continue execution. But main is now also blocked, but main actually may be able to do something useful in the meantime, right? Spawn another task that carries out an unrelated branch of computation. So what if we could just suspend those functions over there while we're waiting and then do something useful in the meantime? That's the main idea here. So a straightforward solution to that is just use threads, right? Just spawn all of these tasks in their own thread. So they go ahead to the side and they run in parallel to main. And then while the inner function is waiting for the result, main can in the meantime just do other things. Of course, threads have a bunch of problems. Thread creation is quite CPU intensive. It's also memory intensive. Thread switching is also expensive, right? If you have a context switch like between main and worker threads, you need to pay for that. The blocked threads, even though they're not blocking main, they may still consume CPU cycles. And depending on how your operating system implements this might be a non-trivial overhead, especially if you have a large number of threads. Once you have threads, you need to think about synchronizing access to shared data. And if you've ever done multi-threaded programming, you know how hard this is. And there's more problems, right? So this is a solution, but it's not an ideal solution. And in particular, it's not a solution that scales well, right? Like this might work well if you just have 1 or 2 worker threads, but the more threads you have, the more difficult these things become. So one alternative to threads that is often mentioned is these so-called green threads, sometimes also known as fibers, user mode threads, cooperative multi-threading, and also stackful coroutines. So how does it work here? So instead of spawning a thread, we're spawning a green thread. And then in the inner function, we now split our blocking I/O call up into 2 parts. So we start with a setup that just sets up our I/O request. But then instead of waiting for the result to come back, we suspend at that point. And we want to be woken up once the result becomes available. So the way that this looks like is when we spawn the green thread, this thread is spawned on the side, our task stack is being built up there. Then we reach this suspend call, and at that point we switch context over to the main thread. The main thread now returns from the spawn function and can do other stuff in the meantime. Eventually our result comes back. Main will invoke some sort of completion handler, and that will then in turn suspend main, and again hand control back to our green thread that was waiting for the result. And now our inner function can continue executing. So this looks somewhat similar to what we've seen with the threads before, but green threads, because they don't involve a context switch that requires help from the operating system, they can be executed with much less overhead. There's no synchronization needed since we don't have anything actually running in parallel. Everything runs sequentially. But the threads need to cooperatively decide when to give up control and hand over to another green thread. However, the intuition about control flow is still very similar to threads. So if you already know how to program with threads, then programming with green threads is like similar intuition. It's just a little bit easier than before because you don't have these threads running in parallel. So how can we implement something like this with C++ coroutines? So the biggest difference here is that C++20 coroutines are stackless. And that means we can only suspend one function at a time, right? Whenever I suspend from a coroutine, control goes back either to my immediate caller or to whoever was resuming that coroutine. So if we want to suspend a computation that is spanning multiple functions, we need to suspend them all one by one. And that's really the goal of this talk, right? We want to figure out how we can suspend an execution context that is larger than a single function. That's the one thing that this talk is about. Okay, so let's try and do this. Okay, starting from our blocking I/O call that we have. We want to introduce coroutines. So the first thing that we do is we sprinkle the coroutine keywords in there. And then we now also need to change the return type to be a coroutine return type. I call this one async here for the purpose of this talk. You will often see these return types named something like task. Recently, also people started to favor lazy as a name for this. I call it async here because of the symmetry with async await in other languages. But there is a design space for how these types look like. So be aware of that. But really, at this level, there's nothing more to do. Like there's some magic going on there inside the async I/O call that I don't want to go into at this point, but that's pretty much what happens at the innermost level. Now, at the middle function level, again, the same thing, right? We sprinkle the coroutine keywords in there, and we have to change the return type. But now, something interesting happens. If we look at the first line of the body of the middle function and we pull that apart, we will see, okay, what's actually happening there is we're calling the inner function. This is like we said before, like a factory function that gives us back the async I/O result, and then we co-await on that. So what we see here now is we have the async type in two different roles. We have this once in the role of the return type and once in the role of the awaitable. And we didn't have that before. So the async now has a dual interface. And understanding that is one of the key insights here to how the mechanism works for async I/O. So let's look at what happens when we want to suspend nested tasks. So we have adjusted all of our interfaces, and now let's say we're in main, we want to spawn up all of our tasks, right? So we spawn up our stack of functions, we reach the inner function, and now it reaches the point where it's waiting for the I/O. So we want to suspend it and drop it off the stack, right? And we really want to do this with all of the outer functions as well until we get back to main. Main now is free to do other stuff in the meantime, and then eventually when we have the result, we want to resume the computation, we want to resume the called stack to its initial state, right? That will be the simple intuition if you come from green threads. So let's zoom in a little bit. Let's see how that works in detail. So we're here in the outer function, right? We get the awaitable back. Then we call co-await here. Okay, everything's fine. Await suspend on the awaitable is called, and now the function goes into suspension. Now, things happen in the background. Eventually, we're woken up. The outer function can continue execution. Await resume is called. We're back in the outer function, and yeah, this is actually not what we wanted, right? So we didn't want to continue execution of the outer function, right? When the I/O result is available, where we want to continue executing is in the inner function, because that was the one that was waiting for the I/O result. So this is actually not going to work. And this is the first important lesson here. Resuming suspended coroutines from the outside in does not work. And the reason for this is once a coroutine has been resumed, it cannot be suspended again, unless we also call co-await again. But we do not know from the outside how often we need to do this, because we don't know what's going on inside this inner function, right? This could need like 100 I/O requests before it has finished, and we can't just keep calling co-await. So the intuition here should always be, if I co-await such an async function, what I want that to mean is wake me up once that function has completed all the way through and its final result is available. Switching gears here for a bit. What's a call stack anyway, right? So we have kind of this problem now that we need to suspend and resume these functions one by one. So we're sort of doing what the call stack is doing in sequential execution. So it might be worth taking a closer look here. So in memory, right, we have this region of memory that holds all of the things that are relevant to the execution of our function. And then we have these three registers, a stack pointer, a base pointer, which is often also called the frame pointer, and the instruction pointer. So the base pointer and the stack pointer, they mark the range of memory in which the state of our function resides, right? And then the stack grows as we accumulate like more local variables to the function. And below the base pointer, we have stored on the stack the frame pointer and the instruction pointer of the function that called us, right? And this is important because once our function has finished executing, we need to know where to jump next in memory to continue execution with the surrounding function, and we also need to be able to restore the state of that function. So one way to think about this, what is happening here in memory, is that we really have a linked list of stack frames, right? And we can follow them by going like from the base pointer and then like through the individual stack frames in memory, from jumping from frame pointer to frame pointer. So this is a singly linked list of stack frames with links pointing from callee to caller, right? So inner functions point to outer functions. And because we can traverse this list in memory, we can always hand control from inner functions to outer functions. So we will need to do something similar to this. So from now on, I will use a color convention here to make things a little bit more transparent to figure out. Whenever you see something marked with the indigo color, as on the top, that's the inner function. Whenever you see something marked with the orange color, that's the outer function for the context that we're talking about. So indigo, inner function, orange, outer function. So if we look now at the async object and the two roles that it plays, then we see that in the context of the inner function, the async plays the role of the return object. And in the context of the outer function, the orange function here, it's playing the role of the awaitable, but it's the same object, right? So the object that is returned from the call to the inner function acts as the awaitable in the context of the outer function. So to clear this up a little bit, let's look at the two roles in isolation first, and then let's see how it comes together. So the return object part is the easier of the one, especially if you're familiar with the things that we talked about in the last talk 2 years ago. So the return object, we will put in there a coroutine handle that points to the inner coroutine. And we will use the constructor of the return object to populate that handle. And that's really all that's going on here, right? So this constructor will get invoked through the promise by a mechanism that is largely driven by the language. You don't need any user code to end up in this constructor, and you will get passed by that language mechanism this handle, and we then just store it away in the return type, and then it just lives in there. That's all that we do, right? Nothing more happens here. So let's look at the other role. Let's look at what happens from the awaitable side. So what an awaitable really is a type that provides the three functions: await, ready, await, resume, await, suspend, right? So we need to implement those three. So for now, in the await ready, we just say, okay, whenever ready, we really want to suspend. We don't quite yet know what to put in the await resume, because that is the function that will need to deliver the final result that that function was supposed to compute back eventually. But if we look at the await suspend and we look really carefully, we will notice something here, because there is a coroutine handle that's being passed here. But what is that handle pointing to, right? That's the handle to the coroutine that is about to be suspended as a result of awaiting on this async object. And that is the outer function handle here, right? So we really have two different handles here. The one that we stored at the creation of the async object, that's the one that's pointing to the inner object. But this now here is a handle to the outer function, which is the function that co-awaits on this object. So we also store this away. And if you now play this through repeatedly, right, you go to this little dance at different layers of always storing these two handles, and you draw a little picture of this, then you will get this, right? So each async object points to a promise, and the promise has a coroutine handle that points to its caller. And this is very similar to what we had before with our call stack. So we're up to something here. So the next question is now, I mean, okay, it's one thing to have this information stored away somewhere, but what we actually want to do is we want to resume the caller from a nested coroutine. So how can we do this? So assume you're the innermost function and you're done with all of your work, right? You have completed your result, and now you somehow need to wake up your caller, right? But your caller is not on the call stack anymore because everything was suspended, right? So how do you get him back? So we have the handle to the outer function, right? We saved that in our promise type. And now the question is like, how do we resume execution of that coroutine? So since the inner function has already completed, the way where we want to do this is in the final suspend, right? That's the customization point that will get called when the inner function reaches the end of its body, right? When it returns a value or when it falls off the bottom of the function. And now the final suspend allows us to return an awaitable that the compiler will then call co-await on. And that is the mechanism that we use here to transfer control flow. So I will just define this awaitable here at the bottom, which I call resume caller. If we look inside that, so remember we still have the handle that we want to resume stored away in the promise at the top. So in here we just say await ready false, like we're done executing and we want to suspend, right? The inner function doesn't want to go on. Await resume will never be called, right? The inner function is done. We just want to get out and want to get back to our caller, so we don't need to do anything there. And in the await suspend, we now return as a return value the handle to the outer function that was saved in the promise. And if you think back to part one, we mentioned this in the very end, this is what is called symmetric transfer. This is a way how you can transfer control from one coroutine to the other. Similar to what we saw with the green threads in the beginning, where just like one thread suspended and then it swapped places with the other thread. This is a similar thing, only that the level of granularity here is always a single coroutine. So let's look at that in more detail to visualize this a bit better. So at the beginning, the situation that we have is we're in the inner function here, and we want to get back to the middle function at the top where the teal-colored arrow is. But that function is not on the stack, right? We only have like some base mechanism on the stack that is like part of the outer framework, and then we're in the inner function. So what happens is the inner function is done, right? So we call return value to handle whatever happens with the return value. And then we call final suspend, right? So we've now fallen out of the body of the inner function, and then we get to final suspend in the promise. This will now construct this resume caller awaitable, and then the language mechanism will call await suspend on that awaitable, and this will now return the handle to the outer coroutine. And now what happens, the part with the symmetric transfer, is notice how now we have the inner function on the stack, and it just changes places with the middle function, right? So here we had the inner function, and now it's not like a function call to the inner function, right? Because then inner would still be on the stack. It's like inner goes into suspension, it's now a suspended coroutine, it's paused, and it swaps places on the call stack with the middle function. And now the middle function resumes. So await resume is called on the awaitable. This takes care of like propagating the return value back out. And now we're back in the body of the middle function. It can continue moving on. It drops to the next line, and now what happens is, remember that the return value of inner function, that was actually the async object, right? But that was only a temporary on that line. So once we move to the next line, that temporary will get destroyed. And at this point now, the inner function goes away, right? Before it was just waiting in the suspended state, but now actually that we've moved on, now it actually gets cleaned up. So the order is a little bit different here, but the end result is still the same than what we would have in a normal function call. So again, here's the overview. The difficult thing here is really to keep track of like what is the context in which this async object is currently being used, and what are the different handles, right? The handle, what is the handle to the outer function? What is the handle to the inner function? And it's a bit hard to follow along with this if you just see it on the slides. But if you actually start writing code and you pay a little bit attention to this, I hope you will be able to figure it out rather quickly. Okay, so this gives us everything that we need to like resume from an inner coroutine to like its outer function. But we still haven't talked about like who resumes the innermost function, right? Somebody needs to start the chain, right? If we suspended everyone, then somebody needs to make the first resumption. Somebody needs to wake up that innermost coroutine. So how does this work? So I was being pretty hand-wavy before about what really goes on here in the inner function, but in the end, there is like some I/O framework, right? That you register with to say, hey, I triggered this I/O operation, and now I need to be woken up whenever that completes, right? And then like some machinery in the background will do like an epoll or a select, will eventually realize that, hey, this result is awaitable, and then that external mechanism needs to wake us up here. But for that to work, we need to register ourselves with that mechanism somehow, right? So what happens here is like this I/O awaitable that falls out of here, that is part of this external mechanism. But to construct this, we need to tell it like what to register with, right? So I call that the scheduler here. And the scheduler, that is really the entity that keeps track of all the outstanding I/O requests and what are the corresponding coroutines that need to be woken up when that result arrives. And the scheduler, like where does that come from, right? It's not anywhere in the function right now. So usually that lives at the level of main, right? So if you think about, if you ever work with Boost ASIO, you will have this I/O service, which you need to pass to all of the objects. because that's where they register themselves for the async results. And that usually lives at main, or at least fairly high up the call stack. So the easiest way would now be to just pass this down as an argument, right? So each function would gain a scheduler argument. But that's not very nice, right? So you will have this explicit argument everywhere, so your function signatures get blown up. You also don't really get any flexibility in changing this later, right? You need to know the scheduler upfront, and you need to propagate it all the way down, and it cannot change. So yeah, let's see if we can do better than an explicit parameter here. So yeah, how can we pass data from the outside in? So again, our point where we were establishing the links here was always the await suspend function. And we can really pass the scheduler along that same chain, right? So we have the link here where the right side gives us the context of the surrounding function, and any information that has, we can pass along to the inner function. One thing to watch out for here is that this promise type here that I have in red, because we're now having the two different contexts, like the inner and the outer, on the same line. If they have different return values, right? If the outer function has a different return value from the inner function, there will be different async objects, right? Since the async object is templatized on the return type. But since the promise type is a nested type of the async class, the promise types will also be different here. So that's a subtlety to watch out for. So really, this needs to be a different type. So we need to templatize it here. But we also don't want this to be an arbitrary type. We want this to be a promise that we know has a scheduler in there that we can propagate, right? So there's sort of this notion of a concept lingering here of what it means to be a promise that plays nicely with this mechanism. And hopefully someday we will get some advice from the standard library what we can do here, but not today. So far we need to figure this out on our own. Okay, so this now allows us to propagate a scheduler along, like from outer functions to the nested inner functions. But there's still a problem here, because if you think about, okay, like when do we actually need the scheduler? It's at this point where we've first reached the first asynchronous I/O call. But like this await suspend, when is that actually called? That is called when the outer function for the first time co-awaits on the async object that was returned here. So this has not happened yet, right? If we build up our call stack naively, as we would do in the synchronous world, at the point where we first reach this line, nothing has been propagated. The scheduler pointers are all null, and we don't know the handle to our outer function. So in order to avoid this problem, you really want to spawn all your tasks lazily. You want to make sure that before you first enter the body of the coroutine, all of the necessary information has been propagated. And this will now lead to a bit of a conundrum here, because it's very easy to just say, okay, then suspend always, everybody goes to sleep immediately. But then what happens is, okay, the outer function, it starts running, but then before it can do anything in the function body, it gets suspended immediately. But that's a bad point to suspend, right? We didn't do anything useful yet, right? We wanted to continue with the middle function. We wanted to get to the inner function where the I/O call happens, right? Because that's when we want to suspend, when we actually set up the I/O and we're waiting for the result. Suspending here is too early, right? So this also doesn't work. So what we need is sort of a middle ground here. And the way that this is done, and this is most complicated thing here, so that's why I left it for last. So bear with me. In the await suspend, right? The await suspend is called on the awaitable of the inner function. It gets as an argument the handle to the outer function that is about to suspend now as well. Now, instead of just suspending here and going like even one layer further up, we're returning here the handle to the inner function, which means we're doing a symmetric transfer right back into the function that was suspended earlier. And let's look at this in detail, because this is the confusing part here. So I'm in middle function here, which is the inner function for this context. Initial suspend says, yeah, before you do anything, go to sleep immediately, right? We don't even enter the body, we don't do anything. So it goes away, right? We're back in the outer function. It now calls co-await on the async object that was just returned to it. It goes into await suspend. And then the await suspend returns the handle of the middle function. So we again do this symmetric transfer thing, right? So notice here we have the outer function, and now it goes away, and instead we get the middle function again. So the outer function suspends itself and then hands over via symmetric transfer to the inner function. And really, at this point, why should we stop at the scheduler here? So let's change this a bit and say, like, okay, all of our promises now inherit from a common base class. And in this base class, I keep two pointers, one that points outwards to the caller and another that points to the child. And now in the await suspend function, I just establish the links in both directions. And now you can really propagate any data that you want along your async task stack. Because your call stack really now is just another data structure. And you control everything about that. So to give you one example of what the consequence of this is, because of the symmetric transfer that we're doing, right? You never get the full call stack with like outer, middle, inner function, right? Because as soon as you hand over, you do this little dance where the outer function is suspended and you symmetrically transfer to the inner function. So if you look at this in a debugger, you only see the inner function, right? And you don't know the context anymore in which it was invoked. And this is really painful for debugging. But your call stack is just a data structure. So what you can do is you can just write a data visualizer, and this takes you about 15 lines of NetVis code, and then there's your call stack in the data watch window. So yeah, I think this is a really useful way to think about coroutines, and to like inspire a little bit what kind of things you can do here and what kind of power they give you. Like, your call stack is just a data structure. You can resume, if you want to resume a function like higher up the stack, do some like exception handling kind of control flow where you just jump up further up the call stack. Sure, you can do that. It's just a data structure. If you want to splice two previously unrelated call stacks together, sure, go wild. It's just a data structure. You want to expose a range interface so you can use range algorithms that iterate over stack frames? Yeah, you can do that. But it's still, in the end, just the structure is still that of a linear list of nested tasks. So let's maybe do one more thing. Now it's a tree. Now it's a directed graph. I want to thank Louis Baker and Mateusz Pusch for valuable feedback on this talk and discussions that really helped me a lot in understanding this better. If you want to understand a little bit better how this works, feel free to check out the Godbold example that I showed for the debug example in the end. It has like full working code here, and feel free to grab me in the hallway if you want to know more. And I'm happy to take questions also. Thank you. Thank you. Thanks.
Thank you very much. Please raise your hands if you want to ask a question. Okay, we have one here.
Hey, thanks for the talk. Could you maybe tell a little bit about the application of the model that this has been applied to? Because you said that the topic doesn't cover multi-threading, yeah? So if it's not used on multiple cores to handle the tasks, so is it just a type of multitasking on one CPU and used for that? Maybe that's the case on the in the automotive or stuff like that.
No. So the thing is, like, if you want to do asynchronous I/O, right? Most of the time, you're I/O bound, which means you're just waiting for results, right? So your CPU is not busy doing like number crunching or whatever. It's most of the time you're just waiting for like the other server just to send your result back, right? And in those scenarios, you can get very far with just one core, since you're just waiting, right? And as long as you can manage efficiently having like hundreds or thousands of tasks up in the air that you're waiting for, you're fine with one core, right? But of course, if your load gets high enough, eventually this alone is not enough anymore, and you want to use multiple cores as well. And then you can expand this mechanism to work multi-threaded in various ways, right? Like, sort of depends on your specific use case and how much you're willing to spend on like synchronizing between threads. So this is extensible to multi-threading, but it can be used, as I showed, also in a single-threaded way. So the decision is sort of up to you. And the only reason really why I didn't go into multi-threading is that it becomes much more complicated than it already is. So I wanted to leave that aside for another talk, maybe.
Yeah, sure, but your application was just like a one-threaded server that waited for the data or something?
Right, yeah, so like with this, you could have a server that just like accepts like hundreds of connections and then always waits for whatever result it needs from the other side, exactly. Yeah.
Thank you. Do we have another question maybe? Okay, if not, once again, thank you, Andreas, very much.
Thank you all. Thanks.
So see you in 12 minutes in another lecture. And right now you can grab a coffee or just go around. And remember about our conference app where you can give us feedback and rate our lectures. Okay, thank you very much. you can take your seats because our next French C++ expert is, our next speaker is a French C++ expert working on somewhat historical video games. He has a love-hate relationship with build systems, but lately mostly focuses on performance and multi-threading. He's a past speaker at CPPCon, Meeting C++, and ACU, or ACCU. Used to run the Paris C++ user group, and currently lives in Sweden. Fun fact about him is that he doesn't like AI, but has plenty opinions about wine. So, hips don't lie. Guidelines for memory allocation in C++. Matthew Roper, the stage is yours. Thank you very much. Big applause.
That's a big room. All right, I'll start with a joke. So how many of you are here to talk about memory allocation? Come on, raise your hand. Okay. How many of you came because it's a stupid Shakira joke? Oh, come on. Really? Oh, you're all nerds. Okay, it's fine. We'll talk about memory allocation then. So have my talk stopped because I have an interaction on Twitter, or sorry, formerly X, or the other way around. I never remember. And the last one was something along those lines. I saw a tweet, something like that. People got very strong opinions about using malloc or not using malloc. I don't know if you're familiar with people having those kind of hot takes. Just tell you if you want performance, just don't use malloc. A variant that I heard way earlier is something like this: don't use malloc while the plane is in the air. I still can't confirm that it's actually true, but I know there are guidelines for aviation industry software and things like that you're not supposed to do dynamic allocation on some part of the critical lifetime of your application. But that's, I wanted in this talk to explore a bit is there a myth around that? Where does that come from? And can we derive some interesting guidelines about this? Because performance is kind of the one thing I've been talking about a lot in the past, as it was mentioned before. I used to talk a lot about build systems, kind of pivoted a bit lately. I had to talk about profiling. I had to talk about multi-threading. This is the talk about allocation. This is kind of the four horsemen of performance, if you will. And I had to talk about caches and data locality, which I think I repeated last year here, actually. So if you were there, was anyone there already? Oh, I have some fans. Good. Let's see if I can keep that up for the future. Cool, so hello. I'm Mathieu. I work at Paradox Development Studios. I work on Hearts of Iron and other secret stuff that I cannot talk about. I have 4 different handles and none of them match. Feel free to hit me up on any of those if you have questions, thoughts, whatever. Hot takes about wine. I will probably disagree, but maybe we can get somewhere. Anyway, the goal of this talk is I will explain briefly. My goal is to be very beginner friendly. So I will explain a bit how does the heap actually work, in practice, almost like an exam, I don't know, final year operating system question. How does the heap actually work? What happens when you call malloc? Given that knowledge, I will try to derive 10 guidelines for handling memory allocation. And my goal again is that from beginner to expert, I hope that there's at least a couple guidelines that you will get out of this, that you will think oh, that's interesting, I never thought about that. I'll see if I do a poll or something at the end, and hopefully we can have a nice distribution around that. But the first question is what's in a malloc? Who here thinks they could re-implement malloc? That's not a lot of people. Who here thinks they could re-implement a good malloc? Okay, that's basically no one. Okay. So I'll try to maybe make it less scary, because I've heard people who think that they can do it easily. And to be fair, maybe the most easy way is doable, maybe not the most efficient way. For the rest of this talk, though, I'm talking about allocation, and it's a big topic. I want to focus really on the act of reserving memory, uninitialized bytes. So this is kind of I'm a C++ programmer, but this is 100% applicable in C and other languages that don't have constructors, because I'm not going to talking about constructing. I'm not even going to bother with zeroing. No, just get some bytes and do whatever you want. They're yours now. Likewise for the allocation, I'm not considering side effects of destructors or anything like that. It's just free. Give those bytes back so I can malloc them again, or relinquish them to the system so I can open another Chrome tab. Right, so if you're there in the previous talk, there was some introduction to the stack. If not, you will have a rough idea of what a stack is. So I hope you're all familiar with the base idea of a stack, right? This idea that we have a linear array or set of memory that we keep growing in one direction. Technically, it goes downwards, but you don't really have to consider that for the talk. And the idea is that this is where you add everything that is considered like a local variable. Every time you do like int x, for example, in a function, that goes on the stack. And you know, as we saw in the previous talk, if you were there, if not, you can see the nice illustration on the right. Every time you enter a new function by doing a call, the rest of the previous stack is still there. It's just further away from you. And then when you return, you purge what you've been using, etc., etc. So the advantage is allocating on the stack is probably the fastest and the cheapest thing you can do. Like if you ask your compiler, your CPU to allocate like the memory for an int on the stack, the only thing it has to do literally is increment the stack pointer by the size of an int. And that's it, you're done. This is all that needs to be done. It's one register add. For frame of reference, your computer can do basically about as much register add as its frequency. So like if you have 4 gigahertz, it can do 4 billion per second. It's not a problem. I would say it's free. At this point, you might as well consider it free. It's technically not free if you go to some very performance-intensive domain. But for the purpose of this talk, I think you can consider it free, especially compared to the other things we're going to talk about. And obviously, you don't need any library. You don't need any operating system call. It's on any CPU, you can implement that trivially. You don't even need an OS to be able to do stack allocation. It's really the simplest thing ever. It has some limitations. Obviously, that's this kind of thing we talk in schools, right? With some caveats, you cannot actually allocate the dynamic size. So like you can allocate an array of 10 elements, for example, but 10 has to be a compile time constant. You cannot allocate an array of n elements with n being a runtime value on the stack. Technically, there are ways, we'll talk about it later, but this is like, as far as the standard is concerned, you cannot do that. You have to know the size in advance. This is due to the way the assembly code is generated behind the scenes for you, which is basically adding a constant to the stack pointer. It's limited in space. Anyone who has ever run into a stack overflow, this is literally what happens, is you just increase the stack pointer one time too many and you run out of space. It's harder to do on modern platform, but it's not impossible. And finally, maybe the good part, mostly the good part, is it's automatically reclaimed at scope exit, right? So when you return from like a block or a function, then the memory you allocated on the stack at this point is lost, which is good on the side that you don't have to care about it and you can't forget to free it. It's bad if you wanted to save it for later, pass it to someone else, process it for longer. Obviously, that won't work. So first guideline, I guess maybe the most simple. Prefer stack allocation when possible. This is probably like the easiest guideline you will have in this whole talk. If you want to go fast, just allocate on the stack. This is the fastest way to allocate memory. But of course, sometimes you can't do that. Sometimes you have variable size. Sometimes you just need to persist the thing for longer. There are many reasons why you can't always use the stack. We have malloc for that. It comes from the C standard, and obviously in C++ you have new. And ideally, you should use neither of those. You should use something like make unique or vector, string. This is what they do behind the scenes. It's also called new and delete, but it's the same concept. So conceptually, the idea is you can allocate any arbitrary amount of memory. You just call the function with a size, and it says, OK, I will give you this amount of bytes. And it will live until you call a matching free. Again, I hope that this is nothing new for you. This is the most basic memory allocation things that exist. And luckily, again, as I mentioned, we can mimic lifetimes like the stack in C++ with stuff like unique pointer, vector, anything that relies on AII, anything that relies on constructor or destructor having like a matching side effect, do that for you. And I would encourage you to always do that because manually chasing stuff with free is something that should have died like 20 years ago. And hopefully it's kind of dead now, I hope. But how does that actually work? When you call malloc, what actually happens? So the first thing we'll do, usually in a good like malloc library, like the one you get on most operating system, we will try to find a free block of size n. What it will do, for performance reason, it will keep a bunch of heaps of different size of objects of a different size. So like for example, okay, this block is for every time you want to allocate 8 bytes. This time is for every time you want to allocate 16, 32. Powers of 2 are usually simple, so that's usually what we go for. But it depends on libraries from library. The base idea, this is really simple. Basically, you just do like a very basic bit shift mask to figure out what size or what bucket your allocation falls into. You go into that bucket, you say, give me the first item, and you return. I think a good programmer can implement that in a couple lines of code. It probably translates into maybe 10 instructions, maybe 20 instructions. It's very simple. It's really basic. It's really not that inefficient. Like, you're probably more likely to pay for like the fact that you have to dereference pointers more than you have to pay for the arithmetic and maybe one if branch. It's really not that expensive. The problem is, what if the block you find has no free entry? That happens at least the first time you start, and then that will happen as your memory grows more and more and you run out of space. But obviously you don't actually run out of space. Instead, what you will do is you will try to grab what we call a free page. Page are like memory blocks that can be the smallest units that can be managed by the operating system. It's like 4 or 8 kilobytes depending on your CPU and operating systems. It's something like that. And most memory manager will have a bunch of those free pages available at any point that they can reserve and recycle to allocate objects into it. So basically, okay, I have no more page of like block of 16 bytes, for example. I will just grab a free page, then I will initialize a bunch of data structures, and then I will return the first entry. It's still a bunch of work, but it's not the end of the world. Like, ideally grabbing a page, doing some like list management, maybe initialize a few structures. It's more expensive than the first one, very obviously, but it's not that horrible. It's usually not going to be the thing that stalls your application. Like, you will visibly see it stutter because you've done that, usually. But sometimes you're out of pages. So then your C library has to call the operating system and say, I need more pages now, because I'm running out. Now you start getting expensive because you have a system call, you have to switch to the operating system process. The operating system has to allocate new pages and has to physically tell the CPU that those bits of RAM are physically connected to your process, has to flush a bunch of data structure on the CPU. That comes with a cost, and then it has to return to you. And of course, every time you do a system call, your operating system might decide that, you know what, you've hit your time share, it's time to go to sleep now because Chrome has, I don't know, whatever Chrome does. It will happen, right? Every time you do a syscall, it's a chance for your system to be for your CPU, for your current process to be paused until somebody else is done with a timeshare and you get it back. You can tweak that with CPU priority, but it might happen. But even then, maybe that's not enough, because maybe your OS thinks like you're out of free pages, right? You're out of RAM. Literally, you're out of RAM. Most operating systems, I think, to this day, don't immediately crash your process when that happens. They do a funny thing that is called swapping, which is they find another process and look at some metrics that say, they haven't used those pages for a long time. Again, probably a Chrome tab. And then they will just page those bytes to disk. You just write out the content of the memory used by the process that is basically asleep for a while. Just write it to disk, and then later when that process resumes, we'll load them back to disk. It's been done for, I don't know, a good part of 30 or 40 years. That is how you basically can go over your RAM, physical RAM capacity. If you add all the processor usage in your Windows Explorer, you will see that it's way higher than your RAM, and you still continue going. That's how that works. The problem is, that is very expensive, because to actually do that and then return you some pages, you have to do disk I/O. So remember, we started by saying, hey, C library, I need like 8 bytes to allocate for an integer, and you end up like reading and writing on your disk, which hopefully is an SSD, but you don't know, maybe it's not. So to give you an order of magnitude, right? It's about 10 times more expensive, roughly speaking. Those are not real figures, but to give you an order of magnitude, it's an order of magnitude more expensive to have to grab a free page if you're out on your current buckets. It's another probably order of magnitude if you're out of buckets and you need to go to the OS and get more memory page for you. And if you have to go to disk, it's probably another order of magnitude again, because you have to do disk I/O, and that's really not cheap compared to how fast a CPU can go nowadays. And the funny part, or maybe the sad part, is you cannot predict which one you're going to hit. Anytime you call malloc, any of those can happen. Statistically speaking, you're more likely to hit the first one than the second one, with itself more likely than the third one, etc. But you can't predict when that will happen. And you can't say, well, this is really a critical time now. I cannot afford to have my operating system call just take 4 milliseconds. I need that RAM yesterday. And I think that goes back to why people say don't allocate while the plane is on the air, because at some point maybe you need to allocate something and you need immediately that memory, or like within the next CPU cycles, not within 10 milliseconds. And since it's unpredictable, you have to eat the cost. So I guess guideline number 2 is malloc is actually fast, except when it isn't. And sadly, you can't predict that, so you have to be aware of that fact. Because it's the kind of thing that is also hard to debug. Because it's a thing that spikes randomly at the moment where you actually get into like, well, I just passed the boundary and now I need to go fetch some memory from the OS. It's also hard to reproduce, obviously. The good thing and the bad thing. The good news is the first 2 parts, right? You know, like managing a bunch of free blocks and then managing a bunch of free pages. That is done by your C library implementation. So if you're unhappy with it, you can write your own. Or more likely, you can find someone who you think is smarter than the one who gives you your reference library and then use that in exchange. Or find something that's maybe more adapted to your use case, because, you know, malloc has to work for any type of process, any type of load case. It has to work for the case where you front load everything with like a loading screen and then you don't allocate anything. It has to work for something that keeps allocating and deallocating all the time. It has to work for any of those possibilities. So obviously, if you have a more specific case, you might be able to find something more dedicated. If you want to optimize how well like memory management is done by your OS, you're out of luck. There's no way to do that unless you make your own like memory driver, and I don't know about anybody who does that. So that part you're out of luck, sadly. So that's where we go. And that's the slide where I talk about Microsoft real quick. If you've ever experienced playing on Windows, the default allocator that comes with MSVC is not amazing. It has some problems. The biggest one that you may have heard is that on the debug build, if you call free, it will lock a mutex, even if you pass null. The standard says free null is a no-op. Microsoft says sure, but I'll lock a mutex still. Then it's a no-op. Don't worry about it. That's really bad when you do multi-threading. I've been bitten by it a couple of times. In general, like freeing and allocating in parallel with MSVC is not efficient because, again, there's a bunch of mutexes that are trying to make sure that 2 different threads do not actually end up banging the same memory area. The funny thing is, there are solutions for that. There are like drop-in replacement that you can use on Windows that come like almost pre-bundle and link to your program. There's this one called memalloc, for example, that I've used in our games that is pretty efficient. And if you look at the GitHub URL, you might notice something interesting about who made that library. And then you look at the paper, you're like, wait a minute, Microsoft Research, what the? Yeah, I think Microsoft knows that their default memory allocation is kind of bad, but for reasons that are not entirely clear to me, instead of just fixing it, they will quietly offer you like a research paper and some drop-in replacement that is way better. I don't know why it's not the default. I guess it's backward compatibility. I don't care about backward compatibility that much. I rebuild my game every time I have to ship it. So, you know, guideline number 3, if you can afford it, just prefer a third-party HIP implementation to the default one on Windows, because it is just way better. Cool. Now that we've got the basic stuff out of the way, we might look at some code and talk about like more like actual implementation best practices. It's more of a collection of things I've run into during my life as a programmer, like as a reviewer, as someone who has to look at performance and found something. There's a thing actually that comes back a lot. We have this test at my company. I'm giving you pointers if you want to apply one day. We'll ask you to write a pathfinder. And every time someone applies at the company, I have to, well, me and a bunch of other programmers have to review the Pathfinder. So I've seen a lot of Pathfinder, and it's really great to find slides to talk about because there is a bunch of things that you see coming back and over again in like either mistakes or ideas or patterns that may or may not be so efficient. So here's the idea, right? What we ask you to do is that you have like a grid of like 2D points and you're supposed to find the path from A to B and there's a bunch of obstacles. It's not rocket science. There are many algorithms out there. I'm not going to give you the whole solution, but roughly speaking, what you do is that for you start with a cell, any given cell, you check each neighbor, you filter out, you return the ones that are actually traversable, and then you recurse until you're done because you found the exit. That's one of the classic algorithms to get your way out of, literally find your way out of a maze. It's not really complicated, but this is actually interesting because let's look at how you would implement it maybe somewhat naively. right? Okay, so I want to find all the neighbors of a point. So I'm going to return a vector of points. So first I create a vector, then I check. Okay, is there something to my right, or am I out of bounds on the map? Because this is the problem number 2. Number 1 is you forgot to do that check on your Pathfinder, and you start checking outside of the boundaries of the map. But obviously, not every of your 4 neighbors are valid, right? So you check. Okay, out of my 4 neighbors, which one are valid and traversable? I simplified this for the thing, but assume that the check is like, is my neighbor valid and can I traverse it? So okay, can I go to the right? Okay, so add it. If can I go to the left, then add it. Can I go down, then add it. Can I go up, then add it. Right? And then we return. Seems simple enough? How many times does this allocate? Who says 1? 2? 3? 4? 5? 20 million? I see a bunch of hands still not raised. You're 0? Okay, I'll give you a hint. It allocates here. Because your vector is empty, you have to allocate the first time. The algorithm for vector is that you usually multiply the previous size by 1.5 unless the size is 0. In that case, you just set it to 1. So your first size is 0, you need to go to 1, so you allocate. Oh, well, you need to go to 2. Well, 2 is more than 1.5 times 1, so you allocate again. Then you have to go to 3. 3 is exactly the same, so usually you have to grow unless you have a right rounding, but half the time you don't. And then finally, you have about 5 elements then, so then you're good and you can return. So basically, you called malloc 3 times and free 2 times and bunch of mem copies to relocate your vector every time in the course of just doing this. And as we mentioned, any of those mallocs may have ended up swapping to disk. Most likely it hasn't because this is a test program, but any of those could. And again, even if it didn't, it's very wasteful. So obviously, how do we fix that? Maybe the most simple fix possible is just call reserve ahead of time. Right? We know the upper bound of this thing. That can be up to 4 element maximum. Just reserve for 4. At most, you will allocate once. Actually, you will allocate once. You could even try to optimize and only do it the first time you start adding something. It's 1 if for the price of 1 less allocation. You do the math and figure out if it's worth it or not. But roughly speaking, this solves the solution. So guideline number 4, reserve the final container size when you know, rather than rely on the geometry growth, because it will always be more efficient if you know the final size. Make sense? Cool, because now I have to warn you against the opposite problem. Because you can abuse reserve, and I've seen that, and this is maybe the first more advanced suggestion I will have, because this is something I caught like more experienced programmers do in the past, including myself maybe once or twice. So let's say later we want to take the results of all those neighbors we found and we want to add them to another collection, because remember, we're trying to build a collection of all the points we can reach. So you're like, oh, okay, here is the idea, right? I know how many neighbors I want to add to my existing collection, so I'll just reserve the size of the amounts I'm supposed to add, and then I'll just copy them into my collection. Right, so the idea is like, okay, I'm gonna add 2 vectors together. Basically, I'm gonna append vector number 2 to vector number 1, and I remember Matthew in his previous guideline who said, if I know the final size, please do a reserve. And the final size is the size of my current vector plus the size of the vector I'm trying to add to it, right? The problem is you're breaking the entire geometric growth factor, and now it's not worth it anymore. Because the blue line is how many allocation would have happened over time if you had not done a reserve. The red line is what happened if you do. And the reason for that is that each time you're reallocating your vector plus 4 maximum. If you're lucky. If you're unlucky, vector plus 1, vector plus 2. The other one will only reallocate every time the size needs to double or become at least 50% bigger. So you will save an allocation. Basically, one of them is logarithmic. The other one is linear. And as we know from math, log is better than linear when we're trying to be small. I'm very good at math, as you can notice. So guideline number 5. Do not use reserve with constant delta in a loop. And by constant, I mean constant-ish, right? Technically, this was not a constant. This depended on another size, but this was another size with an upper bound that we could very clearly know to be like, I don't know, in the 10s, tops. Cool. Let's continue with our Pathfinder, but now let's zoom out a bit. Because what is your Pathfinder doing, right? It's like, okay, while my search queue is empty, get the top of my search queue, like the first point I should explore next, pop it out. For some reason, there is no API in the standard that allows you to do those both instructions in one. I don't know why, don't ask me. And then what you do is you say, okay, for every point in the neighbors, do something. Probably like add them to the search queue or something like that, unless I've seen them already. Make sense? Who thinks this is good? Correct? Somewhat acceptable? Who thinks this is bad? People, do you have to commit to something? Give me something. Like I have to work with it. Yes, this is actually bad. Here's why it's bad. Because every time I run into one node in my grid and I have to explore its neighbors, I will allocate, assuming I use the optimized version of find neighbors, I will allocate once. So if I don't know, if I have like 1,000 by 1,000 points on my grid, I will allocate 1,000,000 times, assuming it's empty and I have to go through all the points. Do I need to allocate 1,000,000 times? No. No, I see some people. No. No, I don't. I don't, because at most I will just fill that vector with up to 4 elements each time, and then I will just go home. So how do we solve this? How do I make the buffer reusable? And that's where I start going. Maybe the most controversial suggestion I have out of this, out of those 10 points. You know what? Maybe I should not use return values. Maybe I should use output parameters. I know, I understand a lot of coding rules, a lot of books, a lot of everything say, no. It's based on math. A function takes an input and returns an output. A function does not take an input-output value, write to the output value, and then return nothing, because that makes no sense fundamentally, and I agree with that. But sadly, my compiler cannot optimize this the way I want, but it can optimize that. Why? Because if I pass the neighbors by reference, then this is my function, and it will probably allocate the first time, because it will grow the vector. And as soon as it reaches 4 size, which is the maximum it will ever reach, I can prove that because this is how much I use it, I will be done. It will never grow bigger than this. Which goes against a lot of things that I have been teaching people and I have been taught myself, which is no, don't use output arguments. The problem is there is no way to reuse arguments if I do returns. I haven't found any. At best, you could pass in by error value and then return a moved version if you want to preserve the semantics of like functional programming. At this point, I would say just use an output parameter and be done with it, right? So our loop will start looking like something like that. You will basically every time you run to the loop, the important part is you put the neighbors out of the main loop, right? So that way the buffer is reused every time you go through, and at most you will allocate the first 4 times, and then you're done. This is amortized around 1,000,000 points. That's basically 0. See, allocates once, roughly. Cool, so guideline number 6. Prefer output parameters when returning containers. Why? Because guideline number 7, reuse previous allocations when possible. At the end of the day, we're trying to have performant malloc and free. The best way to be performant is to never call malloc and free, or minimize the amount of time you have to call malloc and free. Which leads us to clearing things. So I make video games, as you may know, and we have this concept of a frame where you have to set up like a bunch of things that you want to render for a given frame. Then you draw, and then you do again. That's basically the main thing that most video games do, at least on one of their many threads. One of them, the only thing it does is that 60 times per second, hopefully, or more, depending, you basically set up a bunch of things, you throw them at the GPU, you display the result, and then you go over again. Right, so let's say, for example, every frame, I'm going to build a vector of what is actually visible on the screen, like visible entities. It could be like, I don't know, like enemies, weapons, power-ups, whatever is visible on my screen at the moment. I will try to build a list of visible entities, because at some point I will have to tell the graphics card, hey, draw those bad boys, because they're actually visible to you right now. There's probably a sound driver somewhere, and I also want everything that is supposed to be audible to be able to emit sound to the sound driver. So I will also build a list of what is close enough to the camera or the player to be able to get that. And then I don't know, maybe I'll have a debug message I want to show because it's the debug build or whatever. This is slideware, right? Do not start writing a game like this. Or maybe do if it's your first game. I don't mind. And so, okay, I want a clear function, right? And is this pattern a thing you've seen before? The idea of like, oh, I want to reset an object. Why don't you just assign it to a default constructed version of it? And maybe this is just a small pet peeve and I can skip like 10 slides, but it's a thing I've seen a lot. Because it is convenient to implement clear that way, right? The main argument I would hear for it is that I cannot miss a member by writing this, you know? If someone comes and adds a new member and forgets to add something to the clear function, then I'm starting to have some interesting bugs when things you could hear previous frames starts continue, like you get ghosts basically. Things that are not supposed to be visible or audible will start popping up because I forgot to clear on the visible ones. So obviously this is good for that, and this is why usually I've seen that recommended. Because if you do this, you cannot forget to clear a new member that someone added by accident or otherwise. It's total, it's guaranteed by the compiler. But of course, if I'm telling you this, you know that there is a problem there, right? This frees everything, right? Because this is what containers do, and that this is the moment for me to. If anyone is on the standard committee and can explain me why vector is always implemented like this, I'm very curious. Because this is how you implement move assign on a vector, right? If I have a vector, like assume this is my vector of audible or visible entities, right? So the one on the left is the one this is the one I've been reusing over time. So obviously it already has a buffer, probably because I collected some stuff over time. The one on the right is the default constructed one that I just made. It's empty, it doesn't have any buffer. What does it do? It clears my current buffer, fine, you know, remove all the entities from it, that's okay. Shrink to fit, freeze all the memory my vector has, and then just swap to reassign them, and then return. You see the problem, right? Let's see I had like 10,000 visible entities the last time, because I have a very, like a bullet hell game or something. I had 10,000 entities I collected the last frame, so I grew my vector up to 10,000 elements, and then every frame I throw that away, and then I start locating a new vector, which basically gonna also collect about up to 10,000 entities. Why? Because vector does not preserve buffer when you reassign it to another one. And you could say maybe there are cases when that's worth it. I would argue that if the other one is empty, there's just no good reason. Like, I don't think this should be an explicit clear. I think this should be an explicit clear. If I call the explicit function shrink to fit that I've never seen anybody ever call, there are all places where you want to do it. I think this should be explicit and not implicit like it is here. It is. You can even try to be mega smart and be like, oh, is the other empty, but also they have a bigger capacity, I'm going to preserve the bigger stuff too. There are many ways to do this. The point is, none of them do this. I have looked at a bunch. Even EASTL, the EA implementation, the Electronic Arts Gaming Industry TM version of the STL, which is way better, arguably, doesn't do this either. It still loses all memory when you assign it to another vector, even if the other one is empty. Just throw that memory away, it's fine. But obviously, I don't like the one on the right. It's more efficient, but it's more work, and we're all lazy. Are you lazy? Yes, good. That's a very good quality for a programmer. You should be trying to do less work when possible. It's actually also good for your CPU because less work means less cycles. But yeah, the one on the left is good because it's correct all the time and it's less line to types and it's less line to review. But it's also losing me, I don't know how many amounts of bytes every frame that I have to reallocate. Possibly several times because you have a growth factor and everything, blah, blah, blah. And that doesn't stop here, it's viral. Because what if my frame data has a clear function, but again, the guy storing my frame data doesn't call the clear function because he also knows that the easiest way is to call equals frame because I don't want to bother to explicitly clear members, right? If you have members within members within members, they all have to cascade. Excuse me, I think my phone is attacking me. 1 second. There we go. It will cascade down, right? And if at any point someone decides to say, you know what, I'm going to take the assigned to default constructed value instead, then you're going to have the problem again. I don't have a magic solution to this. I would argue that maybe we should change the way vector and other containers are written in terms of reusing memory allocation. if someone is on the committee and have opinion about this, there was probably a discussion somewhere in '97 when this was settled, and I'm not aware of it. But I don't know. Right now, I think it's just a pain for me, and I would rather say prefer member-wise clear over assignment to empty struct if you're reusing things, because you will save memory. This goes for vectors of vectors the same way, by the way. If you have vectors of vectors, well, if you can replace them with like a vector with like a 2D array inside, because you will save on memory. But if you have vectors of vectors and if you clear the whole thing, you will clear the independent vectors within it. So you will also throw all that memory away, and then if you rebuild a second time, then you will restart allocating again. That's a loss of wasted memory. And again, wasting memory is not the problem per se, because your allocators are usually pretty good at not making that a hassle on the memory usage. It's the cost of you have to pay for malloc and free every time. Now that I have just a bit more time, I will go into more advanced solutions. Or maybe the one that I've heard discussed, actually in the past couple of weeks, some people have been putting that up, but I'll just give you a primer for now, and I will probably make an addendum or a longer version of that talk in the future that goes into more detail. We're like, but what if I just had an alternative to malloc or free? Because again, as we discussed, this is a general purpose allocator, and the rule number 1 or maybe number 2 of computer science is that if something is general purpose, it's probably going to be less efficient than something that is fit to purpose, right? This is the best, the better idea. The more constraints you can put on something, the more efficient you can make it, because you don't have to consider yourself with A, B, or C. So again, you can't make assumptions on usage pattern. It has to be good enough for everybody. You have to make compromises, and usually those compromises are made for usability versus performance. But what else can we do? Has anyone here has heard about Alloca? That's more than Shakira. That's a problem. I think more of you should know about Shakira than Alloca. I guess this is my quote for this talk. I'll tweet this afterwards. It's not standard. First of all, it's not standard. 2, it's C, so it's kind of bad. The good thing it does is that it's dynamic stack allocation. Basically what it does is that it emits a bunch of instructions for you that just increment the stack pointer by dynamic amounts, and then it returns to you like where that allocation starts. It's convenient until it isn't. First of all, it's a C API. So if you want to use it in a proper manner and make sure that, for example, if you have a constructor or destructor for this object, it's actually called, you have to do some wrapping. Since it's C, you probably have to use a macro. I've done it. I'm trying to murder them out of my code base because I think this is a very 90s or 2000 things to do. It is fast once you translate that into like actual machine code, because again, it's register add, very cheap. But it has problems. Again, you're bound by stack size, and your stack size is again pretty good. Like I think, okay, actually, I'm gonna ask you if you know. Do you know how big your stack size is? Like, if you're reviewing some code and it does alloca, how can you tell that this is gonna be fine? I think one person says, oh yeah, I think I know what my stack size is. That's less than Shakira and less than alloca. We're not on a good track, right? Because, I don't know. Okay, let's try this. Do you think it's like a meg? Maybe like 10 megs? 100 megs? 1 gigabyte? No, it's a couple megabytes at best. You can tweak it on most OSs, but the default is going to give you a couple megs. So that might be fine for some things, but if you start doing what I've seen people do, which is like, oh, I'm going to allocate like a texture or like an uncompressed music track because I don't want to allocate because I've been told that malloc is slow. I'll just like try to uncompress some textual data on the stack. It might work until your artists start becoming like, hey, I like 4K textures, and then you get in trouble. Again, limited space, especially on threads, especially on Mac. I ship a game on Mac, as you may know, or have realized by now. It's not fun, because the stack size on Mac is hundreds of kilobytes. It's not outside of the main thread. You can't change it. Oh, and since we're talking about C++ standard, the standard does not allow you to change the stack size of a thread. I think the argument is something like, oh, but we write the C++ standard for CPUs that don't even have like stacks. Okay, cool. Yes, so my guideline number 9 is avoid using alloca because you're likely to overflow the stack, especially on Mac, especially on threads. But in general, like, you might be able to get away with it for like avoiding a call to malloc for like 10 kilobytes. Are you gonna really win compared to how long it would have taken malloc to give you 10 kilobytes? I'm not sure it's worth the risk. Very quickly, because we're running short on time, you have a thing called custom allocators, especially since C++ 17. You can write your own allocator. You can say, you know what, I don't like the way malloc does things. I can do something better. And it is absolutely possible to beat malloc on a very specific case, right? If you want to make a better generic purpose allocator, I think as we've seen with the people raising their hands earlier, not a trivial task. Beating malloc on a very specific case, probably doable. There's a guy in this room who's made a talk about allocators. I recommend you go and watch it. You have an hour and 25 minutes of content, and it will probably tell you everything and more. I will try to go to the very quick bits that I think are valuable for this, and then you can go and watch the rest on the internet. Monotonic allocators is the most simple thing you can do ever. It's basically you make your own stack to put mildly. You create an array somewhere, and you remember where it starts and where you are currently, and you push, and then when you're done, you just reset to 0, and then you come again. The drawback is, like the stack, you can't deallocate a specific object. It's all or nothing. It's you revert to a past known point or the start. That's the only thing you can do. So it's limited, but it doesn't. It will not blow in your face because you're a thread on Mac, for example, and it will support dynamic sizes. You can just allocate yourself, like you can just do like malloc me like 1 megabyte or 10 megabyte or 100 megabyte, and then I'll just do a bunch of push and then reset it at the right time. And yeah, free is usually all or nothing. What I mean by that is actually return to a previous point, like the stack does. Return to a previous known moment. I have an implementation here. It's slideware, but honestly, a real implementation is not much more complicated than that. Given the time, I will just go through it. Look at this; it's amazing. Yeah, and that's it. That's your code, right? It's literally 3 slides. It's really dumb. It's really dumb, and it does the trick. You have to be able to scope the thing, right? Because as the stack, it will grow until you run out of memory or you reset it. So you have to figure out a way where you know, okay, at this point I can reset it, and anything it allocated is dead, and I don't have to care about it anymore. I don't have to figure out where it leads, and I have a way to guarantee that, or I hope I have a way to guarantee that nobody has a pointer to it anymore. People in the game industry like this because, for example, if you have something like a level, you say, okay, I have a dedicated allocator for this level. Anything that this level uses, like a texture, a model, a map asset, whatever, goes into this, and then when you exit the level, just throw everything out, reset the pointer to 0, and then try again. Some people optimize this to the next point. They don't even run destructors. They just go, done. You can do it if you guarantee that you have no side effect in your destructors. State machine, any kind of state machine, when you move from state A to state B, as soon as you transition state, you reset and you continue. Every time you build like a request processor, a web server is a classic. Okay, you have to serve a request. Okay, while I'm serving this request, just throw everything at this allocator, and once I start returning my data, and when I'm done serving the request, just kill it and do it again. Anything like that. Frames, obviously. Allocate everything you know to render this frame on this thing, present it on the screen, reset it and try again. You pay for the allocation once when you start the application, you bound it by a size, and then you're done. So guideline number 10, because we're running out of time, consider monotonic allocators when resource can be scoped and budgeted. There are solutions to make them unbounded and be able to grow forever until you run out of RAM, but I'm trying to keep it as simple as possible for the purpose of this talk. Right, so in conclusion, dynamic allocation comes at an unpredictable runtime cost. Most of the time it's fine, and then one time it will bite you. Size up allocation once and reuse containers in memory as much as possible because of the previous statement. And 3, consider monotonic allocators and their friends. I think some are called arenas, but there are other names around there that have been thrown. If you can fit them in your current program model, they're actually really efficient. Oh, and furthermore, I still think your Bing should be destroyed. Thank you.
Thank you, Matthew, very much. If you have any questions to our speaker, please raise your hand.
Oh, can I ask a question before that? How many of you found at least one guideline that was useful? Okay. 5 guidelines? 10 guidelines? Okay, not bad. Thank you. That's how you do statistics, by the way. Questions?
Yeah, hi. So in the case where you have like 4 elements, why not just use something like std array? For assuming you have like small objects, of course.
Because I need to know how many have actually met in the thing. So actually my solution to get hired by Paradox was a very complicated thing where I actually had to return my own custom structure with an array of 4 and then a counter. And then somebody was like, "You're dumb, just use a vector." And, you can, but you have to remember how much you put, because there is no standard container that is upper bound but also has a dynamic size. I think there might be proposals around there. I'm being told in C++ 26 you will have a solution. In the meantime... yeah, Boost has something too, I think.
Any more questions?
Hi, thanks for a nice talk. Actually, I have a question about embedded systems. Maybe you have some experience with it. What about allocator performance on such systems? Because you don't have swap, so actually it should be quite fast, I guess.
I'm no expert on embedded system. I'm assuming that since you can't dynamically malloc, they probably use arenas everywhere, or the equivalent of monotonic allocators or something like that. Like they pre-reserve some size somewhere on some hardware. But I'm not an expert, so you probably would be better asking someone else.
Yeah, I guess so, but I just wanted to ask.
I can try to guess, but...
We have time for a last questions. For one last question. There's one.
Ask
okay.
me about my favorite Shakira song.
So, have you investigated or considered problems to do with the fact that heap structures have to be synchronized between threads, and how to optimize away
yes.
these things?
This is why one of the reasons memalloc can actually beat the default implementation is that it keeps a per thread collection, and then it will only merge them or recycle them between threads at some given point. So one of the solutions is you keep per thread pools, and then when those run out, you have to synchronize with other threads. You have obviously more overhead, because that means that each thread can potentially use like 50% of each block, but there are somewhat smart way to avoid that, the worst of the issue. But that's one of the solutions. If you're using monotonic allocator, the solution is replace your pointer by an atomic, and you're done.
Okay. So, Matthew, thank you very much once again for your lecture. Big applause. Okay, so one thing I would like to remind you about our app where you can give us some feedback, so please do it because feedback is important. And see you in half an hour on our almost last lecture. And you can grab some coffee, something to eat, and see you later in 30 minutes. Thank you very much. Right now? Okay, perfect, thank you. Hello again after our short break in the room number 9. Our next speaker, Damian Gwiszcz, will be talking about optimizing C++ compilation. But before, let me introduce him a little. So, this is what Damian wants to tell us about himself. Technical leader at Nokia, and a research and teaching assistant at AGH University of Science and Technology in Krakow. In my daily work at Nokia, I develop a real-time test framework written in C++ that validates 5G L2 applications. At the university, I teach programming classes. Over the years, I have taught programming in 5 different languages. Fun fact about Damian is that he has some free time, and in his free time, he's working on PhD in geophysics. He uses MPI and CUDA to parallelize seismic simulations in complex geological models. Damian, the stage is yours. Thank you very much.
Okay, now? Oh, yeah. Okay, so sorry for so many difficult shortcuts, acronyms in the intro. So what I am going to talk about today is the C++ build time optimization. So there is one very familiar meme that comes to my mind when I think about the build time in C++. Yeah. So basically, this is like our only legitimate reason for slacking off at work. I guess you can, for example, get up in the morning to work, pull up the changes, and start the compilation, and then you have to wait for like 30 minutes to that finish. So today I think I will make you a bit sad. Maybe you will dislike me a bit after this talk, because I will show you how you can reduce that build time even by 2 orders of magnitude. Yeah? You can use some existing techniques for that, but you can also use one that I am going to show you. It is not that difficult. Most important will be the approach used behind it, but you will see shortly. So someone might say that there is one reason why there is a problem with the build time in C++, and people might call that skill issues, but I think that the header issues are the biggest problem. Björn said this morning that he really dislikes the preprocessor, and you will see shortly why. So this will be the first point. Then we are going to switch into talking about Unity builds, and you will see that there are massive gains from enabling them, but they are not like a silver bullet to solve all the issues. Then I will show you a part of the pointer to implementation, the pimple idiom, that can be used also to improve the build time, sometimes even without additional costs. Then some nice tricks related to the forward declaration, and finally I will show you this new thing, this low-cost data access that we have used internally at Nokia in one of the projects, and the results were like quite promising. Yeah, so to start, I have prepared this short example. It is not really important what it does, but important is that I am using, for example, a reference wrapper, which is forcing me to pull the functional include into the code. Then I am defining a vector of references, so another include. Then we are printing this to the standard output. So this simple piece of code already forced us to do 3 includes in the code. Yeah? And you might think, so what? We have the includes, those are the standard ones, so there should be no issue with them. And we can see what is the issue in the Godbolt. There is a very nice option where you can print the output from the preprocessor. And this example you can see in here. that we have almost 40,000 lines of code just from those 3 includes. Yeah, very standard ones. And I have on purpose fixed the C++ standard to 11 and chosen the GCC, so we can do a quick experiment in here. So what I am going to do is that I am going to, keeping the same compiler, the same source code, I am going to switch to newer versions of the C++ standard. Yeah, I am going to do the same for the CLang and GCC. And then the question is, what will the plot look like? So on the x-axis, I will put the compiler versions, and then on the vertical will be the number of preprocessed lines of code. So do you think it will be like flat? It will stay that way? Is there anyone? Yeah, so do you think it will grow? Yeah, so will the growth be linear or faster? So linear, very few people. Quadratic? Yeah, so quite a lot of you got this right, because this is how the plot looks like. So basically, it doesn't matter whether you use CLang or GCC, we can see the same trend. And I have also tried to do a bit of extrapolation from that data. So you could see that for the C++26, this can get even worse. It will most likely do, but we are not sure yet how much. Yeah, and I'm still talking here about the headers. There is modules are not used here. Yeah, so you can go with modules and try to optimize also that way, but this will be not the main topic of this presentation. Okay, so now another experiment. We have seen that the number of preprocessed lines of code has grown over the C++ standard. So now I will use the build bench, another online tool, and we will see that there is a similar kind of growth in here. So we have this setup, the same code as previously. Again, doesn't matter what it does, only the fact that we have those 3 includes. I have set up all the combinations from the previous slide, and here we have the results, but maybe there are not so much readable in here, so let me show them like this. So this is the memory usage of the compilers. The same compiler, the same code, only difference is the C++ standard. This is the memory usage, and this is the build time. Yeah, so initially you might have thought that the lines of the preprocessed code have grown, so what, yeah? But this has real consequences. And I think that there is a like causal chain in here, because when you have more preprocessed lines of code, this like impacts how the compiler works internally. It uses a lot much memory, and this will then impact the compilation time at the very end. And of course, that is not like the full story, because I am talking only about how much text the preprocessor gets as input. But of course, you will get a different source inside. So you can, for example, from some headers, get some heavy template instantiations into your code. Yeah. So this can be also the factor in here. But yeah, maybe to get a better look in here, some guy who is working on the compilation will have to help me a bit, yeah? So this is the idea that we have, and we have also observed this in the data. So we have internally, for example, plotted the memory usage against the preprocessed lines of code, and there is like this nice linear correlation between them, okay? So in C++, basically, with the use of those types, like for example, I used reference wrapper, but I had to include the whole functional header to get it. And yeah, and this is really wrong, because we are using just one type, but we have to pull like whole the tree from this picture. Yeah. So definitely there is no parity for this rule that we only pay what we use. This is maybe true at the runtime in C++, but at compilation time is definitely not. Okay. Okay, and then yet another online tool that you can use to do some experiments. I have used, again, Godbolt, but this time I have switched to Clang with the time trace flag. And what is really nice is that you can use this online tool to produce very nice charts that show you exactly what happens during the compilation. And maybe this is very detailed, but what is important in here is that this code that I have been working on, with Clang, it compiles almost 1.5 seconds. Yeah, and then we can do some modification. We can include just one header. So we can see half a second for the functional. Then we have vector, another one. We see also the time impact from this header. And finally, the IO stream, which is the heaviest one. And what is important here is that those three numbers, they do not add up. Okay, so if you compile them separately, you will get bigger time than when you compile all of them together. Yeah, and this is the main idea that is applied for the Unity builds, because you can benefit from this overlap in the headers, not only in the header files, but also in the source files, in the CPPs. Okay. Yeah, and this allows us to switch to the first topic that I wanted to cover, how you can optimize your build time, and this is the CMake Unity build. So enabling it is very simple. Basically, in the CMake, you have to specify those two options, and then the tool will do all the magic for you. But this, to demonstrate how this works, I have to get some code that is, this is also some example how the Unity build will look like internally. Yeah, so basically some sources generated which will include all other sources. Yeah, so I had to create some code that is heavy to compile, and you will see some strange things being done in there. But be sure that this is not some imaginary example. I have adapted something that we have actually had in our code base. Yeah, so keep that in mind in here. So the first thing, maybe do you know this library, Boost Preprocessor? Yeah, a few people. So you will now get another tool in your belt, but please use this carefully. So basically, what I have done is that I have created this magical generate macro that will expand at compile time. Sorry, not at compile time, but during the preprocessor. It will expand to the fields and to the methods in this class. Yeah, so I can then very easily generate a lot of code. And this example here is taken from the telecom domain. You see the configuration, the cell groups, the user equipment, UEs. So those are the mobile phones that you use in our domain. Yeah, so those ones. And then the G-Node-B, this is the main hardware that is used for the tests. And then the last one is 50 more of those. So it will expand just to those tuples of those types, name, and then the default at the end. Yeah. So next, maybe this one we can skip. Yeah. So in this generate macro, we use the tools from the Boost preprocessor, and the most important is this one, which basically allows us to iterate over the parameters that we'll put into that macro previously and generate some output for each of them. Yeah, so basically we are iterating in here, and then at the very end, we call this macro, which puts a private field into the type and the accessors. And here I am using the notation in which the field will have the underscore on the end, and the accessors will be exactly the name that you have provided in that macro. Yeah, and this is how this can be used later. So, for example, the field called I7 was generated. I can get the value from that field, and I can print that. Yeah. So this is the first stage of creating very heavy compilation code. Here you can see some proof that this compiles and runs. So you can play later with that Godbold link on the top. Then second thing, because this was still not enough for me, because I wanted to have something very heavy to compile, but this surprisingly was not. Yeah, so I have to try harder. so the next thing that I did, I have used the functional header. Yeah. How many of you think that this header will be heavy for compilation? Yeah, maybe few of you have burned your hands on that header because it is quite heavy. It was this one from which the reference wrapper was coming. And here the most interesting part is that what is actually heavy is the instantiation of this std function. Yeah? And what I did is that I have, apart from those fields which I have generated earlier, and for those accessors, I am now also adding some metadata. So I can then at runtime, for example, get the name of the field. Yeah. So this will be the getter and setter and the name. And again, some very magical macros, boost preprocessor, and in the final step, you are generating something like this. So basically the meta structure which will keep inside the name and the accessors, like wrapped in the lambda. Okay? And then finally, after we do that, we can access the meta. You can see, the pointer is not very visible, but you can see in the second line that we are getting the metadata from the field using the name. And then we can, for example, set the value or get it. Okay, so this was the second part, but this still managed somehow to compile on Godbolt. Yeah, even though I tried very hard. So I have to try harder to make this fail finally. So I have decided to use the tuple. And what I did is that I have put all those metadata that were generated for the separate fields into one structure. So we can then, for example, iterate over them to print all the fields in the structure. Yeah. And this is how the metadata is generated. So basically you can see in here the tuple. And this was the final nail in the coffin, because after doing that, I have expected that this print will work. Yeah, you can see in here that we are just going over all the metadata and then trying to print them using some clever lambda. Yeah, but the result was that this finally has failed on the Godbolt. Yeah, so we ran out of the resources that are allocated in there, and we got a compilation error. So I finally had code that was heavy enough to make some good examples how the Unity builds impact the build time. Yeah. Okay, so basically, it's a really happy guide after that. So we are, yeah. So this one you can see later. Yeah. So the structure that I have created that will be used in the next examples, this is again something that resembles the configuration in those tests that I am working on at work. So we have like tests for some telecom functionality, and in those tests you usually configure some cells. So this will be the area which is covered by the BTS. You configure the UIs and so on. And each of those types, remember that this is not like a contrived example. This was really used in the code. Each of those contains such macros. Those macros expanded to the use of functional, and then finally the functionals and everything of that was wrapped into the tuple. Yeah. So you see that this is very like heavy kind of data. Yeah. So this is the structure. And then what I did is that I have decided to generate 600 source files. And those source files are very simple because basically each of them includes one of those types in here. Yeah, so for example, the configuration, the cell, and so on. And this will look something like this. Yeah. It's not sure if this is visible, but we have in the middle the configuration. And those red balls that point to it, those are the CPPs, which are, in our example, the heaviest one to compile because they like include whole the configuration tree. Yeah. The other ones, for example, the UI or the bearer and so on, those will have less dependencies than the first one. Okay, and then to maybe better visualize for you how the includes are spread out over the 600 files, I have put this into this kind of array diagram, where on the horizontal line you have like a column, the row, and then you have a formula on the top, which you can compute the number of the files. So for example, in here, you will have the file with the number 300, in here, file 500. So basically, this means that at first we have 100 files that are next to each other, and they have all the same include. Yeah. Then the next one, the next one. So basically, this looks like this. And I have tried compiling this now with the different sizes of the Unity builds, and here is the result. So basically, from like 2 minutes to build on this on 8 cores, we went down to some like in the range of 10 seconds. And this was all from just enabling the Unity builds. Yeah, but this case that I have used in here, this was really the perfect case for using Unity builds. So you have very well placed includes like header next to each others. Yeah, so if you like basically take 2 source files, including them in one CPP, then you will have like basically 100% of the overlap. Yeah, so this is why we see like with the increase to Unity build size 2, you can see the 2 times reduction in the build time. Okay, then another example, I have decided to maybe do this more like real life example. So instead of having all the files next to each other, I have mangled a bit the order, and now we have like this sequence. We have the 6 different headers included in 6 different files, and then this repeats and repeats and repeats. And of course, if we add to this plot that was created previously, you see again the quite well optimization, but the downward trend is not so fast at the very beginning, because this time it happens so that the headers they were not so well collocated to the next to each other. For example, you see in here that the last one, which is called bearer, should be next to the UI, so it can be reused, but it was like divided by the cell type, and this is the reason why the first data was better than the second one. Then another example, random permutation of all the data. And in this case, what do you think will happen? Where will the data be? Will it be worse than the first one? Yeah, where? Under the blue line or above the green or in the middle? What do you think? So who is for the under the blue line? Yeah, in the middle. Yeah, quite a lot. And above? Yeah, so quite a lot of hands for the option 2 and 3. So actually this is in the middle. Yeah, because in here it happens so that the distribution was quite unfavorable for Unity builds, because the files were not really that similar, and they were placed in the files next to each other. But in this case, when the files are randomly permutated, it happens that they quite often have the same include next to each other. Yeah. So this is why we see better results in here. Then the next example, and this is where the things start to be interesting. I have added basically empty CPP files between those which have the heavy includes. Yeah. And the result of that is that basically so this is taken, this is as the baseline, so this like greenish line, and then we are adding empty files, and you can see that this greenish line like moves to this side, yeah. So next example, this may be not so well to read, but you have like 2 empty files, between each file that has some include. And now again, we are moving to the right. Yeah, now another additional one. Yeah, and we see the trend. So you increase the number of source files that do not have the related header, and then the gain from the Unity builds start to diminish. Yeah, so the main takeaway from this is that you will gain a lot of benefits from using Unity builds, but you have to have two conditions fulfilled. You have to have like very densely included headers in the CPPs, so there is actually the overlap. Yeah, and you have to have actually something that is heavy to compile, as I have showed you previously, because yeah, in this example, you've seen that I have added empty files between those, which are heavy. But if these source files there were also heavy, then you will get some drawbacks, because you will now compile a lot more in one CPP, and this might actually not scale. Yeah. So if you have like one CPP with 10 different types which are heavy compiled, then this will at least add up. And maybe it will also grow like more fast than just the linear trend. Yeah. So this was the one approach in which we have the Unity builds enabled with different combinations. But of course, you can also try doing some brute force on this stuff. So you can try to increase the number of cores. So I have actually measured all those combinations. So there was like a very nice script that I have started on Friday when leaving the work, and it has finished on Monday. And it has built through all the different combinations. So you see that increasing the number of cores basically almost drops in half, but the shape of this data still remains similar to what was at the beginning. And again, I still have some spare cores on that machine, so another increase to 24 cores and then to 32. So we are at the level of 30% of the original time. Yeah. In the perfect case, we will go down to the 25%. So we are very close. And finally, I have used all the cores on the machine, and we are around what we expect from this, like multiplying the number of cores by 4. Yeah. So this is at what stage I have ended up after just using the Unity builds and putting more cores to the build. So at the level of 55 seconds at the top from the original one for over 120. And then I have started doing some other tweaks into the code. So first one that is actually quite simple to use is to try hiding some of the implementation details in the types that you have. So for example, in here, you can see that we have the Keynote field in the configuration, and it is initialized directly in here. So this forces us to include the full type definition, so we can initialize that field. And what we can do is that we can wrap that field into a unique pointer. And if we do that, you will see that the details of those Keynote types, they can be hidden in a CPP file. Yeah. The only condition when you can do that is that you have to provide some constructors and destructors in the type itself, because if the constructor is still in the header, then it will force you to do the full inclusion. Yeah. So you can hide it in this example, and then of course include the full type definition in the CPP. Okay. Another example, maybe not so obvious as the previous one, is that you can actually, with some types, you can use the forward declaration, and you do not have to include the full type definition. So in here you can see that we have a vector. Yeah, and this vector actually, until you use the members like the size or access the elements, you do not have to include the full type. Yeah. So this is like very nice trick that you can do in your code to also hide the dependencies. So this is basically for free if you have vectors in your configuration tree, for example, like in my case. Yeah. Okay, and then similarly as for the unique pointer, if you do that, you have to hide the initialization into the CPP file, so that constructor and destructor does not force you to do the inclusion of the full type. Yeah, and then the rest of the code. So I have done the modification with the pimple idiom. So this was how the code looked like initially with the direct access to the member, then to the field, some assignment, and we had only one inclusion in here. But after doing those modifications, you can see that the number of includes has grown. And you might have thought that maybe this is worse, but it's actually better because we now have more control over what we actually include in the code. And if you, for example, do not want to modify the fields under the Keynote B, then you do not have to include it at all, and you do not pay for that at the compilation time. Yeah. And then in the final example that I have put on Godbolt, we have those additional CPPs which has to be added to support this kind of pimple idiom. And I have also added some of the forward declarations for the types which I have used that way. So there is this nice convention when you prefix the HPP with FWD for the forward declarations. Okay, so this was the result that we had previously. With the pimple idiom enabled, we went down another 30% over, yeah? So this is how we ended up before this new technique that I wanted to show you. So, yeah. But before that, yeah, one more thing, because you have seen that I have defined some of the forward declarations in here, but there were more types in the configuration tree previously. And what is missing is here are the forward declaration for the vector-like types. So for example, I had a list of the UEs, not just one. So I had to also somehow make the forward declaration for that. And there is a trick which we can use, because just doing a forward declaration for something like this, it is very tricky, because this is a template which has a default value for the allocator. So you cannot simply forward declare that type without explicitly putting the second template parameter in there. So you could do that, but then you have to always provide the allocator in the code, so it will be very inconvenient. So in here, what we did to get the forward declaration for the vector was actually something that is often forbidden by the guidelines, by simply inheriting from the STL container. You can give a type, not just using, like previously, alias for the type, but you can create another type for this given one. So you can then just forward declare it. Yeah, and by that, I have like complete list of all the forward declaration for all the types that were used in my configuration tree. Okay, and now finally to this new techniques, because yeah, the stuff that I have shown you previously was like the necessary background, because we have seen that we have used all the like tools that we have in our belt. We have put more cores on it. We have used Unity builds. We have tried some like hiding of the dependencies and so on. But now we want something even better. So on this chart, you can see that there is like a spectrum of how heavy given include is. So on the green side, we have the forward declarations, which are basically free. And then on the other side, we have the headers, which can be very heavy. And what we did is that we have introduced something in the middle that will be very lightweight. And we actually wanted this to be as fast as the forward declaration. So basically, we can use this for free in the code. Yeah, but we can still access the data in the structure. So this is the motivation, and this is how the use of the LCDA looks like. So first I will show you how you define some accessors, and then you will see how it is implemented. So at the top, there is an include to the library, followed with some forward declaration, and this is very important because those are only the forward declaration. We try to not include anything other in here. At the very end, we are declaring the accessors that can be used. So for example, from the configuration, you can get the Keynote field, yeah, or you can get this i7 integer. So we have the header, and then you have also the CPP, which is implementing those accessors. Yeah, so there is a pair, header and CPP. Okay, the structure is here similar, so we have the implementation header. We here include the full type definition, so this is the heavy header, and in here the macros which are used to implement all these magical accessors. And what happens later in the code, this is something that you have to get used to, because we are switching from this syntax where we are calling methods on objects into something different. Yeah, so there are two changes in here. You see, previously there was a configuration included, yeah, and the fields accessed. Now you have the LCDA header and this LCDA macro under the includes. And what is actually also interesting is that we had to add more includes after changing that. Initially we had the full type. Now we have only this LCDA header, which doesn't have the information about the types which are deeply in the tree. We have only the top level, so you have to include them explicitly if you want to use them. But the benefit from doing this is that there is no longer the include to the configuration in this file. Okay. Yeah, and then this is how this looks on Godbolt. So you can take a look at this small library that I have added in there, the decal, impl, and there is also one like helper file. And then we are adding those two, the header for the LCDA and the CPP. Okay, and of course, you can use this also on the containers. We have a specific macro for the declaration in here, but the idea here is similar, that you only include the forward declarations of the element and the container, and you define the accessors. In this case, it will automatically expand like to some add functions, the size, and so on. Yeah, and then the similar thing in the CPP. So you have the full type inclusion in the CPP, the forward declarations in the header. Yeah. And now, going back to this small example, this is the state before the LCDA was applied for the container. You see the normal calls to the add methods. When doing the migration, you have to shuffle some braces, yeah? Instead of calling add, we are adding this kind of call to the macro. And you see that this is very incremental. You can migrate one type at one type at time, yeah, and you do not have to do this all at once. Yeah, and then the final one, this is where the migration was completed, is that this was the state before, and this is the state after. Yeah, so this is like very trivial conversion in the code, but you have to get used to it. But if you do it, then none of those types which are actually used in here are included in the CPP file. Yeah, because everything is hidden behind the forward declaration, and you only use those accessors. Yeah. So there is the complete type in here. And now, how this works? So the decal from here, this basically expands to a function declaration prefixed with this LCDA at the beginning, and this is actually very crucial. You see in a moment. So very simple thing. If compiler sees that macro in the code, it will like immediately expand this to the function declaration. So this is very lightweight to compile. The implementation, also very simple. You generate those functions which corresponds to what was defined in the header. Yeah, so you can then provide the implementations for the compiler. And finally, those strangely looking, that strangely looking syntax with the LCDA macro, this is actually done for one single purpose. So we can write the expression from left to right instead of the another way around. Yeah, so this second example in here, you see that we are starting from calling add, then cells, then again add, and so on. But this one is much more readable. Yeah, but under the hood, under this macro, we are only adding like simple function calls. And the reason behind this is, again, to not force compiler to do any work. We are expanding to function calls, and then compiler will just go through them as if there was nothing to do actually in the code. Yeah. And there is also another trick, because sometimes you might not want to have this function call overhead in your code. So this can be actually quite easily achieved. Only thing you have to do is just to include the implementation of those accessors somewhere in the code. Yeah. So we go from this, from the header of the LCDA, we include the CPP, and in the CPP, when this flag is enabled, the code that is generated will be slightly changed. So we will put the inline at the beginning. Okay, and I have actually also measured that. We have the test framework internally using like both of those approaches, and there is basically like no approach because the compiler is quite. This is quite light for the compiler to inline. Yeah, so easy to inline, easy to compile. And the result from doing that, this is the initial build time using like the 8 cores without this approach and without also the pimple things that we did previously. And this is how it looks with this LCDA approach applied. So you see, basically, Unity build size 2, and we are already done. Yeah, and only on 8 cores. Yeah, we went down from 136 seconds down to 11. And if you even wanted to regain all the performance in the code by eliminating the function calls, you can enable the LTO. And you see that only like 2 seconds were added to the example in here. Yeah. So this is how this looks like. And another example, this might be also quite illustrative because I have shown you here the time that is visible for the user. So from the time he starts the command until he gets the results. But also what is important is how actually the machine is loaded. So we have the user time from all those parallel compilations, 920 seconds. We go down by 95%, yeah, by using this technique. So basically, all the work that the compiler had to do in the CPPs, it disappears because basically you are almost including nothing from those heavy headers. And then the total build, only 5% of the original one. And what is interesting, after enabling LTO in here, it went even down. Yeah, so this was quite surprising for me, but probably the compiler, when the LTO is enabled, is doing a bit less work during the compilation and is shifting that to the link time. Yes, so if you look at the user time, it will reduce it, but if you look at the real time, it will bump it up a bit, yeah, because the LTO phase might be quite long. Yeah, this will depend on how your code looks like. Yeah, so basically, this simple modifications, and we get the 150 times speed up. So this is the 2 orders of magnitude that I have promised you at the beginning. And some other examples maybe to also show you why the gains are so heavy. This is how the configuration types look like, and we see the inclusion at the level 0. Then at the level 1, it starts to becoming interesting. Level 2, 3, 4, and 5. Yeah, and I stopped in here. Those 2 blobs that you see in here, This one on the right, this is the boost preprocessor library, and on the left you have the standard library. Yeah, all those dependencies that are pulled into the project. And now, this other approach, we have the LCDA header. We include the forward declaration from it, and basically at the level of 2 we are finishing. And this is like very lightweight because of that. And the final table that I have created for you, those are data from one of our internal tools that we are used to measure the compilation time. And it is able to collect some quite nice statistics at the level of headers. So you can see, for example, that the configuration previously was taking almost 800 megabytes to compile. And this LCDA version, from which you can, again, get the same data, is almost 400 times faster. Yeah, so sorry, not faster, but less memory that is used. Yeah, yeah. For the build time, this was how the header contributed to the total build time before and after. Actually, the tool did not manage to even measure that, so I couldn't guess what was the speed up, but it was probably quite big. And the final one, this is probably the statistic that is the easiest one to get, is the number of preprocessed lines. So we are going from 40,000 to just 30, yeah, at the end, by just using this technique. Okay, so thank you. I guess you can try. Maybe you will see similar results in your projects. So thank you.
Do you have any questions? Okay, we have a question there. Perfect.
Did you consider adding this solution to directly to the compiler to avoid affecting code syntax?
Not yet, but I think that there might be actually a thing that could help, because if we had that unified function called syntax in C++, where you can define the methods on the type, not in the type, but outside of it, then instead of like defining the accessor as separate functions, we could define them actually as those methods which will be added to the type, and then there will be no change in the syntax. Yeah, so this is the kind of thing that I hope for the C++ to add in the future.
Good luck.
Any other questions? Okay, I guess not. So thank you once again.
Thanks.
And I have two things to remind you about. The first one is that you can rate our lectures and the conference app. And the second one is that there will be after party at the Szklarnia bar at Ofiar Oświęcimskich 19. So you can just go there after our conference. It should be at 8:30 p.m. So I hope to see you there. And in 12 minutes, we will have our last lecture for today. So see you later. Hello, hello. Welcome on our last lecture in today's Code Dive conference. I'm very happy to greet on the stage Radek, who's only 20 years old and he's working student at Nokia, and he's already the speaker at the Code Dive conference. It's very nice to host you today. So Radosław Szewczyk is computer science student at the Silesian University of Technology. He's interested in ML, especially in NLP. Likes building models from scratch. Avid C++ user and Python enthusiast. I'm sorry, I'm tired already. Okay, Radosław, the stage is yours. I'm very happy to meet you today.
Okay, thank you very much for a warm introduction. And today I would like to talk about NLP with the side of C++ and Python bindings. I will talk a bit about statistical basics of naive Bayes algorithm and how I have used PyBind 11 to speed up my project, and what are strengths and weaknesses of few options that we'll analyze today. But before we start, let's talk about an elephant in the room. NLP is a subfield of artificial intelligence, and AI is everywhere right now. We have AI toasters, vacuum cleaners, toothbrushes, beehives, perfumes, everything. That's what sells nowadays, right? But in this talk, I will focus on something else. I will focus on creating your own model, not the ChatGPT wrapper. We'll go down to basics at what follows. We have to manage expectations a bit. I won't show you how to build LLM and how to get OpenAI out of business, but how to build a pretty useful tool with C++ and Python. So, NLP, natural language processing, as I said earlier, is a specialized subfield within artificial intelligence and machine learning that focuses on enabling machines to understand, interpret, process, and generate human languages by bridging the gap between human communication and computer interpretation. NLP allows machine to derive meaning from natural language inputs, such as text or speech. The core of NLP lies in combination of computational linguists, which involve rule-based modeling of human language, and statistical, as well as machine learning techniques. Computational linguists. Oh. Is it okay now? Okay. So the core of NLP lies in a combination of computational linguists, which involves rule-based modeling of human language and statistical, as well as machine learning techniques. Computational linguists leverage the experience of language specialists to define language structure, syntax, semantics, and context. When combined with data-driven models and algorithms, this approach equips machine with the ability to process a vast amount of natural language data, recognize patterns, extract insights, and respond accordingly. NLP powers a wide range of applications, including machine translation, text summarization, sentiment analysis, speed recognition, and much, much more. Today, we'll be focusing on creating naive Bayes algorithm. This is a classification algorithm, which is type of predictive modeling technique in machine learning that aims to categorize or to classify data into predefined labels. It is one of the fundamental aspects of supervised learning, where the goal is to learn from labeled training data and use that knowledge to make predictions or to assign labels to new unseen data. Here's how it works. We will feed our program sets of two things, text and the tag. Tag will be sentiment of a given sentence, so whether a sentence is positive or negative. We could also neutral tag, but it would increase our program's complexity. And as you can see, the formula is pretty simple, but let's take a look at the example. So, given the data set of green dots and red dots, so this is our training data, we get a new data point, this uncolored dot in the circle. And now, using the naive Bayes theorem, we have to decide whether the data point belongs to greens or to the reds. A prior probability represents the initial assessment of probability of an event before any additional evidence or data is taken into account. It reflects probability based on previous knowledge, experiences, or assumptions before analyzing new data. Let's suppose you want to determine the probability that randomly selected person is a doctor. If you know from past data that 5% of populations are doctors, your prior probability of selecting doctor is 5%. This is your baseline estimate before starting, before considering any new information. The prior probability serves as a starting point for updating beliefs when new evidence is introduced. A posteriori probability is the revised probability of an event when new data is introduced or is taken into account. It represents the probability of, and is calculated using our Bayes theorem. So, as you can see, it is not complicated. It's pretty straightforward. But why do we need our speedy C++ combined with Python? Why can we only use C++ or Python? So, text processing and tokenizations. Those are fundamental steps in NLP as they help us transform raw data into a format suitable for analysis by filtering out elements that could blur or hinder our results. These unnecessary things typically include non-alphabetical symbols like commas, dots, slashes, exclamation marks, etc., that do not carry meaning in context of model training. In addition to these symbols, numbers may also be removed, but it depends on a specific task. However, one of the most important words to filter out are stop words. Those are common words in a given language, such as a, with, from, at, in, or are, which appear frequently, but usually carry very little information value on their own. By focusing on filtering these elements, we allow our model to capture the words as structures that truly contribute to understanding and prediction. This is where NLP programmers greatly benefit from collaboration with language experts. Our models would become nonsensical without their deep understanding of language nuance and context. It is also important to mention that models trained on English data and with English stop words, etc., are not capable of classifying or processing other languages. Tokenization defines how words are split and affects the overall comprehension of the text by the model. This is a process when we split our text into smaller units like words or subwords called tokens. Improper tokenization can lead to misleading or irrelevant interpretations, emphasizing why this step is so critical. That's where C++ and Python bindings come into play, in these performance-critical areas. But let's start with the question, why even use Python? Why can't we only use C++? And the reasons are kind of obvious. As the Stack Overflow developer survey suggests, Python is a widely popular language. However, take it with a grain of salt. I bet results will be drastically different if we poll this audience. JavaScript wouldn't be first. Python is also simple and quick to code with very low boilerplate and supports tons and tons of libraries. Very powerful and simple to use libraries that are used by millions of professionals across dozens of different fields. So, let's get down to business. Let's merge the two and get the best out of the both worlds. What do we get? First and foremost, we get a lot of speed, especially complex operations when Python lags and C++ excels. As seen on the right-hand side of the slide, a lot of libraries take advantage of said C++ speed, performing mathematical calculations, data processing, or image processing. Secondly, we get to reuse code already written in C++ and use it in a new way, in a new context, without writing everything in Python again. We have a lot of libraries that accomplish the same thing, and here are some of the more popular ones. But today I will focus on PyMind 11 because it is very easy to use and easy to learn. So let me show you how easy it is to start using PyMind 11. We have our hello world function in C++, but we have some new code here. PyMind 11 macro that creates a module named hello module and exposes my function to Python. So what happened here? How C++ can be loaded to Python? How .so file compiled in C++ can be loaded to Python? The answer is CPython. CPython is the implementation of Python language. It is a C program that interprets Python's instructions. It works something like that. In CPython, every object, regardless of its type, is represented by a PyObject. So int, string, function, whatever. It's all represented by PyObjects. The structure contains essential information that all objects share, allowing the interpreter to manage them consistently. The CPython core reads your Python instructions to change its internal state, which is represented by set PyObjects. So the SO file that we have created earlier have instructions that change those PyObjects, so these internal states of CPython interpreter, in your memory. And that's about it. But let's take a look at a real-world example of implementing naive Bayes classificator with PyMind 11. I wanted to have a simple web app that is fast to write and good for data presentation, so I chose Dash. It is an easy-to-use Python library with plenty of features for this project. So, sorry. Let's take a look at the code and how PyMind 11 benefited this project. This is a part of PyMind 11 module macro, which exposes class data frame. The first line defines a new Python class data frame that wraps the C++ data frame and enables Python to interact with it. The std shared pointer part specifies that the data frame object should be managed using shared pointers, which helps manage memory automatically, allowing for shared ownership of data frame objects between Python and C++. M is a PyMind 11 module defined a little bit higher, similarly as in the previous example. So this is a module where the Python class will be made available. Data frame in quotes is the name as it will appear in Python. So let's take a look. What do we have binded there? The first one, def init, is a default constructor of class data frame. Next, we have 4 public data members, which can be read and written directly from Python. Then I have my methods with some default arguments using pyarg. And lastly, we have 2 overloaded operators. Over at the Python side, we have our data class defined and our model class. Then we have our method calls like train, processing line, and predict. And that's about it. As you can see, writing bindings in PyMind 11 is fast and simple, but still very, very powerful. But I said earlier that C++ speedup will benefit data tokenization and preprocessing. So let's take a look at a few functions and benchmark them to see if there is any improvement, and if so, how big. Firstly, let's take a look at Lavenstein distance algorithm. Lavenstein distance is a string metric for measuring the distance between difference between two sequences. The distance between 2 words is a minimum number of single character edits, like insertion, deletion, or substitution, required to change one word into the other. It works by building a matrix when one string is represented on the horizontal axis and second one on the vertical axis. Each cell in matrix represents the cost of converting substring up to that point. The algorithm computes values iteratively by considering the minimum cost among insertion, deletion, and substitution. Ultimately, we find our results at the bottom right cell of the matrix. So, let's take a look at the results. At this point, we have all expected that PyBind P11 to be faster, but for such a simple example, the difference is quite noticeable. So, yeah, but when we add C++, it doesn't look so good after that, but still, difference is very big. Okay, next, let's take a look at data processing function. It processes a single line of text, and it makes a bunch of operations. As I said earlier, it deletes, removes special characters from the line, removes stop words, every time comparing it with Lavenstein distance, and implements simple autocorrect function also with Lavenstein. So just a bunch of words transformation. And the results are much closer this time around, but the difference is still there. But let me introduce you to this middle ground. I mean, it's not really middle ground, but you will see in the moment. Enter Python C API. Python C API is a set of functions, macros, and structures provided by Python implementation, so by our CPython, that allows you to interact with Python code and objects using C or C++. It enables us to write C extensions, create new built-in modules, manipulate Python objects directly from C. This is a backend of PyBind 11. This is what is simplified with PyBind 11 and many libraries alike. Besides that, Python C API enables us to do a lot of cool stuff, like you can embed Python interpreter with a C application using Python C API. This makes it possible to use Python as a scripting language within a larger application. So there's a lot of cool stuff to play around here, but let's come back to our bindings. Here's an example how to expose C++ function to Python using Python C API. First function acts as a bridge between Python and C for our module. It can be called from Python code and takes PyObject self and PyObject args. Args represent the tuple of arguments passed from the Python side. And inside, firstly, we parse arguments from Python. Then we call our C++ function, and then return it as a Python object. In the next function, we are defining module methods, Lavenstein methods, then our module definition, and lastly, module initialization function, pyinit Lavenstein. PyModule create in pyinit Lavenstein creates a new module object using the Lavenstein module definition, and this function is automatically called from Python when module is imported. So there's a lot of occasions to shoot yourself in the foot here, right? But is it worth it? Yes, as always. It is much faster than PyBind 11, as seen on a now updated Lavenstein benchmark. So, why the difference is so big? As I said earlier, PyBind 11 is built on top of Python C API. It acts as a higher level abstraction layer that simplifies the process of creating Python bindings for C++ code by using underlying functionality provided Python C API. It simplifies binding creation. As we've seen, Python C API can be very verbose and requires significant boilerplate to create extensions and handle Python objects. PyBind 11 abstracts away much of this complexity by providing more C++ friendly interface that uses modern C++ features. PyBind 11 also uses Python C API to perform automatic conversions between C++ and Python types, such as translating between C++ std string and Python string, or between C++ containers like vector and Python lists. As all things in life, we have to make trade-offs and choose what works best for our problem. It all boils down to choosing the right tool for a job. If maximum performance is your goal and you want to bind Python and C++, then Python C API offers low-level control and minimal abstraction. It enables you to finally optimize interactions between C and Python, making it ideal for performance-critical tasks. In contrast, PyBind 11 strikes a balance between power and ease of use. Leveraging modern C++ features, greatly simplifies creating Python bindings for C++ code. Automatic type conversions, class bindings, and exception handling make PyBind 11 easy to use, but there is performance penalty due to the higher abstraction level. However, exposing C++ libraries to Python requires extra effort, whether using Python C API or tools like PyBind 11. Directly writing in C++, of course, provides the most control and the best performance for demanding tasks, but limits us in terms of vast range of easy and ready-to-use Python libraries. Writing purely in Python, on the other hand, offers the fastest development and easiest debugging, thanks to Python dynamic typing and rigid libraries. But Python can struggle with performance, particularly in computation-heavy loops and tasks. So if you prioritize rapid development and easy maintenance with acceptable performance overhead, PyBind 11 is excellent choice, as it reduces complexity significantly compared to using Python C API directly. So the conclusion is simple. Write it all in assembly, right? But jokes aside, to make the best choice, ask yourself, what is the critical performance need of the project? And is the added development complexity justified by expected performance gains? These are the main two actors here: performance versus complexity. Thank you for your attention. If you have any questions, feel free to ask.
On the right side.
Who has a question?
Thank you for the presentation. My question is, for instance, the natural language processing try to mimicate certain part of what we have knowledge of intelligence. And I would argue that we somehow tied intelligence with speed. So the fastest we can simulate intelligence actually will correlate more in our perception of intelligence. Then how do you find the usability and let's say performance trade-off, as you mentioned in your talk? What do you think is the direction that the people are following these days, or what's your opinion on which side we should invest more? Because what we see in the market, for instance, you see in company NVIDIA and many other companies, what we see is like people moving more towards speed than actual usability to a certain extent. But also I acknowledge that it's something like Python, PyTorch that made machine learning accessible to most people. So what are your thoughts between these two lines, basically? What do you see and what you advise people to follow more?
If I think correctly, if this was you mean, NLP is a very fast and very simple way to, for example, as I said in the talk, to analyze, for example, sentiment, right? So you don't have to have like powerful, beefy NVIDIA GPU to get great performance and very good accuracy with quite simple models, because that's it. You don't have to have LLM to analyze your for example, article for sentiment, right? If that's what you mean, but you can specify maybe a bit more.
I mean, I didn't put in context with which algorithm inside of natural processing. I was just generalizing to the biggest and the ones that we use more in the market. Because, I mean, the way you mentioned between the way we want something easier to use and we also want to trade it for speed.
Yeah, but it's all about the project that you have to work for. In my case, it started with Python being like absurdly slow. I had to like wait 5 days for my file to process, and it wasn't just it's no-brainer to think about something else, because I can't process file 5 days, then have mistake and process another 5 days the same file, right? So it was just a need for that. And also, as you said, in a lot of Python libraries, if you had to write PyTorch in Python, it would be like nightmare, right? It would take 10 years to make your model, to train your model. So that's more of necessity than like a choice.
Do we have another question?
Hello, thank you for your talk. I have a question about, I'm just curious, what is your experience with Python, and how does it impact the way that you approach the language models that you set? Why Python? Why exactly is it better? Is it your preferable way to work with language models?
My preferred way is C++, of course.
Of course.
Of course. But I chose Python for this project. I mean, to write the main code in Python, let's say, because I wanted to have GUI and to present my data somehow, right?
Okay.
And the thought of making it C++ library and taking it a lot of time and a lot of pain that comes with it, and it wasn't worth it. So I just chose Python and make GUI in like 2 hours, right? And just be done. Right? So
all right, thank you. That answers my question. Thanks.
Questions? Okay, I guess not. So thank you, Radosław, once again. And when it comes to you, thank you very much for attending our last lecture for today. Right now you can attend the ending in the main room, and we can see each other at the after party at 8:30 at Ofiar Oświęcimskich 19. So see you there. Thank you very much for attending.